Letter number 1 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy by Leonhard, Euler. Translated by Henry Hunter. Letter 1 of Magnitude or Extension. Madam, the hope of having the honor to communicate in person to your Highness my lessons in geometry, becoming more and more distant, which is very sensible mortification to me, I feel myself impelled to supply personal instruction by writing, as far as the nature of the objects can permit. I begin my attempt by assisting you to form a just idea of magnitude, producing, as examples, the smallest as well as the greatest extensions of matter actually discoverable in the system of the universe. And first, it is necessary to fix on some one determinate division of measure, obvious to the senses, and of which we have an exact idea, that of a foot, for instance. The quantity of this, once established and rendered familiar to the eye, will enable us to form the idea of every other quantity. As to length, great or small, the former, by asserting how many feet it contains, and the latter, by ascertaining what part of a foot measures it. For, having the idea of a foot, we have that also of its half, or its quarter, or its 12th part, denominated an inch, of its 100th, and of its 1000th part, which is so small as almost to escape the sight. But it is to be remarked that there are animals, not of greater extension than this last subdivision of a foot, which, however, are composed of members through which the blood circulates, and which again contain other animals, as diminutive compared to them as they are compared to us. Hence it may be concluded that animals exist, whose smallness eludes the imagination, and that these again are divisible into parts unconceivably smaller. Thus, for example, though the 10,000th part of a foot be too small for fight, and, compared to us, ceases to be an object of sense, it nevertheless surpasses in magnitude certain complete animals, and must, to one of those animals, were it endowed with the power of perception, appear extremely great. Let us now make the transition from these minute quantities, in pursuing which the mind is lost, to those of the greatest magnitude. You have the idea of a mile. The distance from hence to Magdeburg is computed to be 18 miles. A mile contains 24,000 feet, and we employ it in measuring the distance of the different regions of the globe, in order to avoid numbers inconceivably great in our calculations, which must be the case if we used foot instead of mile. A mile, then, containing 24,000 feet, when it is said that Magdeburg is 18 miles from Berlin, the idea is much clearer than if the distance of these two cities were said to be 432,000 feet. A number so great almost overwhelms the understanding. Again, we shall have a tolerably just idea of the magnitude of the earth when we are told that its circumference is about 5,400 miles, and the diameter being a straight line passing through the center and terminating in opposite directions in the surface of the sphere, which is the acknowledged figure of the earth, for which reason also we give it the name of globe. The diameter of this globe is calculated to be 1,720 miles, and this is the measurement which we employ for determining the greatest distances discoverable in the heavens. Of all the heavenly bodies, the moon is nearest to us, being distant only about 30 diameters of the Earth, which amount to 51,600 miles, or 1,238,400,000 feet. But the first computation of 30 diameters of the Earth is the clearest idea. The Sun is about 300 times farther from us than the Moon, and we may say his distance is 9,000 diameters of the Earth. We have a much clearer idea than if it were expressed in miles or in feet. You know that the Earth performs a revolution round the Sun in the space of a year, but that the Sun remains fixed. Beside the Earth, there are 5 other similar bodies, named planets, which revolve around the Sun. 2 of them at smaller distances, Mercury and Venus, and 3 at greater, namely Mars, Jupiter, and Saturn. All the other stars which we see comets expected are called fixed, and their distance from us is incomparably greater than that of the Sun. The distances are undoubtedly very unequal, which is the reason that some of these bodies appear greater than others, but the nearest of them is unquestionably above 5,000 times more distant than the Sun. Its distance from us, accordingly, exceeds 45 million of times the Earth's diameter. That is 77,400,000,000 of miles. And this again, multiplied by 24,000, will give that prodigious distance expressed in feet. And this, after all, is the distance only of those fixed stars which are the nearest to us. The most remote, which we see, are perhaps 100 times farther off. It is probable, at the same time, that all these stars, taken together, constitute only a very small part of the whole universe, relatively to which these prodigious distances are not greater than a grain of sand compared to the Earth. This immensity is the work of the Almighty, who governs the greatest bodies and the smallest. Berlin, 19th of April, 1760. End of Letter 1. Read by Elijah Fisher. Letter number 2 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 2, A Velocity. Flattering myself that your Highness may be pleased to accept the continuation of my instructions, a specimen of which I took the liberty of presenting to you in a former letter, I proceed to unfold the idea of velocity, which is a particular species of extension, and susceptible of increase and of diminution. When any substance is transported, that is, when it passes from one place to another, we ascribe it to a velocity. Let 2 persons, the one on horseback, the other on foot, proceed from Berlin to Magdeburg. We have, in both cases, the idea of a certain velocity, but it will be immediately affirmed that the velocity of the former exceeds that of the latter. The question, then, is wherein conflicts the difference which we observe between these several degrees of velocity. The road is the same to him who rides and to him who walks, but the difference evidently lies in the time which each employs in performing the same course. The velocity of the horseman is the greater of the 2, as he employs less time on the road from Berlin to Magdeburg, and the velocity of the other is less, because he employs more time in traveling in the same distance. Hence it is clear that in order to form an accurate idea of velocity, we must attend at once to 2 kinds of quantity, namely, to the length of the road and to the time employed. A body, therefore, which in the same time passes through double the space which another body does, has double its velocity. If, in the same time, it passes through thrice the distance, it is said to have thrice the velocity, and so on. We shall comprehend then the velocity of a body, when we are informed of the space through which it passes, in a certain quantity of time. In order to know the velocity of my pace when I walk to Leitzow, a village about a league from Berlin, I have observed that I make 120 steps in a minute, and one of my steps is equal to 2.5 feet. My velocity, then, is such as to carry me 300 feet in 1 minute, and a space 60 times greater, or 18,000 feet, in an hour, which, however, does not amount to a mile, for this, being 24,000 feet, would require an hour and 20 minutes. Were I, therefore, to walk from hence to Magdeburg, it would take exactly 24 hours. This conveys an accurate idea of the velocity with which I am able to walk. Now, it is easy to comprehend what is meant by a greater or less velocity. For if a courier were to go from hence to Magdeburg in 12 hours, his velocity would be the double of mine. If he went in 8 hours, his velocity would be triple. We remark a very great difference in the degrees of velocity. The Toro test furnishes an example of a velocity extremely small. If she advances only 1 foot in a minute, her velocity is 300 times less than mine, for I advance 300 feet in the same time. We are likewise acquainted with velocities much greater. That of the wind admits of great variation. A moderate wind goes at the rate of 10 feet a second, or 600 feet in a minute. Its velocity, therefore, is the double of mine. A wind that runs 20 feet in a second, or 1,200 in a minute, is rather strong, and a wind which flies at the rate of 50 feet in a second is extremely violent, though its velocity is only 10 times greater than mine, and would take 2 hours and 24 minutes to blow from hence to Magdeburg. The velocity of sound comes next, which moves 1,000 feet in a second and 60,000 in a minute. The velocity of sound is generally computed at 1,142 feet each second, but varies with the elasticity and density of the air. The Earth travels in her orbit 1,612,000 miles in the space of 24 hours, and, therefore, with a velocity more than 50 times greater than that of a cannonball. Light moves about 13 millions of miles every minute. This velocity, therefore, is 200 times greater than that of my pace, and were a cannon to be fired at Magdeburg, if the report could be heard at Berlin, it would arrive there in 7 minutes. A cannonball moves with nearly the same velocity, but when the piece is loaded to the utmost, the ball is supposed capable of flying 2,000 feet in a second, or 120,000 in a minute. This velocity appears prodigious, though it is only 400 times greater than that of my pace in walking to Leitzow. It is, at the same time, the greatest velocity known upon earth. But there are in the heavens velocities far greater, though their motion appears to be extremely deliberate. You know that the earth turns round on its axis in 24 hours. Every point of its surface, then, under the equator, moves 5,400 miles in 24 hours, while I am able to get through only 18 miles. Its velocity is, accordingly, 300 times greater than mine, and less, notwithstanding, than the greatest possible velocity of a cannonball. The earth performs its revolution round the sun in the space of a year, proceeding at the rate of 128,250 miles in 24 hours. Its velocity, therefore, is 18 times more rapid than that of a cannonball. The greatest velocity, that of light, which moves 2 million miles every minute and exceeds the velocity of a cannonball 400,000 times. 22nd of April, 1760. End of Letter 2. Read by Elijah Fisher. Letter number 3 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 3, of Sound and its Velocity. The elucidations of the different degrees of velocity, which I have had the honor to lay before your Highness, carry me forward to the examination of sound, or noise in general. It must be remarked that a certain portion of time always intervenes before sound can reach our ears, and that this time is longer in proportion to our distance from the place where the sound is produced, a second of time being requisite to convey sound 1,000 feet. When a cannon is fired, those who are at a distance do not hear the report for some time after they have seen the flash. Those who are a mile or 24,000 feet distant hear not the report till 24 seconds after they saw the flame. You must no doubt have frequently remarked that the noise of thunder reaches not the ear for some time after the lightning, and it is by this time we are enabled to calculate our distance from the place where the thunder is generated. If, for example, we observe that 20 seconds intervene between the flash and the thunderclap, we may conclude that the feet of the thunder is 20,000 feet distance, allowing 1,000 feet of distance for every second of time. This primary property leads us to inquire in what sound consists, whether its nature is similar to that of smell, that is, whether sound issues from the body which produces it, as smell is emitted from the flower, by filling the air with subtile exhalations proper to affect our sense of smelling. This opinion was formerly entertained, but it is now demonstrated that from a bell struck nothing proceeds that is conveyed to our ear, and that the body which produces sound loses no part of its substance. When we look upon a bell that is struck, or the string of an instrument when touched, we perceive that these bodies are then in a state of trembling or agitation, by which all these parts are affected, and that all bodies susceptible of such an agitation of their parts likewise produce sound. These shakings or vibrations are visible in the string of an instrument when it is not too small. The tense string A, C, B passes alternately into the situation A, M, B and A, N, B. See Plate 1, Figure 1, in which I have represented these vibrations much more obvious to sense than they are in fact. It must be further observed that these vibrations put the adjacent air into a similar vibration, which is successfully communicated to more remote parts of the air, till it come at length to strike our organ of hearing. It is the air, then, that receives these vibrations, and which transmits this sound to our ear. Hence, it is evident that the perception of sound is nothing else but the impression made by our ear by the concussion of the air, communicated to us through the organ of hearing, and when we hear the sound of a string touched, our ear receives from the air as many strokes as the string performs vibrations in the same time. Thus, if the string performs 100 vibrations in a second, the ear likewise receives 100 strokes in the same time, and the perception of these strokes is what we call sound. When these strokes succeed each other uniformly, or when the intervals are all equal, the sound is regular, and such as is requisite to music. But when the strokes succeed unequally, or when their intervals are unequal among themselves, an irregular noise, incompatible with music, is the result. On considering somewhat more attentively the musical sounds, whose vibrations take place equally, I remark first that when the vibrations, as well as the strokes impressed on the ear, are more or less strong, no difference of sound results from it, and that the stronger or weaker, which produces the distinction termed by musicians forte and piano. But there's a difference much more essential when the vibrations are more or less rapid, that is, when more or fewer of them are performed in a second. When one string makes 100 vibrations in a second, and another string makes 200 vibrations in the same time, their sounds are essentially different. The former is lower, or more flat, and the other higher, or more sharp. Such is the real difference between the flat and sharp sounds, on which all music hinges, and which teaches how to combine sounds different in respect or flatness or sharpness, but in such a manner as to produce an agreeable harmony. In the flat sounds there are fewer vibrations in the same time than in the sharp sounds, and every key of the harpsichord contains a certain and determinate number of vibrations, which are completed in a second. Thus, the note marked by the letter C and the note marked fourth octave makes 1,600 vibrations in the same space of time. A string which vibrates 100 times in a second will give precisely the note C, and if it vibrated only 50 times, the note would be lower or more flat. But with regard to our ear, there are certain limits beyond which sound is no longer perceptible. It would appear that we are incapable of determining either the sound of a string, which makes less than 30 vibrations in a second because it is too low, or that of a string which would make more than 7,552 in a second because such a note would be too high. 26th April, 1760. End of Letter 3. Read by Elijah Fisher. Letter number 4 of Letters on Different Subjects in Natural Philosophy, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 4 of Consonance and Dissonance. I resume my remark that on hearing a simple musical sound, our ear is struck with a series of strokes equally distant from each other, the frequency and number of which, in a given space of time, constitute the difference which subsists between low notes and high, so that, the smaller the number of vibrations or strokes produced in a given time, say a second, the lower we estimate that note, and the greater the number of such vibrations, the higher is the note. The perception of a simple musical sound may, therefore, be compared to a series of dots, equidistant from each other, as if the intervals between these dots be greater or smaller, the sound produced will be lower or higher. It cannot be doubted that the perception of a simple sound is somewhat familiar, or analogous, to the sight of such a series of dots equidistant from each other. We are enabled thus to represent to the eye what the ear perceives on hearing sound. If the distances between the dots were not equal, or were these dots scattered about confusedly, they would be a representation of a confused noise, inconsistent with harmony. This being laid down, let us consider what effects two sounds emitted at once must produce on the ear. First, it is evident that if two sounds are equal, or if each performs the same number of vibrations at the same time, the ear will be affected in the very same manner as by a single note. And in music, these two notes are said to be in unison, which is the simplest accord. We mean by the term accord the blending of two or more sounds heard at once. But if two sounds differ in respect of low and high, we shall perceive a mixture of two series of strokes, in each of which the intervals are equal among themselves, but greater in the one than the other, the greater intervals corresponding to the lower note, and the smaller to the higher. This mixture, or this accord, of two notes may be represented to the eyes by two series of dots arranged on two lines, A, B, and C, D. And in order to form a just idea of these two series, we must have a clear perception of the order which subsists among them, or, in other words, of the relation between the intervals of the one line and the other. Having numbered and marked the dots of each line, and placed number 1 under number 1, those marked with the figure 2 will not exactly correspond, and still less those marked 3. But we find number 11 exactly over number 12, from which we discover that the higher note makes 12 vibrations and the other only 11. If we had not affixed the figures, the eye would hardly have perceived this order. It is the same with the ear, which would with much difficulty have traced it in the two notes which I have represented by two rows of dots. But in the following figure, you discover at the first glance that the upper line contains twice as many dots as the under, or that the intervals in the underline are twice as great as those of the upper. This is undoubtedly next to unison, the simplest of all the cases, in which you can at once discover the order which subsists between these two series of dots. And the same thing holds with respect to the two notes represented by these two lines of dots. The number of vibrations contained in the one will be precisely the double of the vibrations contained in the other, and the ear will easily perceive the pleasing relation of these two sounds, whereas, in the preceding case, it was extremely difficult, if not impossible, to discriminate. When the ear readily discovers the relation subsisting between two notes, their accord is dominated consonance, and if it be very different, or even impossible to catch this relation, the accord is termed dissonance. The simplest consonance, then, is that in which the note produces precisely twice as many vibrations as the low note. This consonance, in the language of music, is called octave. Everyone knows what it means, and two notes which differ precisely in octave harmonize so perfectly, and possesses such a complete resemblance, that musicians mark them by the same letters. Hence it is that in church music the women sing an octave higher than the men, and yet imagine they are uttering the same sounds. You may easily ascertain the truth of this by touching the keys of a harpsichord, when you will perceive with pleasure the delightful accord of all the notes which are just an octave distant, whereas any other two notes whatever will strike the ears less agreeably. 29th of April, 1760. End of Letter 4. Read by Elijah Fisher. Letter number 5 of Letters on Different Subjects in Natural Philosophy, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 5, of Unison and Octaves. Your Highness has by this time remarked that the accord which musicians call an octave strikes the ear in a manner so decided that the slightest deviation is easily perceptible. Thus, having touched the key marked F, that marked F, which is an octave higher, is easily attuned to it by the judgment of the ear only. If the string which is to produce this note be ever so little too high or too low, the ear is instantly offended, and nothing is easier than to put the two keys perfectly in tune. Thus we observe that in singing the voice slides easily from one note to another, which is just an octave higher or lower. But were it required to pass immediately from the note F to the note D, for example, an ordinary singer might easily fall into a mistake unless assisted by an instrument. Having fixed the note F, it is almost impossible, all at once, to make the transition to the note D. What then is the reason of this difference, that it is so easy to make note F harmonize with note F, and so difficult to make note D accord with it? The reason is evident from the remarks already made. It is this, that note F and note F make an octave, and that the number of vibrations of note higher F is precisely double that of note lower F. In order to have the perception of this accord, you have only to consider the proportion of 1 or 2, which, as it instantly strikes the eye by the representation of the dots I formerly employed, affects the ear in a similar manner. You will easily comprehend, then, that the more simple any proportion is, or expressed by small numbers, the more distinctly it presents itself to the understanding, and conveys it to a sentiment of satisfaction. A footnote. In order to have a clear conception of what follows, it must be recollected that the terms relation and ratio are synonymous, and that the author is here considering geometrical proportion, which consists in the number of times that the first term is contained in the second, Fe. End of footnote. Architects, likewise, carefully attend to this maxim, as they uniformly employ in their works proportions as simple as circumstances permit. They usually make the height of doors and windows double the breadth, and endeavor to employ, throughout, proportions capable of being expressed by small numbers, because this is obvious and grateful to the understanding. The same thing holds good in music. Accords are pleasing only in so far as the mind perceives the relation subsisting between the sounds, and this relation is so much more easily perceptible, as it is expressed by small numbers. Now, next to the relation of equality, which denotes two sounds in unison, the ratio of 2 to 1 is undoubtedly the most simple, and it is this which furnishes the accord of an octave. Hence, it is evident that this accord possesses many advantages above every other consonance. Having thus explained the accord, or interval of two notes denominated by musicians an octave, let us consider several notes, as F2, F3, F4, F5, F6, each of which is an octave higher than the one immediately preceding. Since then the interval of F2 from F3, of F3 from F4, of F4 from F5, of F5 from F6 is an octave, the interval of F2 to F4 will be a double octave, that of F2 to F5 a triple octave, and that of F2 to F6 a quadruple octave. Now, while note F2 makes one vibration, note F3 makes 2, note F4 makes 4, note F5 makes 8, and note F6 makes 16. Hence, we see that as an octave corresponds in the relation of 1 to 2, a double octave must be in the ratio of 1 to 4, a triple in that of 1 to 8, and a quadruple in that of 1 to 16. And the ratio of 1 to 4 not being so simple as that of 1 to 2, for it does not so readily strike the eye. A double octave is not so easily perceptible to the ear as a single. A triple is still less perceptible, and a quadruple still much less so. When, therefore, in tuning a harpsichord, you have fixed the note F2, it is not so easy to attune the double octave F4 as the single F3. It is still more difficult to attune the triple octave F6 and the quadruple F7 without rising through the intermediate octaves. These accords are likewise comprehended in the term consonance, and as that of unison is most simple, they may be arranged according to the following gradations. 1. Degree, unison indicated by the relation of 1 to 1. 2. Degree, the immediate octave in the ratio of 1 to 2. 3. Degree, the double octave in that of 1 to 4. 4. Degree, the triple octave in that of 1 to 8. 5. Degree, the quadruple octave in that of 1 to 16. 6. Degree, the quintuple octave in that of 1 to 32. And so on, as long as sound is perceptible. Such are the accords nominated consonances, to the knowledge of which we have been thus far conducted. But hitherto we know nothing of the other species of consonants, and still less of the dissonances employed in music. Before I proceed to the explanation of these, I must add one remark respecting the name octave, given to the internal of two notes, the one of which contains twice the vibrations contained in the other. You see the reason of it in the principal stops of the harpsichord, which rise by 7 degrees before you arrive at the octave C, D, E, F, G, A, B, C, so that stop C is the 8th, reckoning C the 1st. And this division depends on a certain series of musical intervals, the nature of which shall be unfolded in the following letters. 3rd of May, 1760. End of letter 5. Read by Elijah Fisher.
Letter 6 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Claire. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler. Translated by Henry Hunter. Of Other Consonances. It may be affirmed that the relations of 1 to 2, of 1 to 4, of 1 to 8, of 1 to 16, which we have hitherto considered, and which contain the progression of octaves, are all formed by the number 2 only, since 4 is 2 times 2, 8 2 times 4, 16 2 times 8. Were we to admit, therefore, the number 2 alone into music, we should arrive at the knowledge of only the accords or consonances which musicians call the single, double, or triple octave. And as the number 2, by its reduplication, furnishes only the numbers 4, 8, 16, 32, 64, the one being always double the preceding, all other numbers would remain unknown. Now, did an instrument containing octaves only, as the notes marked C2, C3, C4, C5, C6, and were all others excluded, it could not produce an agreeable music, on account of its too great simplicity. Let us introduce then, together with the number 2, the number 3 likewise, and observe what accords or consonances would be the result. The ratio of 1 to 3 presents at once 2 sounds, the one of which makes 3 times more vibrations than the other in the same time. This ratio is undoubtedly the most easily to be comprehended. Next to that of 1 to 2, it will accordingly furnish very pleasing consonances, but of a nature totally different from that of octaves. Let us suppose, then, that in the proportion of 1 to 3, number 1 corresponds to C2. Since note C3 is expressed by number 2, number 3 gives a sound higher than C3, but at the same time lower than note C4, which corresponds to number 4. Now, the note expressed by 3 is that to which musicians affix the letter G, and they denominate the interval from C to G a fifth, because in the keys of a harpsichord, that of G is the fifth from C, as C, D, E, F, G. If then number 1 produces the sound C2, number 2 will give C3, number 3 gives G, number 4 the note C4, and note G4 being the octave of G, the number corresponding to it will be 2 times 3, or 6. Rising still an octave, the sound G5 will correspond to a number twice greater, that is 12. All the notes with which the two numbers 2 and 3 furnish us, indicating note C by 1, therefore are C2, C3, G3, C4, G2, C5, G1, C6. Hence it is clear that the ratio of 1 to 3 expresses an interval compounded of an octave and a fifth, and that this interval, on account of the simplicity of the numbers which represent it, must be, next to the octave, the most grateful to the ear. Musicians accordingly assign the second rank among consonances to the fifth, and the ear catches it so easily that there is no difficulty in tuning a fifth. For this reason, in violins, the 4 strings rise by fifths, the lowest being G3, the second D4, the third A4, and the fourth E5. And every musician puts them in tune by the ear only. A fifth, however, is not so easily tuned as an octave, but the fifth above the octave, as from C to G, being expressed by the proportion of 1 to 3, is more perceptible than a simple fifth, as from C2 to G2, or C3 to G3, which is expressed by the proportion of 2 to 3, and is likewise known by experience, that having fixed the note C, it is easier to attune to it, the higher fifth G than the simple G. If unity had marked the note F, number 3 would mark the note C, so that F2, F3, C4, F4, C5, F5, C6 would be marked by 1, 2, 3, 4, 6, 8, 12, where from F to C the interval is a fifth in the relation of 2 to 3. From F4 to C5, from F5 to C6 are also fifths, as the ratio of 4 to 6 and of 8 to 12 is that as the fame of 2 to 3. For if 2 strings perform in the same time, the one 4 vibrations, the other 6, the former string will make in a time equal to half the first space of time 2 vibrations, and the second in the same time will make 3. Now, the sounds emitted from these strings are the same in both cases. Of consequence, the relation of 4 to 6 expresses the same interval as that of 2 to 3, that is, a fifth. Hence we have arrived at the knowledge of another interval contained in the ratio of 3 to 4, which is that of C4 to F1, and consequently also of C3 to F3, or C2 to F2. Musicians call it a fourth, and being expressed by greater numbers, it is not so agreeable by a great deal as the fifth, and still less of than the octave. Number 3, having furnished us new accords or consonances, namely the fifth and the fourth, before we call in any others, let us take it again 3 times, in order to have the number 9, which will give a higher note than note 3, or C4, 1 octave and 1/5. Now C5 is the octave of C4, and G5 the fifth of C5. Number 9 then gives us the note of G5. Of that, C4, F4, G4, C6 will be marked by 6, 8, 9, 12. And if these notes be taken in the lower octaves, the relations remaining the same, we shall have C2, F2, G2, C3, F3, G3, C4, F4, G4, C5, F5, G5, C6, which leads us to the knowledge of new intervals. The first is that of F to G, contained in the ratio of 8 to 9, which musicians call a second or tone. The second is that of G to F, contained in the ratio of 9 to 16, called a seventh, and which is 1 second or 1 tone less than an octave. These proportions, being already expressed by very great numbers, are not reckoned among the consonances, and musicians call them dissonances or discords. Again, if we take 3 times the number 9, or 27, it will mark a tone higher than C4, and precisely a fifth higher than G. It will be accordingly the tone D4, and its octave D5 will correspond to twice the number 27 or 54, and its double octave D6 to twice the number 54 or 108. Let us represent these tones some octaves lower in the manner following: C2, D2, F2, G2, C3, D3, F3, G3, C4, D4, F4, G4, C5, D5, F5, G5, C6. Hence, we see that the interval from D to F is contained in the ratio of 27 to 32, and that of F to D in the ratio of 32 to 54. The two terms of which are divisible by 2, and then in place of this relation we have that of 16 to 27. The first interval is called a tierce minor, or lesser third, and the other a greater sixth. The number 27 might be still farther multiplied by 3, but music extends not so far, and we limit ourselves to number 27, resulting from 3, multiplied 3 times by itself. Other musical tones still wanting are introduced by means of number 5, and shall be unfolded in my next letter. 3rd of May, 1760. End of letter 6. Letter 7 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Claire. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard, Euler, translated by Henry Hunter. Of the 12 Tones of the Harpsichord. The present subject of my correspondence with Your Highness is so dry that I begin to apprehend it may be growing tiresome. That I may not waste too much time on it, and be relieved from the necessity of recurring frequently to a topic so disgusting, I send you by this conveyance 3 letters at once. My intention in undertaking it was to render visible the real origin of musical notes, with which musicians themselves are almost totally unacquainted. It is not to theory they are indebted for the knowledge of all these sounds, but rather to the secret power of genuine harmony operating so efficaciously on their ears that they have been constrained, if I may be allowed to say it, to receive tones actually in use, though they are not hitherto perfectly agreed respecting their just determination. The principles of harmony are ultimately reducible to numbers, as I have demonstrated, and it has been remarked that the number 2 furnishes octaves only, so that having fixed, for example, the note F, we are conducted to the notes F3, F4, F5, F6. The number 3 afterwards furnishes C2, C3, C4, C5, C6, which differ 1/5 from the preceding series, and the repetition of the same number 3 furnishes again the fifths of the first, namely G2, G3, G4, G5, G6, and finally the third repetition of this number 3 adds farther the notes D2, D3, D4, D5, D6. The principles of harmony, then, being attached to simplicity, seem to forbid our pushing farther the repetition of number 3. Hitherto, accordingly, we have only the following notes for each octave: F2, G2, C3, D3, F3, 16, 18, 24, 27, 32, which certainly would not furnish a very copious music. But let us introduce, in addition to these, number 5, and observe the tone which shall emit 5 vibrations, while F2 emits only 1. Now F3 makes 2 vibrations in the same time, F4 makes 4, and C5 6. The note in question then is between F4 and C6. It is that which musicians indicate by letter A4. the accord of which, with the note F4, is denominated by a greater third and is found to produce a very agreeable concord, being expressed by the very simple ratio of 4 to 5. Farther, note A4 with note C6 produces an accord contained in the ratio of 5 to 6, which is almost as agreeable as the former, and which is denominated a lesser third, represented by the ratio of 27 to 32, and its difference from the first is almost imperceptible to the ear. The same number 5 being applied to the other notes G2, C3, D3 will give us in like manner their greater thirds taken in the second octave below, that is to say, the notes B4, C5, and F6, which being transposed will give the following notes with their corresponding numbers: F2, F sharp, G2, A2, B2, C3, D3, E3, F3, 128, 135, 144, 160, 180, 192, 216, 240, 256. Take away the notes F sharp and you will have the principal touches of the harpsichord, which according to the ancients constitutes the genus denominated diatonic, resulting from number 2, from number 3, thrice repeated, and from number 5. Admitting these sounds only, we are in condition to compose harmonies very agreeable and various, the beauty of which is founded on the simplicity alone of the numbers corresponding to the notes. Finally, upon applying a second time the number 5, we shall be furnished with the thirds of the 4 new tones, A, E, B, and F sharp, which we have just found. We shall have the notes C sharp, G sharp, D sharp, and B, so that now the octave is completed of the 12 tones received in music. All these tones derive their origin from the 3 numbers 2, 3, and 5, multiplying 2 by itself as often as the octaves require, but we carry the multiplication of 3 only to the third stage, and of 5 to the second. All the tones of the first octave are contained in the following table, in which you will see how the fundamental numbers 2, 3, and 5 enter into the composition of those which express the relation of these notes. Table: 13 rows, 15 columns. Row 1, Ut or C. 2, 2, 2, 2, 2, 2, 3, blank, blank, blank. 384. Row 2, Ut sharp or C sharp. 2, 2, 2, 2, 5, 5, blank, 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 blank. 400, difference of 16. Row 3, Re or D. 2, 2, 2, 2, 3, 3, 3, blank, 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 blank. 432, difference of 32. Row 4, Re sharp or D sharp. 2, 3, 3, 5, 5, blank, 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 blank. 450, difference of 18. Row 5, Mi or E. 2, 2, 2, 2, 2, 3, 5, blank, 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 blank. 480, difference of 30. Row 6, Fa or F. 2, 2, 2, 2, 2, 2, 2, 2, 2, blank, blank. 512, difference of 32. Row 7, Fa sharp or F sharp. 2, 2, 3, 3, 3, 5, blank, 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 540, difference of 28. Row 8, Sol or G, 2, 2, 2, 2, 2, 2, 3, 3, blank, 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 576, difference of 36. Row 9, Sol sharp or G sharp, 2, 2, 2, 3, 5, 5, blank, 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 600, difference of 24. Row 10, La or A, 2, 2, 2, 2, 2, 2, 2, 5, blank, 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 640, difference of 40. Row 11, Phi flat or B flat, 3, 3, 3, 5, 5, blank, 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 675, difference of 35. Row 12, Phi natural or B natural, 2, 2, 2, 2, 3, 3, 5, blank, 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 720, difference of 45. Row 13, Ut or C, 2, 2, 2, 2, 2, 2, 2, 3, 3, blank, blank, 768, difference of 48. End of table. While note C makes 384 vibrations, the tone C sharp gives 400, and the others as many are as marked by their corresponding numbers. Note C3 will give then, in the same time, double the number of vibrations marked by 384, that is 768. And for the following octaves, you have only to multiply these numbers by 2, by 4, or by 8. Accordingly, note C4 will give twice 768, or 1,536 vibrations. Note C5 twice 1,536, or 3,072 vibrations, and note C6 twice 3,072, or 6,144 vibrations. In order to comprehend the formation of sounds by means of these numbers 2, 3, and 5, it must be remarked that the points placed between the numbers in the preceding table signify that they are multiplied into each other. Thus, taking the tone F sharp, for example, the expression 2, 2, 3, 3, 3, 5 signifies 2 multiplied by 2, that product by 3, that again by 3, that again by 3, and that by 5. Now 2 by 2 makes 4, that by 3 makes 12, that by 3 makes 36, that by 3 make 108, and that by 5 make 540. Hence it is seen that the differences between these tones are not equal among themselves, but that some are greater and others less. This is what real harmony requires. The inequality, however, not being considerable, we commonly look on all these differences as equal, denominating the interval from one note to another, semitone, and thus the octave is divided into 12 semitones. Many modern musicians make them equal, though this be contrary to the principles of harmony, because no 1/5 or third is perfectly exact, and the effect is the same as if these tones were not perfectly in tune. They likewise admit that we must give up exactness of accord in order to obtain the advantage of equality of semitones, so that the transposition from any one tone whatever to another may in no respect injure the melody. They acknowledge, however, that the same piece played in the tone of C, or a half tone higher, that is, C sharp, must considerably affect its nature. It is evident, therefore, that in fact all semitones are not equal, whatever efforts may be made by musicians to render them such, because true harmony resists the execution of a design contradictory to its nature. Such, then, is the real origin of the musical notes already in use. They are derived from the numbers 2, 3, and 5. Were we farther to introduce number 7, that of the tones of an octave would be increased, and the art of music carried to a higher degree of perfection. But here the mathematician gives up the musician to the direction of his ear. 3rd of May, 1760. End of Letter 7. Letter 8 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Claire. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard, Euler. Translated by Henry Hunter. Of pleasure derived from fine music. It is a question as important as curious. Whence is it that a fine piece of music excites a sentiment of pleasure? The learned differ on this subject. Some pretend that it is mere caprice, and that the pleasure produced by music is not founded on reason, because what is grateful to one is disgusting to another. This, far from deciding the question, renders it only more complicated. The very point to be determined is, how comes it that the same piece of music produces effects so different, seeing all admit that nothing happens without reason? Others maintain that the pleasure derived from fine music consists in the perception of the order which pervades it. This opinion appears, at first sight, sufficiently well-founded and merits a more attentive examination. Music presents objects of two kinds, in which order is essential. The one relates to the difference of the sharp or flat tones, and you will recollect that it consists in the number of vibrations performed by each note in the same time. This difference, which is perceptible between the quickness of the vibrations of all sounds, is what is properly called harmony. The effect of a piece of music, of which we feel the relations of the vibrations of all the notes that compose it, is the production of harmony. Thus, two notes which differ an octave excite a perception of the relation of 1 to 2, a fifth of that 2 to 3, a greater third of that 4 to 5. We comprehend, then, the order which is found in harmony when we know all the relations which pervade the notes of which it is composed, and it is a perception of the ear which leads to this knowledge. This perception, more or less delicate, determines why the same harmony is felt by one and not at all by another, especially when the relations of the notes are expressed by somewhat greater numbers. Music contains, besides harmony, another object equally susceptible of order, namely the measure, by which we assign to every note a certain duration, and the perception of the measure consists in the knowledge of this duration and of the relations which result from it. The drum and cymbal furnish the example of a music in which measure alone takes place, as all the notes are equal among themselves, and then there is no harmony. There is likewise a music consisting wholly in harmony, to the exclusion of measure. This music is the choral, in which all the notes are of the same duration, but perfect music unites harmony and measure. Thus, the connoisseur who hears a piece of music, and who comprehends by the acute perception of his ear all the proportions on which both the harmony and the measure are founded, has certainly the most perfect knowledge possible of that music, while another who perceives these proportions only in part or not at all, understands nothing of the matter, or possesses at most a very slender knowledge of it. But the sentiment of pleasure excited by fine music must not be confounded with the knowledge of which I have been speaking, though it may be confidently affirmed that a piece of music cannot produce any, unless the relations of it are perceived. For this knowledge alone is not sufficient to excite the sentiment of pleasure. Something more is wanting, which no one hitherto has unfolded. In order to be convinced that the perception alone of all the portions of a piece of music is insufficient to produce pleasure, you have only to consider music of a very simple construction, such as goes in octaves alone, in which the perception of proportions is undoubtedly the easiest. Such music would be far from conveying pleasure, though you might have the most perfect knowledge of it. It will be said, then, that pleasure requires a knowledge not quite so easily attained, a knowledge that occasions some trouble, which must, if I may use the expression, cost us something, but in my opinion neither is this a satisfactory solution. A dissonance, the relations of which are expressed by the highest numbers, is caught with more difficulty. A series of dissonances, however, following without choice and without design, cannot please. The composer must therefore have pursued in his work a certain plan, executed in real and perceptible proportions. Then a connoisseur, on hearing such a piece and comprehending, beside the proportions, the very plan and design which the composer had in view, will feel that satisfaction which constitutes the pleasure produced by exquisite music to an ear accustomed to relish the beauties and delicacies of that enchanting art. It arises then from divining in some measure the views and feelings of the composer, whose execution, when fortunate, fills the soul with an agreeable sensation. It is a satisfaction somewhat similar to that which is derived from the sight of a well-acted pantomime, in which you may conjecture by the gesture and action the sentiments and dialogue intended to be expressed, and which presents besides a well-digested plan. The enigma of the chimney sweeper, which was so diverting to your highnesses, furnishes me with another excellent comparison. When you can guess the sense and discover that it is perfectly expressed in the proposition of the enigma, you feel a very sensible pleasure on making the discovery. But insipid and incongruous enigmas produce none. Such are, if I may be permitted to judge, the true principles on which decisions respecting the excellency of musical compositions are founded. 6th of May, 1760. End of Letter 8.
Letter 9 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Prajakta. Letters on Different Subjects in Natural Philosophy, Volume 1 by Leonhard Euler. Translated by Henry Hunter. Compression of the air. The explanation of sound, which I have had the honor to present to your Highness, leads me forward to a more particular consideration of air, which, being susceptible of a movement of vibration, such as that by which musical strings, bells, and other sonorous bodies are agitated, transmit the concussion to our ears. It will be immediately asked, what is air? For it does not appear at first sight to be a material substance. As we perceive no sensible body in it, surrounding space seems to contain no matter whatever. We feel nothing. We can walk and move every limb in it without meeting the slightest obstacle. But you have only to move your hand briskly to be sensible of some resistance, and even to perceive a stream of wind excited by that rapid movement. Now, the wind is nothing else but air put in motion, and feeling it is capable of producing effects so surprising, how is it possible to doubt that air is a material substance and consequently a body? For the terms body and matter are synonymous. Body is divided into two great classes, solid and fluid. The air, it is evident, must be referred to the class of fluids. It has several properties in common with water, but it is much more subtle and fine. Experiments have ascertained that air is about 800 times more subtle and more rarefied than water, and that if air were to be rendered 800 times denser than it is, it would have the same consistency as the other fluid. A principal property of air by which it is distinguished from other fluids is its quality of being compressed or reduced into a smaller space. This is demonstrated by the following experiment. Take a tube of metal or glass ABCD, plate 1 figure 2, close shut at the end AB and open at the other, into which is introduced a piston filling exactly the cavity of the tube. On pushing the piston inwards, when it has arrived at the middle E, the air which occupied at first the cavity ABCD will be reduced one half and consequently will have become twice as dense. If the piston is pushed still farther in, as far as F, halfway between B and E, the air will be reduced to a space 4 times smaller than at first, and if you continue to drive forward the piston to G, so that BG shall be the half of BF or the eighth part of the whole length BD, The same air which in the beginning was expanded over the whole cavity of the tube will be contracted to a space 8 times smaller. Going on in the same manner, to contract it into a space 800 times smaller, you will obtain an air 800 times denser than ordinary air. It would then be as dense as water, which it would be easy to prove by other experiments. Hence, it appears that air is a fluid substance capable of compression, or in other words, of being reduced to a smaller space, and in this respect, it differs entirely from water. For let the tube ABCD be filled with this last fluid and attempt to introduce the piston, you will find it impossible to drive it forward. Employ what force you may, you will gain nothing. The tube will burst sooner than you can reduce the water to a space sensibly smaller. This then is the essential difference between air and water. The latter is susceptible of no compression, but air may be compressed to any degree you please. The more the air is compressed, the denser it becomes. Thus, the air which occupied a certain space, when compressed or reduced to half that space, becomes twice as dense. If reduced to a space 10 times smaller, it is rendered 10 times more dense, and so on. I have already remarked that could it be rendered 800 times more dense, it would then be as dense as water and consequently as heavy, for weight increases in the same proportion as density. Gold, the heaviest substance with which we are acquainted, is likewise the most dense. It is found by experiment to be 19 times heavier than water, and that a mass of gold in form of a cube of 1 foot would weigh 19 times a mass of water of the same dimensions. Now such a mass of water weighs 70 pounds. The mass of gold therefore would weigh 19 times 70, that is 1330 pounds. It follows that were it possible to compress air till it were reduced to a space 19 times 800, that is 15,200 times smaller, it would become as dense and as weighty as gold. But it is very far from being possible to carry the compression of air to that degree. You may at first without difficulty drive forward the piston, but the farther you advance, the resistance becomes more powerful, and before you are able to reduce the air to a space 10 times smaller, such a force must be employed as would burst the tube unless it were of uncommon strength. And not only would such a force be necessary to drive the piston farther, but an equal force would be required to keep it in that state, for on the slightest relaxation of the power, the compressed air would drive it backward. The more compressed the air is, the more violent are its efforts to expand and to recover its natural state. This is what we call the spring or elasticity of the air, of which I propose to treat in my next letter. 10th May 1760. End of letter 9. Letter 10 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Prajakta. Letters on Different Subjects in Natural Philosophy, Volume 1 by Leonhard Euler. Translated by Henry Hunter. Letter 10. Rarefaction and Elasticity of the Air. I have remarked that air is a fluid about 800 times more subtle than water, so that could water, without being reduced to vapor, be expanded over a space so many times greater, and could become of consequence so many times more subtle, it would be of a familiar consistence with the air which we breathe. But air has a property which water has not, that of suffering compression into a smaller space and of being proportionably condensed, as I demonstrated in the preceding letter. And we discover in air another property no less remarkable. It is capable of being expanded over a greater space and thus rendered still more subtle. This operation is called the rarefaction of air. You have only to take as before a tube A, B, C, D, plate 1, figure 3, at the bottom of which AC, let there be a small aperture O, so that on introducing the piston as far as to F, the air may escape by that aperture without being condensed. The air which now occupies the cavity ACEF will then be in its natural state. Let the aperture O be closely stopped. On drawing back the piston, the air will gradually expand through the greater space so that when the piston is brought back to the point G, the space CG being double the space CF. The same air which was contained in the space ACEF will fill the space twice as great. It will be, of course, only half as dense, or, which is the same thing, twice as rare. If you draw back the piston to the point H, the space CH being 4 times as great as the space CF, the air will become 4 times as rare as it was at first, as it is then expanded over a space 4 times as great. And could the piston be drawn back till the space became 1000 times as great? The air would still equally expand through that space and consequently become 1000 times as rare. Here then, likewise, air differs essentially from water. For if the cavity ACEF were filled with water, to no purpose would you draw back the piston, the water would continue to occupy the same space as at first, and the rest would remain empty. Hence, we see that the air possesses an intrinsic power of expanding itself more and more, which it exerts not only when it is condensed, but also when rarefied. In whatever state of condensation or rarefaction the air may be, it makes unremitting efforts to extend itself over a larger space and is continually expanding so long as it meets no obstacle. This property is called the elasticity of air, and it has been demonstrated by experiments which I shall presently describe, that this elastic power is in proportion to the density. In other words, the more the air is condensed, the greater are its efforts to expand itself, and the more rarefied it is, the feebler are those efforts. It will be demanded perhaps why the air now in my chamber does not make its escape by the door, being endowed with an expandability continually impelling it to occupy a greater space? The answer is obvious. This would infallibly happen did not the external air make equal efforts to extend itself, but the efforts of the air of the chamber to get out and that of the external air to press in being equal, they balance each other and remain in a state of rest. Had the external air accidentally acquired a greater degree of density, that is, more elasticity, it would, in part, force its way into the chamber where the air being compressed would likewise acquire a greater degree of elasticity. This current would accordingly last till the elasticity of the internal became equal to that of the external air. And should the air of the chamber suddenly become more dense and its elasticity greater than that of the external air, it would force its way out, and its definitely gradually diminishing, its elasticity too would diminish till it became equal to the external air. The current would then cease and the air in the chamber would be in equilibrium with the external. Free air then is in a state of rest only when it has the same degree of elasticity with that which surrounds it. And as soon as that of the one tract becomes more or less elastic than the adjoining, the equilibrium can no longer subsist. But if the elasticity is greater, the air will expand itself and slide into spaces where it is smaller, and from this motion of the air results the wind. Footnote: Wind, the action of the moon upon the atmosphere and the motion of the earth's rotation likewise produce regular winds. Chains of mountains sometimes change the direction of winds. Hence we see that the known cause of currents of air are of three kinds: regular, accidental and local. FE. End of footnote. Hence it comes to pass that the elasticity of the air is sometimes greater, sometimes less in the same place, and this variation is indicated by the barometer, the description of which merits a particular consideration. I confine myself at present to these qualities of air, its condensation and rarefaction, entreating you to recollect that the more condensed it is, the greater power of expansion or elasticity it acquires, and that, on the contrary, the more it is rarefied, the more this quality is diminished. Experimental philosophers have invented one machine for rarefying of air and another for condensing it. The former is called the air pump, the latter the condenser. These machines serve to perform many curious experiments with which you are already well acquainted. I reserve to myself, however, the liberty of recapitulating some of them because they are necessary to elucidate and explain the nature and properties of air, which, as they powerfully contribute to the preservation of animals and the production of plants, press upon us the importance of forming a just idea of them. 14th May 1760. End of Letter 10. Letter 11 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Prajakta. Letters on Different Subjects in Natural Philosophy, Volume 1 by Leonhard Euler. Translated by Henry Hunter. Gravity of the air. I have endeavored to demonstrate that the air is a fluid endowed with the particular property of suffering compression into a smaller space and of expanding into a greater when no obstacle interposes. This property of air, known by the name of spring or elasticity, from its resemblance to a spring, which it requires an effort to unbend, and which resumes its form as soon as the effort ceases, is accompanied by another in common to it with all bodies in general, namely gravity or weight, in virtue of which all bodies tend toward the center of the earth and by which they are under the necessity of falling down unless supported. The learned are very much divided and very uncertain, reflecting the primary and mechanical cause of this power, but its existence is undubitable. Daily experience evinces it. We know even the quantity of it and can measure it exactly. For the weight of a body is nothing else but the power which constrains it to descend, and as the weight of every body may be exactly measured, we know perfectly well the effect of gravity, though the cause or that invincible power which acts upon all bodies, forcing them to descend, may be absolutely unknown to us. It follows that the more matter any body contains, the heavier it is. Gold and lead are heavier than wood or a feather, and as they contain more matter in the same bulk or in the same extent. But as air is a very subtle and thin substance, and its gravity, of consequence, very little, this property usually escapes our senses. Experiments, however, may be made capable of producing full conviction that it possesses gravity. You have seen how the air may be rarefied in a vessel or a tube, and by means of the air pump, This rarefaction may be carried so far as almost entirely to exhaust the air and to leave the receiver sensibly a vacuum. Or you may take a tube ABCD, plate 1 figure 4, into which you introduce the piston so as perfectly to touch the bottom and to leave no air between the two surfaces. To perform the experiment with more advantage, let there be at the bottom of the tube a little aperture G through which the air may escape as the piston is pushed forward. Let the aperture then be closely stopped that not a particle of air may be included between the piston and the bottom of the tube. Having made this arrangement, draw back the piston and the external air not being able to force its way into the tube, there will remain between the bottom of the tube and the piston a perfect vacuum, which may be increased at pleasure by continuing to draw back the piston. You may thus exclude the air contained in a vessel, and such vessel reduced to a vacuum, being tried in accurate scales, will be found to weigh less than when filled with air. Hence we deduce this very important conclusion that the air contained in an empty vessel increases its weight and that the air itself possesses gravity. Were the vessel large enough to contain 800 pounds of weight of water, we might discover by this experiment that the body of air which fills it would weigh nearly 1 pound. Hence we conclude that air is 800 times lighter than water. I must be understood as speaking of the common air which surrounds us and which we breathe, for you know that with the assistance of art, air may be compressed by forcing it into a smaller space and its gravity thereby increased. Were the vessel which I have mentioned to be filled with air compressed to twice the consistency of common air, it would weigh 2 pounds more than when empty. Were it filled with air 800 times more compressed than common air, it would weigh 800 pounds more than when empty, that is, as much as if it were filled with water. The air, then possessing a certain degree of gravity, though in the natural state of this fluid, its gravity is extremely small, it must, however, as well as all other bodies, tend toward the center of the earth and consequently presses on everything which opposes this tendency. For this reason, the superior air presses downward on the inferior, and this last undergoes a compression from the weight of the whole mass of air which is above it. Hence it comes to pass that in these regions the air has a certain degree of compression or density which is the effect of the gravity of the superior air, and that if the superior air had more or less gravity, the air which surrounds us would likewise become more or less dense. It is thus that the air below supports the weight of the superior air, and that the more we ascend, the more it loses its density and rarefies, so that were it possible to continue to ascend, the air would at length be totally lost, or would become so subtle and so rarefied as to be no longer perceptible. Were you to descend, on the contrary, into a very deep pit, you would find the density of the air continually increasing from the increase of the mass of air pressing downward upon it. 17th May 1760. End of Letter 11.
Letter 12 of Letters on Different Subjects in Natural Philosophy, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 12 of the Atmosphere and the Barometer. Having demonstrated that air is a fluid, elastic, and possessed of gravity, I proceed to remark that the Earth is surrounded on all sides by this fluid, and that the space which it fills is called the atmosphere. It would be absolutely impossible for a perfect vacuum to exist on any part of the Earth's surface, for the air of the adjoining regions, compressed by the weight of the superior air and making incessant efforts to dilate, would force itself into the empty space and fill it. The atmosphere, therefore, occupies the whole region which surrounds the Earth. The inferior air is continually compressed by the weight of the superior air, and that until the degree of elasticity which results from this compression is able to form an equilibrium to the compressing power. Then, although this air is compressed only in a downward direction, it produces, in virtue of its elasticity, efforts to expand itself not only downwards but sideways also. For this reason, the air in a chamber is as much compressed as the external, which appeared a paradox to contain philosophers. For they reasoned thus: in a chamber, the inferior air is compressed only by the small quantity of superior air included in that chamber, whereas the external air is compressed by the weight of the whole atmosphere, the height of which is immense. But the difficulty is at once removed, but the property which air possesses of expanding itself when compressed in all directions. Now the air in the chamber is at first reduced by the external air to the same degree of compression and elasticity with itself. Hence, whether I am in my chamber or in the open air, I feel the same compression, it being always understood that I mean at the same height, or at the same distance from the center of the earth. For I have already remarked that on getting to the summit of a high tower, or of a lofty mountain, the compression of the air is less, because the weight of the superior air is then diminished. Various phenomena confirm this state of the compression of the air. Take, for instance, Plate 1, Figure 5, a tube A, B, close at the end. A, having filled it with water or any other fluid, invert it so that the open end B may be undermost, and you will find that the fluid does not run out. The elasticity of the air acting at B in opposition to the fluid supports it in the tube. But if you make any aperture tuned to the tube at A, the fluid immediately descends. The air which is admitted by the aperture acts then from above by its pressure upon the water and forces it downward, which demonstrates that while the tube was close at top, it was the external air which supported the water in it. And were such a tube to be placed in a receiver from which the air was extracted by the air pump, the fluid would instantly descend. The ancients, to whom this property of air was unknown, alleged that nature supported the water in the tube from the horror which it has of a vacuum. For, said they, were the fluid to descend, there must be a vacuum at the upper end of the tube, as the air could find no admission into it. According to them, therefore, it was the horror of a vacuum which kept the fluid suspended in the tube. It is now demonstrated that it is the force of the air which supports the weight of the fluid in the tube, and as this force has a determinate quantity, the effect cannot exceed a certain limit. It is found by experiment that if the tube AB is more than 33 feet in length, water will no longer remain suspended in it, but will run out till it comes to the height of 33 feet. The space left atop will, of course, be a real vacuum. The force of the air then cannot support the water in the tube at more than the height of 33 feet. And, as the same force supports the whole atmosphere, it is concluded that a column of the atmosphere is of equal weight, the basis being equal with a column of water 33 feet high. If, instead of water, you were to use mercury, which is 14 times heavier, the force of the air could support it in the tube at the height of only 28 inches. And if you go beyond that, the mercury descends, till its height corresponds to the pressure of the atmosphere, leaving the space atop in the tube a vacuum. Such a tube closed above and open below, being filled with mercury, forms the instrument called the barometer, by means of which it has been discovered that the atmosphere is not always of equal gravity, for its real gravity is ascertained by the barometer from the height of the mercury, which, as it rises or falls, indicates that the density of the air, or the pressure of the atmosphere, is increasing or diminishing. 20th of May, 1760. End of Letter 12. Read by Elijah Fisher. Letter number 13 of Letters on Different Subjects in Natural Philosophy, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 13, of Wind Guns and the Compression of Air in Gunpowder. Having explained that remarkable property of air which is denominated compressibility, by means of which it is reducible into a smaller space, we are enabled to give an account of several productions of both nature and art. I shall begin with an explanation of the wind gun, though I have no doubt that you are well acquainted with that instrument. Its construction is similar to that of the common fuffle, but instead of powder, we employ condensed air to discharge the bullet. In order to comprehend the process of this operation, it must be observed that air can be compressed only by a force proportional to the degree of condensation which you wish to obtain. In this state, it strives to extend itself, and the efforts which it makes are precisely equal to the force necessary to reduce it to the size which it actually occupies. The more, then, that the air is condensed, the more violent are its efforts to dilate, and if the air is raised to a density twice as great as when it is free, which is the case when we reduce it to half the space which it occupies in its natural state, the force with which it endeavors to expand is equal to the pressure of a column of water 33 feet high. Figure to yourself a great cask of this height, filled with water. This fluid will, undoubtedly, make a strong pressure on the bottom of the vessel. If you make a hole in it near the bottom, the water will force itself out with considerable violence, and on flopping the aperture with your finger, you will be abundantly sensible of this pressure of the water. The bottom of the cask sustains throughout a similar pressure. Now, a vessel containing air twice as dense as that of the atmosphere must undergo precisely such a pressure that if it were not sufficiently strong to sustain it, would burst. The sides, then, of this vessel must be as strong as the bottom of the cask I have mentioned. If in the same vessel the air were 3 times as dense as common air, the force with which it would act upon the sides must be increased in the proportion of 1 more, and would be the same which is sustained by the bottom of a cask full of water, of 66 feet in height. You will easily conceive that this force must be very great, and that it must go on increasing in the same ratio, according to the different degrees of condensation of the air. This being laid down, there is, at the bottom of the air gun, a cavity strongly fortified on all sides, into which the air is more and more compressed, in order to reduce it to as high a degree of density as the force employed for that purpose can admit. The air confined in this cavity will thereby acquire a prodigious power to force itself out, and if an aperture is made, it will fly off with a velocity proportional to that power. Now, there is such an aperture which terminates in the cavity of the tube into which the ball is put. It is closely stopped. But when you wish to discharge the piece, you open, for an instant, the valve which shuts it, and the air rushing forth forces out the ball with all the velocity which we remark in shooting. Every time you discharge, the valve is kept open only a single moment. A certain quantity of air, therefore, and no more, can escape, and enough still will remain for several shot. But on discharge, its density and corresponding elasticity diminish, and for this reason, the latter discharges are less forcible than the former, till the force is at length entirely exhausted. Were the valve to remain open any considerable time, more air would make its escape, which would all go to waste, for this force acts upon the ball only while it is in the barrel of the gun. As soon as it is shot off, it is useless to leave a passage for the air. Hence it appears that were it possible to carry the condensation of this fluid a great deal farther, you will produce from the wind gun the same effects as from the guns and cannons in common use. The effect of artillery is accordingly founded on the same principle. Gunpowder is only a substance which contains in its pores an air extremely confined. Nature produces here the same operations which we employ for compressing the air, but carries a condensation to a much higher degree. All that is necessary is to open the little cavities in which this dense air is confined, that it may have liberty to escape. This is performed by means of fire, which bursts open these little envelopes. The air then suddenly flies off with incredible velocity, and forces before it bullets and balls in a manner entirely similar to that which we have remarked in the café of the wind gun, but with much greater impetuosity. Here, then, are two very surprising effects produced from the condensation of air, with this single difference, that in the one it is the work of art, and in the other that of nature. We see, therefore, in this, as in everything else, how infinitely the operations of human skill are surpassed by those of nature. 24th of May, 1760. End of Letter 13. Read by Elijah Fisher. Letter number 14 of Letters on Different Subjects in Natural Philosophy, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 14. The effect produced by the heat and cold on all bodies, and of the pyrometer and thermometer. Beside the properties already mentioned, air has another very remarkable quality, in common to it with all bodies, not excepting such as are solid. I mean the change produced on it by heat and cold. It is observable, in general, that all bodies being heated dilate or increase in size. A bar of iron made very hot is somewhat longer and thicker than when it is cold. There is an instrument called the Pyrometer, which accurately indicates the slightest differences of length or shortness that a bar of iron undergoes, to which it is applied. You know that in a watch some of the wheels move very slowly, though they communicate motion to others which revolve with considerable rapidity. By a similar mechanism, it is possible, from a change almost imperceptible, to produce one very considerable, as is the case of the pyrometer, which I have just mentioned. It has an index which runs over a very considerable space on the slightest change produced in the length of the body on which the experiment is made. On applying this instrument to a bar of iron, or any other metal, placed over a burning lamp, the index is immediately put in motion, and shows that the bar is becoming longer, and, as the heat increases, the bar likewise increases in length. But on extinguishing the lamp, and the bar growing cold again, the index moves in a contrary direction, and thereby shows that the bar is growing shorter. The difference, however, is so slight that, without the help of this instrument, it would be difficult to perceive it. Yet, this variation is abundantly perceptible in the motion of pendulum timepieces. The use of the pendulum is to regulate the motion. If you lengthen it, the clock goes slower, and if you shorten it, the clock goes faster. Now, it is remarked that in very hot weather all clocks lose time, and proportionably gain it in very cold weather, which clearly demonstrates that the pendulum is lengthened or shortened according to the temperature of the air. All bodies undergo this alteration, but the quantity differs greatly, according to the nature of the substance of which they are composed. In fluids especially, this variability is very perceptible. To ascertain it, take a glass tube B, C, plate 1, figure 6, joined at the end B to a hollow ball A, and let it be filled with any liquor you please up to M. On heating the ball A, the liquor will rise from M toward C. When it becomes cold again, the liquor will fall toward B. This clearly proves that the same liquid occupies a greater space when it is heated, and a smaller when cold. It is likewise clear that this variation must be more perceptible when the ball is large and the tube narrow. For if the whole mass of liquor increases or diminishes by 1,000th part, that 1,000th part will occupy in the tube a space great in proportion to its narrowness. Such an instrument, then, is exceedingly proper to indicate to us the different degrees of heat or cold. For, if the liquor rises or falls, it is a certain indication that the heat is increasing or diminishing. This instrument is called the thermometer, which points out the changes that take place in the temperature of the air, and of the bodies which surround us. It must not be confounded with the barometer, whose use is to indicate the gravity of the air, or rather the force with which it is compressed. This caution is the most necessary, that the barometer and thermometer have a considerable resemblance, being both glass tubes filled with mercury. But their construction and the principles on which they are founded are entirely different. This quantity of body, extension of heat, and contraction by cold belongs likewise in a very superior degree to air. I'll explain it at greater length in my next letter. May 27th, 1760. End of Letter 14. Read by Elijah Fisher. Letter number 15 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 15. Changes produced in the atmosphere by heat and cold. Heat and cold produce the same effect on air as on every other body. Air is rarefied by heat and condensed by cold. From what I have said on the elasticity of air, you easily perceive that a certain quantity of this fluid is not determined to occupy only a certain space, as all other bodies are, but, by its nature, it has a perpetual tendency to dilate, and actually does expand itself, as long as it meets no obstacle. This property of air is denominated elasticity. When this fluid is confined in a vessel, makes efforts in every direction to burst it, and these efforts are greater or less in proportion to its condensation. Hence, we come to this conclusion that the elasticity of air is in exact proportion to its density, so that when its density is doubled, its elasticity is likewise doubled, and that in general a certain degree of elasticity corresponds to a proportional degree of density. It must be remarked, however, that this takes place no longer than while the air preserves the same degree of heat. Whenever it becomes hotter, it acquires greater power of expansion than what corresponded to its density, and cold produces the opposite effect, by diminishing its expansive power. In order, then, to determine the elasticity of a mass of air, it is not sufficient to know its density. You must likewise know its degree of heat. In order to set this in a clear light, let us suppose two chambers closely shut on all sides, but united by a door of communication, and that the heat in both is equal. In order to this, the air in both chambers must have the same degree of density. For were the air more dense and consequently more elastic in the one than the other, part of it would escape from the one and force its way into the other till the density in both were the same. But let us suppose that one of the chambers has become hotter than the other. The air, thereby acquiring a greater elasticity, would of course force itself into the other and reduce that which it found there into a smaller space, till the elasticity in both chambers was brought to the same degree. During this change there will be a current of air through the door from the chamber which is more, into that which is less heated, and when the equilibrium is restored, the air will be more rarefied in the warm apartment, and more condensed in the cold, and yet the elasticity of both will be the same. From this, it clearly follows that two masses of air of different density may have the same elasticity, when the one is hotter than the other, and this circumstance taken into consideration, it may happen that with the same degree of density, they may be endowed with different degrees of elasticity. What I have said of two chambers may be applied to two countries, and hence it may be concluded that when one country becomes warmer than the other, there must, of necessity, be a current of air from the one to the other, and from this results the wind. Here, then, is one fruitful source of winds, though there are, perhaps, others which consist in the different degrees of heat, which prevail in different regions of the earth, and it is demonstrable that the whole air which surrounds the earth could not be in a state of rest, unless that, universally, at equal heights, there were found the same degree, not only of density, but likewise of heat. And should it happen that there were no wind over the whole surface of the earth, it might, with certainty, be concluded that the air would likewise be everywhere equally dense and warm, at equal heights. Now, as this never happens, there must of necessity always be winds, at least in some regions. But these winds are, for the most part, to be met with only on the surface of the earth, and the higher you rise, the less violent winds are. Winds are hardly perceptible at the summit of very high mountains. Their perpetual tranquillity reigns, from which it is impossible to doubt that at considerable elevations the air is always in a state of rest. Hence it follows that in regions remarkably elevated, there universally prevails all over the earth the same degree of density and heat. For were it hotter in one place than in another, the air could not be in a state of rest. And as there is no wind in these elevated regions, it must necessarily follow that the degree of heat there must be universally and always the same, which is a very surprising paradox, considering the great variations of heat and cold which we feel on the surface of the earth, during the course of a year, and even of one day, without taking into the account the difference of climate, that is, the intolerable heats felt under the equator, and the dreadful cold which ever prevails toward the poles of the earth. Experience itself, however, confirms the truth of this astonishing fact. The snow and ice remain equally, summer and winter, on the mountains of Switzerland, and are equally unchangeable on the Cordilleras, lofty mountains of Peru, situated under the very equator, and where there perpetually reigns, nevertheless, a cold as excessive as that of the polar regions. The height of these mountains is not a German mile, or 24,000 feet. From this it may be, with confidence, concluded that were it possible for us to ascend to the height of 24,000 feet above the earth, we should always and universally meet with the same degree of cold, and that cold excessively severe. We should remark there no sensible difference during either summer or winter, under the equator or near the poles. At this height, and still higher, the state of the atmosphere is universally, and at all seasons, the same, and the variations of heat and cold take place near the surface of the earth alone. It is only in these inferior regions that the effect of the rays of the sun becomes perceptible. You have, undoubtedly, some curiosity to know the reason of this. It shall be the subject of the following letter. 31st May, 1760. End of letter 15, read by Elijah Fisher. Letter number 16 of Letters on Different Subjects in Natural Philosophy, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 16. The cold felt on high mountains and at great depths accounted for. It appears very surprising that we should feel the same degree of cold in all regions after we have risen to a certain height, say 24,000 feet, considering that the variations with respect to heat on the earth, not only in different climates but in the same country at different seasons of the year, are so perceptible. This variety, which takes place at the surface of the globe, is undoubtedly occasioned by the sun. It appears, at first sight, that his influence must be the same above and below, especially when we reflect that a height of 24,000 feet, or a mile, though very great with respect to us, and even far beyond the height of the loftiest mountains, is a mere nothing, compared to the distance of the sun, which is about 30 millions of miles. This is, therefore, a very important difficulty, which we must endeavor to solve. For this purpose, I begin with remarking that the rays of the sun do not communicate heat to any bodies, but such as do not grant them a free passage. You know that bodies, through which we can discern objects, are denominated transparent, pellucid, and diaphanous. These bodies are glass, crystal, diamond, water, and several other liquids, though some are more or less transparent than others. One of these transparent bodies, being exposed to the sun, is not heated to such a degree as a body not transparent as wood, iron, etc. Bodies not transparent are denominated opaque. The burning glass, for example, by transmitting the rays of the sun, sets on fire opaque bodies, while the glass itself is not sensibly heated. Water exposed to the sun becomes somewhat warm, only because it is not perfectly transparent, when we see it considerably heated by the sun at the brink of rivers. It is because the bottom, being an opaque body, is heated by the rays which the water transmits. Now, every heated body communicates that heat to all adjoining bodies. The water, accordingly, derives heat from the bottom. If the water be very deep, so that the rays cannot penetrate to the bottom, it has no perceptible heat, though the sun bears upon it. As air is a very transparent body, to a much higher degree than glass or water, it follows that it cannot be heated by the sun, because the rays are freely transmitted through it. The heat which we frequently feel in the air is communicated to it by opaque bodies, which the rays of the sun have heated, and were it possible to annihilate all these bodies, the air would scarcely undergo any change in its temperature by the rays of the sun. Exposed to it or not, it would be equally cold. But the atmosphere is not perfectly transparent. It is even sometimes so loaded with vapors that it loses almost entirely its transparency and presents only a thick fog. When the air is in this state, the rays of the sun have a more powerful influence upon it and heat it immediately. But these vapors rise to no great height. At the height of 24,000 feet and beyond, the air is so subtile and so pure that it is perfectly transparent, and for this reason the rays of the sun cannot immediately produce any effect upon it. This air is likewise too remote for terrestrial bodies to receive a communication of heat from them. They act only upon such as are adjacent. Hence you will easily perceive that the rays of the sun cannot produce any effect in regions of the air very much elevated above the surface of the earth, and that the same degree of cold must always and universally prevail in such regions, as the sun has no influence there, and as the heat of terrestrial bodies cannot be communicated so far. This is nearly the case on the summit of very high mountains, where it is always much colder than on plains and in valleys. The city of Quito in Peru is almost under the equator, and were we to form our judgment from its situation on the globe, we would suppose it oppressed in intolerable heat. The air, however, is abundantly temperature, and differs very little from that of Paris. Quito is situated at a great height above the rayed surface of the earth. In going to it from the seashore, you have to ascend for several days. It is accordingly built in an elevation equal to that of our highest mountains, though surrounded by others still much higher, called the Cordilleras. This last circumstance would afford a reason for thinking that the air there must be as hot as the surface of the earth, as it is contiguous on all sides to opaque bodies, on which the rays of the sun fall. The objection is solid, and no solution can be given but this, that the air at Quito, being very elevated, must be much more subtile and of less gravity than with us, and the barometer, which always stands considerably lower, incontestably proves it. Air of such a quality is not so susceptible of heat as common air, as it must contain less vapor and other particles which usually float in the atmosphere, and we know by experience that air, very much loaded, is proportionably susceptible of heat. I must here subjoin another phenomenon, no less surprising. In very deep pits, and lower still, if it were still possible to descend, the same degree of heat always and universally prevails, and nearly for the same reason. As the rays of the sun exert their influence only on the surface of the earth, and as the heat which they there excite communicates itself up and down, this effect, at very great depths, is almost imperceptible. The same thing holds representing considerable heights. This elucidation will, I flatter myself, prove satisfactory. 3rd of June, 1760. End of Letter 16. Read by Elijah Fisher.
Letter 17 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit librivox.org. Read by Bonnie DeLeon. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler. Translated by Henry Hunter. Of light and the systems of Descartes and Newton. Having spoken of the rays of the sun, which are the focus of all the heat and light that we enjoy, you will undoubtedly ask, what are these rays? This is beyond question one of the most important inquiries in physics, as from it an infinite number of phenomena is derived. Everything that reflects light and that renders objects visible is closely connected with this inquiry. The ancient philosophers seem to have taken little interest in the solution of it. They contented themselves with saying that the sun is endowed with the quality of shining, of giving heat and light. But is it not worthwhile to inquire, wherein does this quality consist? Do certain portions, inconceivably small, of the sun himself or of his substance come down to us? Or is the transmission similar to the sound of a bell, which the ear receives? though no part of the substance of the bell be separated from it, as I observed in explaining the propagation and perception of sound. Descartes, the first of modern philosophers, maintained this last option, and having filled the whole universe with a subtle matter composed of small globules, which he calls the second element, he supposes that the sun is in a state of continual agitation, which he transmits to these globules and pretends that they again communicate their motion in an instant to every part of the universe. But since it has been discovered that the rays of the sun do not reach us instantaneously, and that they take 8 minutes to fly through that immense distance, the opinion of Descartes, which labored beside under other difficulties, has been given up. The great Newton afterwards embraced the former system, and maintained that the luminous rays are really separated from the body of the sun, and the particles of light thence emitted with that inconceivable velocity which brings them down to us in about 8 minutes. This opinion, which is that of most modern philosophers, particularly the English, is called the system of emanation, it being imagined that rays emanate from the sun and other luminous bodies as water emanates or springs from a fountain. This opinion appears at first sight very bold and irreconcilable to reason. For were the sun emitting continually and in all directions such floods of luminous matter, with a velocity so prodigious, he must speedily be exhausted, or at least some alteration must, after the lapse of so many ages, be perceptible. This, however, is contradicted by observation. It cannot be a matter of doubt that a fountain, which should emit streams of water in all directions, would be exhausted in proportion to the velocity of the emission, much more the sun, whose rays are emitted with a velocity so inconceivable. Let the particles of which rays of light are formed be supposed as subtle as you please, nothing will be gained. The system will ever remain equally untenable. It cannot be affirmed that this emanation is not made in all directions, for wherever you are placed, the whole sun is visible, which proves incontestably that rays from every point of the sun are emitted toward the spot which you occupy. The case is very different from that of a fountain, which should emit streams of water in all directions, for one point in the fountain could furnish only one stream directed to a particular spot, but every point of the sun's surface must emit an infinite number, diffusing themselves in all directions. This circumstance alone infinitely increases the expenditure of luminous matter, which the sun would have to make. Another difficulty, and which appears equally insuperable, is that the sun is not the only body which emits rays, but that all the stars have the same quality, and as everywhere the rays of the sun must be crossing the rays of the stars, their collision must be violent in the extreme. How must their direction be changed by such collision? This collision must take place with respect to all luminous bodies, visible at the same time. Each, however, appears distinctly, without suffering the slightest derangement from any other. A certain proof that many rays may pass through the same point without disturbing each other, which seems irreconcilable to the system of emanation. Let 2 fountains be set a-playing upon each other, and you will immediately perceive their different streams disturbed and confounded. It must of consequence be concluded that the motion of the rays of light is very essentially different from that of a jet d'eau, and in general from all substances forcibly emitted. Considering afterwards transparent bodies through which rays are freely transmitted in all directions, the supporters of the system are under the necessity of affirming that these bodies contain pores, disposed in straight lines, which issue from every point of the surface, and proceed in all directions. It being inconceivable how there could be any line through which a ray of the sun might be transmitted with such amazing velocity, and even without the slightest collision. Here then are bodies wonderfully porous, which have the appearance, nevertheless, of being extremely solid. Finally, in order to enjoy vision, the rays must enter into the eye and penetrate its substance with the same velocity. All these difficulties taken together will, I doubt not, sufficiently convince you that the system of emanation has, in no respect, a foundation in nature, and you will certainly be astonished that it could have been conceived by so great a man, and embraced by so many enlightened philosophers. but it is long since Cicero remarked that nothing so absurd could be imagined as to find no supporter among philosophers. For my part, I am too little a philosopher to adopt the opinion in question. 7th June, 1760. End of Letter 17. Letter 18 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit librivox.org. Read by Bonnie DeLeon. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler. Translated by Henry Hunter. Difficulties attending the system of emanation. However strange the doctrine of the celebrated Newton may appear, that rays proceed from the sun by a continual emanation, it has, however, been so generally received that it requires an effort of courage to call it in question. What has chiefly contributed to this is, no doubt, the high reputation of the great English philosopher, who first discovered the true laws of the motions of the heavenly bodies. And it is this very discovery which led him to the system of emanation. Descartes, in order to support his theory, was under the necessity of filling the whole space of the heavens with a subtle matter, through which all the celestial bodies move at perfect liberty. But it is well known that if a body moves in air, it must meet with a certain degree of resistance, from which Newton concluded that, however subtle the matter of the heavens may be supposed, the planets must encounter some resistance in their motions. But, said he, this motion is not subject to any resistance. The immense space of the heavens, therefore, contains no matter. A perfect vacuum, then, universally prevails. This is one of the leading doctrines of the Newtonian philosophy, that the immensity of the universe contains no matter, in the spaces not occupied by the heavenly bodies. This being laid down, there is between the sun and us, or at least from the sun down to the atmosphere of the earth, an absolute vacuum. In truth, the further we ascend, the more subtle we find the air to be, from whence it would apparently follow that at length the air would be entirely lost. If the space between the sun and the earth be an absolute vacuum, it is impossible that the rays should reach us in the way of communication, as the sound of a bell is transmitted by means of the air. For if the air intervening between the bell and our ear were to be annihilated, we should absolutely hear nothing, let the bell be struck ever so violently. Having established, then, a perfect vacuum between the heavenly bodies, there remains no other opinion to be adopted but that of emanation, which obliged Newton to maintain that the sun and all other luminous bodies emit rays, which are always particles infinitely small of their mass, darted from them with incredible force. It must be such to a very high degree, in order to impress on rays of light that inconceivable velocity with which they come from the sun to us, in the space of 8 minutes. But let us see whether this theory be consistent with Newton's leading doctrine, which requires an absolute vacuum in the heavens, that the planets may encounter no manner of resistance to their motions. You must conclude on a moment's reflection that the space in which the heavenly bodies revolve, instead of remaining a vacuum, must be filled with the rays not only of the sun, but likewise of all the other stars which are continually passing through it from every quarter and in all directions with incredible rapidity. The heavenly bodies which traverse these spaces, instead of encountering a vacuum, will meet with the matter of luminous rays in a terrible agitation, which must disturb these bodies in their motions much more than if it were in a state of rest. Thus Newton, apprehensive lest a subtle matter, such as Descartes imagined, should disturb the motion of the planets, had recourse to a very strange expedient, and quite contradictory to his own intention, as, on his hypothesis, the planets must be exposed to a derangement infinitely more considerable. I have already submitted to you several other insuperable objections to the system of emanation, and we have now seen that the principal and indeed the only reason which could induce Newton to adopt it is so self-contradictory as wholly to overturn it. All these considerations united leave us no room to hesitate about the rejection of this strange system of the emanation of light, however respectable the authority of the philosopher who invented it. Newton was, without doubt, one of the greatest geniuses that ever existed. His profound knowledge and his acute penetration into the most hidden mysteries of nature will be a just object of admiration to the present and to every future age. But the errors of this great man should serve to admonish us of the weakness of the human understanding, which, after having soared to the greatest possible heights, is in danger of plunging into manifest contradiction. Footnote: if we are liable to weaknesses and inconsistencies so humiliating in our researches into the phenomena of this visible world, which lies open to the examination of our senses, how wretched must we have been had God left us to ourselves with respect to things invisible, and which concern our eternal salvation. On this important article, a revelation was absolutely necessary to us, and we ought to avail ourselves of it with the most profound veneration. When it presents to us things which may appear inconceivable, we have but to reflect on the imperfection of human understanding, which is so apt to be misled, even as to sensible objects. Whenever I hear a pretended freethinker inveighing against the truths of religion, and even sneering at it with the most arrogant self-sufficiency, I say to myself, poor weak mortal, how inexpressibly more noble and sublime are the subjects which you treat so lightly than those respecting which the great Newton was so grossly mistaken. I could wish your Highness to keep this reflection ever in remembrance. Occasions for making it occur but too frequently. End footnote. 10th June, 1760. End of Letter 18. Letter 19 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit librivox.org. Read by Bonnie de Leon. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler. Translated by Henry Hunter. A different system, respecting the nature of rays and of light, proposed. You have seen that the system of the emanation of the rays of light labors under insuperable difficulties, and that the doctrine of a vacuum for the heavenly bodies to range in is equally untenable, as the rays of light would completely fill it. Two things, then, must be admitted. First, the space through which the heavenly bodies move is filled with a subtle matter. Secondly, rays are not an actual emanation from the sun and other luminous bodies, in virtue of which part of their substance is violently emitted from them, according to the doctrine of Newton. That subtle matter which fills the whole space in which the heavenly bodies revolve is called ether. Of its extreme subtlety no doubt can be entertained. In order to form an idea of it, we have only to attend to the nature of air, which, though extremely subtle, even on the surface of the earth, becomes more and more so as we ascend, and entirely ceases, if I may use the expression, when it comes to be lost in the ether. The ether, then, is likewise a fluid, as the air is, but incomparably finer and more subtle, as we are assured that the heavenly bodies revolve freely through it, without meeting any perceptible resistance. It is also, without doubt, possessed of elasticity, by means of which it has a tendency to expand itself in all directions and to penetrate into spaces where there would otherwise be a vacuum. So that if by some accident the ether were forced out of any space, the surrounding fluid would instantly rush in and fill it again. In virtue of this elasticity, the ether is to be found not only in the regions which are above our atmosphere, but it penetrates the atmosphere universally, insinuates itself by the pores of all bodies, and passes irresistibly through them. Were you, by the help of the air pump, to exhaust the air from a receiver, you must not imagine you have produced an absolute vacuum, for the ether, forcing itself through the pores of the receiver, completely fills it in an instant. Having filled a glass tube of the proper length with mercury, and immerged it, when inverted, in the cistern, in order to make a barometer, it might be supposed that the part of the tube which is higher than the mercury is a vacuum, because the air is completely excluded, as it cannot penetrate the pores of glass. But this vacuum, which is apparent only, is undoubtedly supplied by the ether, insinuating itself without the smallest difficulty. It is by this subtlety and elasticity of the ether that I shall, by and by, explain to you the remarkable phenomena of electricity. It is even highly probable that ether has an elasticity much superior to that of air, and that many of the phenomena of nature are produced by means of it. For my own part, I have no doubt that the compression of the air in gunpowder is the effect of the elastic power of ether. And as we know by experiment that the air in it is condensed almost 1,000 times more than common air, and that in this state its elasticity is likewise 1,000 greater, the elasticity of the ether must in this case be so too, and consequently 1,000 times greater than that of common air. We shall then have a just idea of ether in considering it as a fluid in many respects similar to air, with this difference, that ether is incomparably more subtle and more elastic. Having seen then that the air, by these very qualities, is in a proper state for receiving the agitations or shakings of sonorous bodies, and to diffuse them in all directions, as we find in the propagation of sound, it is very natural to suppose that ether may, in the same circumstances, likewise receive agitations in the same manner, and transmit them to the greatest distances. As the vibrations of the air produce sound, what will be the effect of those of ether? You will undoubtedly guess at once, light. It appears, in truth, abundantly certain that light is, with respect to ether, what sound is with respect to air, and that the rays of light are nothing else but the shakings or vibrations transmitted by the ether, as sound consists in the shakings or vibrations transmitted by the air. The sun, then, loses nothing of his substance in this case, any more than a bell in vibrating. And, in adopting this system, there is no reason to apprehend that the mass of this orb should ever suffer any diminution. What I have said of the sun must also be extended to all luminous bodies, such as fire, a wax taper, a candle, etc. It will undoubtedly be objected that these terrestrial luminaries evidently waste, and that unless they are continually fed and kept up, they will be speedily extinguished. That consequently the sun must in time be wasted away, and that the parallel of a bell is not accurate. But it is to be considered that these fires beside their light throw out smoke and a great deal of exhalation, which must be carefully distinguished from the rays of light. Now the smoke and exhalation evidently occasion a considerable diminution, which must not be imputed to the rays of light. For were it possible to separate them from the smoke and other exhalations, the luminous quality alone would occasion no expenditure. Mercury may, by means of art, be rendered luminous, as you have probably seen, and that without any diminution of its substance, which proves that light alone produces no waste of luminous bodies. Thus, though the sun illuminates the whole world by his rays, he loses nothing of his own substance, his light being only the effect of a certain agitation or violent concussion of his minute particles, communicated to the adjoining ether, and thence transmitted in all directions, by means of this fluid, to the remotest distances, as a bell, when struck, communicates its own agitation to the circumambient air. The more we consider this parallel between sonorous and luminous bodies, the more we shall find it conformable to nature, and justifiable by experience. Whereas the more we attempt to reconcile the phenomena of nature to the system of emanation, the more difficulties we encounter. 14th June, 1760. End of Letter 19. Letter 20 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit librivox.org. Read by Bonnie de Leon. Letters on Different Subjects in Natural Philosophy. Volume 1 by Leonhard Euler. Translated by Henry Hunter. Of the Propagation of Light. The propagation of light in the ether is produced in a manner similar to that of sound in the air. And just as the vibration occasioned in the particles of air constitutes sound, in like manner, the vibration of the particles of ether constitutes light, or luminous rays, so that light is nothing else but an agitation or concussion of the particles of ether, which is everywhere to be found on account of its extreme subtlety, in virtue of which it penetrates all bodies. These bodies, however, modify the rays of light in many different ways by transmitting or stopping the propagation of the concussions. Of this I shall treat at large in the sequel. I confine myself at present to the propagation of rays in the ether itself, which fills the immense space in which the heavenly bodies revolve. There the propagation takes place in perfect liberty. The first thing which here presents itself to the mind is the prodigious velocity of the rays of light, which is about 900,000 times more rapid than that of sound, though this last travels no less than 1,000 feet in a second. This amazing velocity would be sufficient of itself to overturn the system of emanation. But in that which I am attempting to establish, it is a natural consequence, from the principles laid down, as I hope to demonstrate. They are the same with those on which is founded the propagation of sound in air, and this depends at once on its density and elasticity. It is evident that if the density of air were diminished, sound would be accelerated, and if the elasticity of the air were increased, the same thing would happen. If the density of the air diminished and its elasticity increased at once, we should have a twofold reason for the increase of the velocity of sound. Let us conceive, then, the density of the air diminished and its elasticity increased till its density and elasticity became equal to those of ether, and we should then no longer be surprised that the velocity of sound had become many thousands of times greater than it actually is. For you will be pleased to remember that, according to the first ideas we formed of ether, this fluid must be inconceivably rarer and more elastic than air. Now both of these qualities equally contribute to accelerate the velocity of vibrations. From this explanation, the prodigious velocity of light is so far from presenting anything irreconcilable to reason that it rather perfectly harmonizes with the principles laid down, and the parallel between light and sound is, in this respect, so firmly established that we may confidently maintain that if air should become as subtle and as elastic as ether, the velocity of sound would become as rapid as that of light. The subtlety of ether, then, and its great elasticity, are the reason which we assign for the prodigious velocity of the motion of light. And so long as the ether preserves this same degree of subtlety and elasticity, this velocity must continue the same. Now it cannot be doubted that the ether has, through the whole universe, the same subtlety and the same elasticity. For were the ether less elastic in one place than in another, it would force itself into it, till the equilibrium was perfectly restored. The light of the stars, therefore, moves with as great velocity as that of the sun. And as the stars are at a much greater distance from us than the sun, a much greater quantity of time is requisite to transmit their rays to us. However great the distance of the sun may appear, whose rays nevertheless reach the surface of our globe in 8 minutes, the fixed star nearest to us is, at least, 400,000 times more distant than the sun. A ray of light issuing from that star will employ, then, 400,000 times 8 minutes in traveling to us. That is 53,333 hours, or 2,222 days, or 6 years nearly. It is then upwards of 6 years since the rays of light issued from that fixed star, the least remote and probably the most brilliant, in order to render it visible to us, and these rays have employed a period so considerable to fly through the space which separates us from that star. Were God just now to create a new fixed star at the same distance, it could not become visible to us till more than 6 years had elapsed, as its rays require that length of time to travel this distance. Had one been created at the beginning of the world, 1,000 times more distant than that which I have mentioned, it could not yet be visible to us, however brilliant, as 6,000 years are not yet elapsed since the creation. The first preacher of the court of Brunswick, Mr. Jerusalem, has happily introduced this thought in one of his sermons. The passage runs thus: "Raise your thoughts from the earth which you inhabit to all the bodies of the vast universe, which are so far above you. Launch into the immensity of space, which intervenes between the most remote which your eyes are able to discover, and those whose light, from the moment of creation till now, has not as yet, perhaps, come down to us. The immensity of the kingdom of God justifies this representation." Sermon on the Heavens and Eternal Beatitude. I flatter myself that these reflections will excite a desire to further instruction respecting the system of light, from which is derived the theory of colors and of vision. 17th June, 1760. End of Letter 20.
Letter number 21 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler. Translated by Henry Hunter. Digression on the distances of the heavenly bodies and on the nature of the sun and his rays. The observations which I have been making respecting the time which the light of the stars employs in making its progress down to us convey a striking idea of the extent and greatness of the universe. The velocity of sound, which flies through the space of 1,000 feet in a second, furnishes us with nearly the first standard of measurement. It is about 200 times more rapid than the pace of a man who is a good walker. Now the velocity of the rays of light is 900,000 times still more rapid than that of sound. These rays accordingly perform every second a course of 900 millions of feet, or 37,500 German miles. Footnote: more than 170,000 miles English. End footnote. What astonishing velocity! Yet the nearest fixed star is so remote that its rays, notwithstanding this prodigious velocity, would take more than 6 years in descending to us. And were it possible for a great noise, such as that of firing of a cannon issuing from that star, to be conveyed to our ears, it would require a period of 5,400,000 years to reach us. And this is applicable only to those stars which are the most brilliant and are probably nearest to us. Those which appear the smallest are very probably 10 times still farther remote, and more. A whole century, then, at least, must elapse before the rays of these stars could possibly reach us. How prodigious must that distance be which cannot be passed through in less than 100 years by a velocity which flies at the rate of 37,500 German miles every second. Were then one of these stars to be just now annihilated, or eclipsed only, we should still continue to see it for 100 years to come, as the last rays which it emitted could not reach us in less time. The generality of mankind is very far from having anything like just ideas respecting the vast extent of the universe. Many consider it as a work of little importance, which chance alone might have produced. But what must be the astonishment of one who reflects on observing that all these immense bodies are arranged with the most consummate wisdom, and that the more knowledge we acquire on the subject, though it must ever be very imperfect, the more we must be disposed to admire their order and magnificence. I return to the great luminous bodies, and particularly the sun, which is the principal source of the light and heat which we enjoy on the earth. It will be asked, in the first place, wherein consists the light which the sun is incessantly diffusing through the whole universe, without ever suffering the smallest diminution? The answer is obvious according to the system which I have been endeavoring to establish. But that of emanation furnishes no satisfactory solution, the whole universe being filled with that extremely subtle and elastic fluid which is called ether. we must suppose in all the parts of the sun an incessant agitation, by which every particle is in a constant motion of vibration, and this, by communicating itself to the circumambient ether, excites in that fluid a similar agitation, and is thence transmitted to regions the most remote, with the rapidity which I have been describing. And to keep up the parallel between sound and light, the sun would be in a state similar to that of a bell which should be ringing continually. The particles of the sun must consequently be kept in this incessant agitation to produce in the ether the undulations which we call rays of light. But it is still no easy matter to explain by what power this agitation in the particles of the sun is constantly kept up, as we observe that a match does not long continue burning, but presently goes out unless it be supplied with combustible matter. But it must be remarked that as the sun is a mass many thousand times greater than our whole globe, if it is once thoroughly inflamed, it may continue in that state for several ages without suffering any sensible diminution. Besides, the case is not the same with the sun and our fires and candles, a considerable part of whose substance is dissipated in smoke and exhalations, from which a real waste results. Whereas, though perhaps some particles may be forced from the sun in form of smoke, they cannot remove to a great distance, but speedily fall back into its mass, so that there cannot be any real expenditure to occasion a diminution of his substance. Note: the author is evidently embarrassed in his explanation of the continual inflammation of the sun, and though he has said above that the system of emanation was untenable on account of the frequent and unavoidable collision of rays proceeding from different luminous bodies, which must disturb and even obstruct the vision of several of these bodies at once, as he has not explained how two sounds may be heard at the same time, a similar objection might be made to his system, which is analogous to the phenomena of sound. End of note. The only thing of which we are still ignorant respecting this subject is the power which incessantly maintains all the particles of the sun in this agitation. But as it contains nothing inconsistent with good sense, and as we are under the necessity of acknowledging our ignorance of many other things much less remote than the sun, we ought to be satisfied if our ideas are not involved in contradiction. 21st of June, 1760. End of letter number 21. Read by Sandra in Nova Scotia, 2023.
Letter 22 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler. Translated by Henry Hunter. Elucidations on the nature of luminous bodies and their difference from opaque bodies illumined. The sun being a luminous body, whose rays are universally diffused in all directions, you can no longer be at a loss to account for this wonderful phenomenon, which consists in the shaking or vibration with which all the particles of the sun are agitated. The parallel of a bell lends considerable assistance toward the explanation of this fact, but it is obvious that the vibrations produced by light must be much more vehement and rapid than those produced by sound, ether being incomparably more subtle than air. A feeble agitation not being capable of shaking the air so as to produce sound in it, that of a bell, and of all other sonorous bodies, are too feeble relatively to ether to produce in it the vibration which constitutes light. You will recollect that in order to excite a perceptible sound, more than 30 and less than 7,552 vibrations must be produced in a second, the air being too subtle to admit of the sensible effect from a sound consisting of less than 30 vibrations in a second, but not sufficiently so to receive one of more than 7,552 vibrations in the second. A note higher than this could not be at all heard. It is the same with respect to ether. 7,552 vibrations, produced in a second, could not possibly act upon it, because of its greater subtlety. It requires vibrations much more frequent. An agitation so rapid could not take place but in the minutest particles of bodies which elude our senses. The light of the sun, then, is produced by a very violent agitation, which affects all his infinitely minute particles, each of which must shake many thousands of times every second. It is a similar agitation which likewise produces the light of the fixed stars and of all fires, such as candles, tapers, torches, etc., which give us light, and supply the place of the sun during the night. On attentively observing the flame of a wax light, you will easily perceive that, in the minutest particles, there is a constant and surprising agitation. And I do not apprehend that my system is liable, on this side, to any contradiction, while that of Newton requires a most enormous agitation, capable of launching the minutest particles with the velocity of 37,500 German miles in a second. Footnote: upwards of 170,000 English miles. End footnote. This, then, is the explanation of the nature of bodies luminous of themselves. For there are luminous bodies which are not so immediately, such as the moon and the planets, which are similar to our globe. We see the moon only when, and in as far as, she is illuminated by the sun. And this is the case of all terrestrial bodies, fires excepted, which have a light of their own. But other bodies, which are denominated opaque, become visible to us only when they are illuminated by some luminous body. In a very dark night, or in an apartment, so closely shut on every side, that no light can find admission, to no purpose will you turn your eyes toward the objects which surround you in the dark. You perceive nothing. But the moment a taper is introduced, you immediately see, not the taper only, but the other bodies which were before invisible. We have here, then, a very essential difference between luminous and opaque bodies. I have already employed the term opaque to denote bodies which are not transparent, but it comes to almost the same thing, and we must accommodate ourselves to the common modes of expression, though they are not perfectly accurate. Luminous bodies are visible by their own light, and never affect our organs of sight more than when the darkness is otherwise most profound. Those which I here denominate opaque are rendered visible to us only by means of a light that is foreign to them. We perceive them not while they remain in darkness, but as soon as they are exposed to a luminous body, whose rays strike upon them, they become visible, and they disappear the moment that foreign light is withdrawn. It is not even necessary that the rays of a luminous body should fall upon them immediately. Another opaque body, when well illuminated, produces nearly the same effect, but in a feebler manner. The moon is an excellent instance. We know that the moon is an opaque body, but when she is illuminated by the sun, and we see her during the night, she diffuses a feeble light over all opaque bodies, and renders visible to us those which we could not have perceived without her assistance. Placed in the daytime in an apartment whose aspect is toward the north, and into which, of course, the rays of the sun cannot enter, it is, however, perfectly clear, and I am able to distinguish every object. What can be the cause of this clearness, but what the whole heaven is illuminated by the sun? What we call the azure sky, and besides, the walls opposite to my apartment, and the other surrounding objects, are likewise illuminated, either immediately by the sun, or mediately by other opaque bodies, exposed to the action of that focus of light. And the light of all these opaque but illuminated bodies, as far as it has admission into my apartment, renders it luminous, and that in proportion as the windows are high, wide, and well placed. The glass is little or no interruption, being, as I have already remarked, a transparent body, which freely transmits the rays of light. When I completely exclude the light from the apartment, by closing the window shutters, I am reduced to a state of darkness, and discern no object, unless I call for a candle. Here, then, is an essential difference between luminous and opaque bodies, and likewise a very striking resemblance, namely, that opaque bodies, when illuminated, illuminate other opaque bodies, and produce, in this respect, nearly the same effect as bodies luminous of themselves. The explanation of this phenomenon has hitherto greatly perplexed philosophers, but I flatter myself that my solution of it has been clear and satisfactory. 24th June, 1760. End of Letter 22. Read by Verla Vieira in Las Cruces, New Mexico, USA. May 17th, 2024.
Letter 23 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by JJ. Letters on Different Subjects in Natural Philosophy, Volume 1 by Leonhard, Euler. Translated by Henry Hunter. How opaque bodies become visible. Newton's system of the reflection of rays proposed. Before I attempt an explanation of the phenomenon of opaque bodies becoming visible when they are illuminated, it must be remarked, in general, that we see nothing but by means of the rays which enter into our eyes. When we look at any object whatever, rays issuing from every point of that object and entering into the eye, paint upon it, if I may use the expression, the image of the object. This is not mere conjecture, but may be demonstrated by experiment. Take, for example, the eye of an ox, or of any animal recently killed, and, after having uncovered the bottom, you find all the objects which were before it painted there. As often then as we see an object, the image of it is painted on the bottom of our eyes, and this is produced by the rays which proceed from the object to us. I shall afterwards take occasion to go into a more minute detail on the subject of vision, and explain in what manner the images of objects are formed on the bottom of the eye. Let this general remark suffice for the present. As we see opaque bodies only when they are illuminated, this is a proof that there must proceed from every point of these bodies rays of light, which subsist only during the illumination. The moment they are placed in the dark, these rays disappear. They are not proper then to opaque bodies. Their origin must be sought in the manner in which other bodies illuminate them. And this is the great question: how illumination alone is capable of producing rays on opaque bodies, or of putting them in nearly the same state as luminous bodies are, which, by an agitation in their minutest particles, produce rays of light. The great Newton and other philosophers who have examined the subject assign reflection as the cause of this phenomenon. It is, therefore, of the highest importance that you should form a just idea of what is called reflection. This name is given to the repulsion of one body struck against another, as may be seen in the game of billiards. When the ball is struck against the cushion or ledge of the billiard table, it recoils again, and this retrograde motion is termed reflection. It is necessary here to attend to a distinction between two cases. Let us suppose AB, Plate 1, Figure 7, to be the ledge of a billiard table. The first case is this: when you play the bally D perpendicularly against the ledge in the direction of DC perpendicular to AB, and, consequently, the adjacent angles ACD and BCD are right angles. In this case, the ball will be driven back or reflected in the same line DC. The other case is when the ball is played obliquely against the ledge, suppose in the line EC, forming with AB an acute angle ACE. This is called the angle of incidence. The ball will, in this case, be repelled from the ledge in the direction of the line CF, so that this line shall make on the other side with the ledge BC an angle BCF exactly equal to the angle of incidence, ACE. This angle, BCF, formed by the line in which the ball recoils, is called the angle of reflection, and this law always takes place when a body in motion meets an obstacle. A cannonball shot against a wall sufficiently strong to resist it is reflected conformably to this law. It extends, in like manner, to sounds, which are frequently reflected from certain bodies. And you know what this reflection of sound is called echo. It cannot be doubted that the same thing frequently takes place with respect to the rays of light. The objects which we see in mirrors are represented to us by the reflection of rays, and every well-polished surface reflects the rays of light which fall upon it. It is undoubtedly certain, therefore, that there are cases without number in which the rays that fall on certain bodies are reflected, and philosophers have thence taken occasion to maintain that opaque bodies are rendered visible by means of reflected rays. I see just now houses opposite to my windows which are illuminated by the sun. According, then, to the opinion of those philosophers, the rays of the sun falling on the surface of these houses are reflected from them. They enter into my apartment and render these houses visible to me. In the same manner, if we believe those philosophers, the moon and the planets become visible, and these are, unquestionably, opaque bodies. The rays of the sun, which fall on these bodies and illuminate the parts which are exposed to them, are reflected, and are thence transmitted to us, just as if the bodies were luminous of themselves. According to this opinion, we see the moon and the planets only by the rays of the sun which they reflect, and you must frequently have heard it affirmed, that the light of the moon is a reflection of the light of the sun. In the same manner, say they, the rays of the sun are reflected by the first opaque bodies which are exposed to them on other bodies of the same nature, and undergo a series of similar reflections till they are entirely weakened. But, however plausible this opinion may, at first sight, appear, it involves so many absurdities, when closely examined, that it is absolutely untenable, which I hoped to demonstrate as a preparation for the true solution of this phenomenon. 28th June, 1760. End of Letter 23.
Letter 24 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Emanuela. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler. Translated by Henry Hunter. Examination and Refutation of Newton's System. I affirm, then, that when we see an opaque body illuminated by the sun, it is impossible to maintain that it reflects luminous rays, and that, by means of such rays, it is rendered visible to us. The example of a mirror, which undoubtedly reflects the rays and is employed to support this opinion, rather confutes it. The mirror, beyond contradiction, sends back the rays which fall upon it, but when these reflected rays enter into our eyes, what do they represent? you will readily answer that it is not the mirror, but the objects from which they originally proceeded, and the reflection does nothing else but enable us to see this object in another place. Besides, we see those objects not on the surface of the mirror, but rather within it, and it may be said with truth that the mirror itself remains invisible to us. But on looking at an opaque body illuminated by the sun, we do not see in it the image of that glorious orb. We see only the surface of the bodies, with all the variations to be found on them. We perceive then a very essential difference between the rays which are reflected from a mirror and those by means of which opaque bodies are rendered visible. But there is besides another difference equally palpable in the mirror. For on changing the place of the objects, or our own situation, the appearance will always change, and the rays reflected from the mirror will continually represent to our eyes other images corresponding to the nature and position of the objects and to the place where we are stationed. But, as I have already said, these reflected rays never represent to us the mirror itself. Now, let a body be illuminated by the sun, or other bodies, whether luminous or opaque, already illuminated. In whatever manner this body may change its place, or we change ours relatively to it, its appearance is always the same. We see always the same object and remark in it no change relative to the different circumstances above mentioned. This furnished a new proof that we do not see opaque bodies by means of the rays reflected from their surface. Footnote. This can hardly be deemed a fair statement. It is true that opaque bodies are seen only by reflected light, but it by no means follows that all the incident light is again reflected. Some bodies are, by their constitution, disposed to reflect certain kinds of rays the most freely, and as the rest are absorbed, the peculiar color predominates. This color will, therefore, not be the same, whatever be the quality of the incident light, but will receive an analogous shade. For the same reason, no substance reflects only one species of rays. The elective attractions and repulsions between the particles of light and the body are most remarkable at very minute distances, and hence the color is prominent when the surface is raw, for the light, suffering then a partial repulsion only, gains a nearer approach. I cannot imagine how Mr. Euler would explain these facts on his own principles. It is in a polished surface only that the surrounding bodies can be seen by reflection, for distinct vision requires the rays, proceeding from different points, to be transmitted with regularity. No substance is, indeed, perfectly smooth, but the different repulsions exerted by the superficial particles may balance each other and produce an uniform effect. At the distance where the reflection takes place, Mr. Euler's principles would lead to the conclusion that polish is not at all necessary to a mirror. Echo is formed from surfaces which are very uneven, since the air is heaped on the obstacle, and the principal reflux of the undulation commences at a sensible distance from it. The same obtains in water, though in a less degree, and is, in general, more remarkable in proportion to the rarefaction of the fluid. How wonderful, then, in that respect, must ether be, which is supposed to be the most subtle of all fluid! we might expect the walls of a house to reflect the most enchanting picture of the landscape in front. End of footnote. An objection will perhaps be started, drawn from the dove's neck, and certain kinds of stuff, which present different objects according as our point of view changes. But this in no respect weakens my conclusion with regard to ordinary opaque bodies which are not subject to this change. The objection only proves that these singular objects are endowed with certain qualities, as, for example, that their miniature particles are finely polished and that a real reflection takes place beside the usual and ordinary manner in which bodies are rendered visible to us. Now, it is easy to comprehend that this reflection must be clearly distinguished from the manner in which ordinary opaque bodies are illuminated. Finally, the rays reflected from a mirror always represent to us, likewise, the colors of the bodies from which they originally proceed, and the mirror, which reflects, makes no change in this respect. One opaque body, illuminated by any other body, in whatever manner, always presents the same colors, and every body may be said to have its proper color. This circumstance absolutely overturns the opinion of all those who maintain that we see opaque bodies by means of the rays which their surface reflects. Putting together all the reasons which I have now submitted to your consideration, there can be no hesitation in pronouncing that this opinion is totally untenable in philosophy, or rather in physics. I cannot, however, flatter myself with the hope that philosophers wedded to opinions once adopted should yield to these reasons, but the naturalist, who is more nearly related to the mathematician, will have less difficulty in resigning an opinion overthrown by reasons so convincing. You will again recollect that Cicero has said on this subject that nothing so absurd can be conceived as not to be supported by some philosopher. In fact, however strange the system which I have been refuting may appear to you, it has hitherto been propagated and defended with much warmth. It is impossible to say to what a degree the difficulties and contradiction which I have been endeavoring to expose were unknown to or overlooked by the partisans of this system. The great Newton himself strongly felt their force, but as he rested in a very untenable idea respecting the propagation of light, it is not to be wondered at that he should overlook these great difficulties, and in general, depth of understanding does not always prevent a man from falling into absurdity in supporting an opinion once embraced. But if this system, that opaque bodies are rendered visible by reflected rays, befalls, say, its partisans, what then is the true one? They even think it impossible to imagine another explanation of this phenomenon. It is, besides, rather hard and humiliating for a philosopher to acknowledge ignorance of any subject whatever. He would rather maintain the grossest absurdities, especially if he possesses the secret of involving them in mysterious terms, which no one is capable of comprehending, for in this case the vulgar are the more disposed to admire the learned, taking it for granted that what is obscurity to others is perfectly clear to them. We ought always to exercise a little mistrust when very sublime knowledge is pretended to, knowledge too sublime to be rendered intelligible. I hope I shall be able to explain the phenomenon in question in such a way as to remove every difficulty. 1st of July 1760. End of letter 24. Letter 25 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Emanuela. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. A different explanation of the manner in which opaque bodies, illuminated, become visible. All the phenomena of opaque bodies, which I have unfolded in the preceding letter, incontestably demonstrate that when we see an opaque body illuminated, it is not by rays reflected from its surface that it becomes visible, but because its miniature particles are in an agitation similar to that of the miniature particles of luminous bodies. With this difference, however, that the agitation in opaque bodies is far from being so strong as in bodies luminous of themselves. For an opaque body, however much illuminated, never makes on the eye an impression so lively as luminous bodies do. As we see the opaque bodies themselves, but by no means the images of the luminous bodies which enlighten them, as must be the case if we saw them by the reflection of their surface, it must follow that the rays emitted by opaque bodies are proper to them, just as the rays of a luminous body are peculiar to itself. As long as an opaque body is illuminated, the miniature particles of its surface are in a state of agitation proper to produce in the ether a motion of vibration such as is necessary for forming rays, and for painting in our eyes the image of the body from which they proceed. For this effect, rays must be diffused from every point of the surface in all directions, as experience evidently confirms. For, from whatever side we look at an opaque body, we see it equally in all its points, from which it follows that every point emits rays in all directions. This circumstance essentially distinguished these rays from such as are reflected, whose direction is always determined by that of the rays of incidence, so that if the incidence rays proceed from one single quarter, say the sun, the reflected rays can follow only one single direction. It must be admitted, then, that when an opaque body is illuminated, all the particles on its surface are put in a certain agitation, which produces rays, as is the case with bodies luminous of themselves. This agitation, likewise, is stronger in proportion as the light of the illuminating body is more intense. Thus, the same body exposed to the sun is agitated much more violently than if, in a room, it were illuminated only by daylight, or in the night time by a taper, or by the moon. In the first case, its image is painted with much greater vivacity on the bottom of the eye than in the others, especially the last, the light of the moon being scarcely sufficient to enable us to distinguish or to read writing of a large size. And when the opaque body is conveyed into a closed room or into the dark, nothing is then to be seen, a certain proof that the agitation in its parts has entirely ceased, and that they are now in a state of rest. In this, therefore, consists the nature of opaque bodies. Their particles are of themselves at rest, or at least destitute of the agitation necessary to produce light. But these same particles are so disposed that when illuminated or struck with rays of light, they are immediately put into a certain agitation, or motion of vibration, proper to produce rays. And the more intense the light is which illuminates these bodies, the more violent also is this agitation. As long as an opaque body is illuminated, it is in the same state as luminous bodies. Its particles are agitated in the same manner and are capable of exciting of themselves rays in the ether, with the difference that the agitation kept up in luminous bodies by an intrinsic force subsists always of itself, whereas in opaque bodies this agitation is only momentary and produced by the motion of the light which illuminates them. This explanation is consistent with every phenomenon and labors under none of the difficulties which determined us to abandon the other, namely that founded on reflection. Whoever will take the trouble candidly to weigh all these reasons must admit their force. But a very great difficulty still remains to be solved. How comes it that illumination simply can put the particles of an opaque body into an agitation capable of producing rays, and that this agitation should always continue nearly the same, whatever difference there may be in the illumination? I acknowledge that were it impossible to answer this question, it would be a greater defect in my theory, though it would not amount to a complete refutation, for it contains nothing contradictory. Supposing I were ignorant how illumination produces an agitation in the particles of opaque bodies, this would only prove that the theory is incomplete. Until it is demonstrated to be absolutely impossible that illumination should produce this effect, my system must subsist. But I shall endeavor to supply this defect by showing you how illumination agitates the minutest particles of bodies. 5th of July, 1760. End of letter 25. Letter 26 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Emanuela. Letters on Different Subjects in Natural Philosophy. Volume 1 by Leonhard Euler. Translated by Henry Hunter. Continuation of the same subject. I have undertaken to show how the illumination of an opaque body must produce, in its minutest particles, an agitation proper to excite the rays of light, which render that same opaque body visible. The parallel between sound and light, which differ only in respect of less and more, light being the same thing relatively to ether, that sound is relatively to air. This parallel, I say, will enable me to fulfill my engagement. Luminous bodies must be compared to musical instruments actually in a state of vibration. It is a matter of indifference whether this be the effect of an intrinsic or of a foreign power. It is sufficient, for my purpose, that sound is emitted. Opaque bodies, as long as they are not illuminated, must be compared to musical instruments not in use. or, if you will, two strings which emit no sound till they are touched. The question then, being transferred from light to sound, is resolved into this: whether it be possible for the string of an instrument in a state of rest, when brought within the sphere of activity of the sound of instruments in a state of vibration, to receive, in certain circumstances, some agitation, and emit sound without being touched. Now, this is confirmed by daily experience. If you take the trouble, during a concert, to attend to a particular string in proper tune, you will observe that string sometimes to tremble without having been touched, and it will emit the same sound as if it had been immediately put into vibration. This experiment will succeed still better if the instruments strike the same note with the string. Consider attentively the strings of a harpsichord, not played upon, while the violin strikes the note A, for example, and you will observe, on the harpsichord, the string of the same note begins sensibly to tremble, and even to emit sound, without having been touched. Some other chords will likewise be agitated, particularly those which are distant an octave, a fifth, and even a third, provided the instrument be perfectly in tune. This phenomenon is well known to musicians, and Mr. Rameau, one of the most celebrated French composers, established his principles of harmony upon it. He maintains that octaves, fifths, and thirds must be considered as consonances, because one chord is agitated by the sound only of another chord, which is in unison or an octave, a fifth or a third, from the first. But it must be admitted that the principles of harmony are so well established by the simplicity of the relations which sounds have to each other that they have no need of a new confirmation. In truth, the phenomenon observed by Mr. Rameau is a very natural consequence from the principles of harmony. To render these more sensible, let us attend to two chords wound up to unison. On striking the one, the other will begin on itself to tremble and will emit its sound. The reason is abundantly clear, for as a chord communicates to the air by its trembling a motion of vibration similar to its own, the air, agitated by this motion of vibration, must reciprocally make the chord tremble, provided that, by its degree of tension, it be susceptible of this motion. The air, being put into vibration, strikes the chord ever so little at every reverberation, and the repetition of strokes soon impresses on the chord a sensible motion, because the vibrations to which it is disposed by its tension accord with those of the air. If the number of vibrations in the air is the half, or the third, or any other whose relation is sufficiently simple, the chord does not receive a new impulse at every vibration as in the preceding case, but only at the second, or the third, or the fourth, which will continue to increase its tremulous motion, but less than in the first case. But the vibrations of the air have not any simple relation with that which corresponds to the chord. The agitation of that fluid will produce no effect whatever upon it. The vibrations of the chord, if there be any, not corresponding to those of the fluid, the following impulsions of the air destroy, for the most part, the effect which the first might have produced. And this is completely confirmed by experience. Thus, when a chord is shaken by a sound, that sound must, in order to its being perceptible, be precisely the same with that of the chord. Other sounds, which have a consonance with that of the chord, will produce, it is true, a similar but less sensible effect, and dissonances will produce none at all. This phenomenon takes place not only in musical strings, but in all sonorous bodies whatever. One bell will resound by the noise only of another bell, which is in unison with it, or at the distance of an octave, a fifth, or a third. The instance of a person who could break glasses by his voice further confirms what I have advanced. When a glass was presented to him, by striking it, he found out the note. He then began to squall in unison, and the glass immediately caught the vibration. Proceeding to give to his voice all the force he was able, always preserving the unison, the vibration of the glass became at length so violent that it broke. It is confirmed then by experience that a chord and every other sonorous body is put into vibration by its kindred sound. The same phenomenon must take place with regard to opaque bodies, of which the minuter particles may be put into a state of agitation by illumination only, which is the question I propose to solve. The following letter will contain a more ample discussion of it. 8th of July, 1760. End of letter 26. Letter 27 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Emanuela. Letters on Different Subjects in Natural Philosophy. Volume 1 by Leonhard Euler. Translated by Henry Hunter. Conclusion: Clearness and color of opaque bodies illuminated. After what has just been submitted to your consideration, you will no longer be surprised that an opaque body is capable of receiving, from illumination alone, an agitation in its particles, similar to that of the particles of luminous bodies, and which gives them the property of producing rays that render them visible. Thus, the great objection to my explanation of the visibility of opaque bodies is happily removed, while the other theory, founded on the reflection of rays, has to encounter difficulties, which grow in proportion as you attempt to make a more direct application of them to known phenomena. It is, then, an established truth that the particles of the surfaces of all bodies which we see undergo an agitation similar to that of a chord in vibration, but their vibrations are much more rapid, whether it be that this agitation is the effect of an intrinsic force, as in bodies luminous of themselves, or whether it be produced by the rays of light which fall upon the bodies, that is to say, by illumination, as is the case in opaque bodies. It is false, then, that the moon, being an opaque body, reflects the rays of the sun, and that, by means of this reflected light, she is rendered visible to us, as is commonly understood. But the rays of the sun, falling on the surface of the moon, excite in its particles a concussion, from which result the rays of the moon, and these, entering into our eyes, paint its image there. It is the same with the other planets, and with all opaque bodies. This agitation of opaque bodies, when illuminated, lasts only during the illumination which is the cause of it, and as soon as an opaque body ceases to be illuminated, it ceases to be visible. But is it not possible that this agitation, once impressed on the particles of an opaque body, may be for some time kept up, as we see that a string, once struck, frequently continues to vibrate, though no new impression be made upon it? I do not pretend to deny the fact. I even believe that we have examples of it in those substances which Mr. Marggraf presented to you, and which, once illuminated, preserve their light for some time, though conveyed into dark room. This, however, is an extraordinary case, the vibration of the miniature particles disappearing. In all other bodies, with the illumination which occasioned it. But this explanation, which thus far is perfectly self-consistent, leads me forward to researches of still greater importance. It is undoubtedly certain that we find an infinite difference between the particles of opaque bodies according to the variety of the bodies themselves. Some will be more susceptible of vibrations, and others less, and others, finally, not at all so. This difference in bodies occurs but too evidently. One, whose particles easily receive the impression of the rays which strike it, appears to us brilliant. Another, on the contrary, in which the rays scarcely produce any agitation, cannot appear luminous. Among several bodies equally illuminated, you will always remark a great difference, some being more brilliant than others. But there is, besides, another and a very remarkable difference between the particles of opaque bodies, respecting the number of vibrations which each of them, being agitated, will make in a certain time. I have already observed that this number must always be very great, and that the subtlety of ether is such as to require many thousands in a second. But the difference here may be endless. If some particles, for example, should make 10,000 vibrations in a second, and others 11,000, 12,000, 13,000, according to the smallness, the tension, and the elasticity of each, as in the case of musical chords, in which the number of vibrations given in a second may be varied without end, and thence it is I have deduced the difference of high and low notes, as this difference is essential in sounds, and as the ear is affected by it in a manner so particular as to render it the foundation of the whole theory of music, it cannot be called in question that a similar difference in the frequency of the vibrations of rays of light must produce a variation as particular in vision. If, for example, a particle makes 10,000 vibrations in a second and produces rays of the same species, the rays which enter into the eye will strike the nerves of that organ 10,000 times in a second, and this effect, as well as the sensation, must be totally different from those produced by a different particle, which should make more or less vibrations in a second. There will be in vision a difference similar to that which the ear perceives on hearing sharp or flat notes. You will, no doubt, be desirous to know into what this difference in vision is to be resolved, and what different sensations correspond to the number, greater or less, of the vibration produced in every body during a second. I have the honor of informing you that diversity of colors is occasioned by this difference, and that difference of color is to the organ of vision what sharp or flat sounds are to the ear. We have resolved, therefore, without going after it, the important enquiry respecting the nature of colors, which has long employed the attention of the greatest philosophers. Some of them have called it a modification of light absolutely unknown to us. Descartes maintains that colors are only a certain mixture of light and shade. Newton accounts for difference of color by tracing it up to the rays of the sun, which, according to him, are a real emanation, whose matter may be more or less subtle, and thence settles the rays of all the colors, as red, yellow, green, blue, violet, etc. But as this system falls to pieces of itself, all that has been said respecting colors conveys no information, and you are now clearly sensible that the nature of each color consists in the number of vibrations produced in a certain time by the particles which present them to the eye. 12th of July, 1760. End of letter 27.
Letter number 28 of Letters on Different Subjects in Natural Philosophy. This LibriVox recording is in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 28. Nature of Colors in particular. The ignorance which prevailed respecting the true nature of colors has occasioned frequent and violent disputes among philosophers, each of whom made an attempt to shine by maintaining a peculiar opinion on the subject. The system which made colors to reside in the bodies themselves appeared to them too vulgar and too little worthy of a philosopher who ought always to soar above the multitude. Because the clown imagines that one body is red, another blue, and another green, the philosopher could not distinguish himself better than by maintaining the contrary, and he accordingly affirms that there is nothing real in colors and that there is nothing in bodies relative to them. The Newtonians make colors to consist in rays only, which they distinguish into red, yellow, green, blue, and violet, and they tell us that a body appears of such and such a color when it reflects rays of that species. Others, to whom this opinion seemed absurd, pretend that colors exist only in ourselves. This is an admirable way to conceal ignorance. The vulgar might otherwise believe that the scholar was not better acquainted with the nature of colors than themselves. But you will readily perceive that these affected refinements are mere cavil. Every simple color, in order to distinguish from compound colors, depends on a certain number of vibrations which are performed in a certain time, so that this number of vibrations, made in a second, determines the red color, another the yellow, another the green, another the blue, and another the violet, which are the simple colors represented to us in the rainbow. If, then, the particles of the surface of certain bodies are disposed in such a manner that being agitated they make in a second as many vibrations as are necessary to produce, for example, the red color, I call such a body red, just as the clown does, and I see nothing like a reason for deviating from the common mode of expression. And rays which make such a number of vibrations in a second may with equal propriety be denominated red rays, and finally, when the optic nerve is affected by these same rays, and receives from them a number of impulsions, sensibly equal in a second, we receive the sensation of the red color. Here everything is clear, and I see no necessity for introducing dark and mysterious phrases which really mean nothing. The parallel between sound and light is so perfect that it hits even in the minutest circumstances. When I produce the phenomenon of a musical chord which may be excited into vibration by the resonance only of certain sounds, you will please to recollect that the one which gives the unison of the chord in question is the most proper to shake it, and that other sounds affect it only in proportion as they are in consonance with it. It is exactly the same as to light and colors, for the different colors correspond to the different musical sounds. In order to display this phenomenon, which completely confirms my assertion, let a dark room be provided. Make a small aperture in one of the shutters, before which at some distance place a body of a certain color, say a piece of red cloth, so that when it is well illumined its rays may enter by the aperture into the darkened room. The rays thus transmitted into the room will be red, all other light being excluded, and if you hold on the inside of the room, opposite to the aperture, a piece of cloth of the same color, it will be perfectly illumined, and its red color appear very brilliant. But if you substitute in its place a piece of green cloth, it will remain obscure, and you will hardly see anything of its color. If you place on the outside, before the aperture, a piece of green cloth, that within the chamber will be perfectly illumined by the rays of the first, and its green color appear very lively. The same holds good as to all other colors, and I do not imagine that a more convincing demonstration of the truth of my system can be demanded. We learn from it that in order to illuminate a body of a certain color, it is necessary that the rays which fall upon it should have the same color, those of a different color not being capable of agitating the particles of that body. This is further confirmed by a well-known experiment. When the spirit of wine is set on fire in a room, you know that the flame of spirit of wine is blue, that it produces only blue rays, and that every person in the room appears very pale, their faces, though painted ever so deep, have the aspect of death. The reason is evident. The blue rays not being capable of exciting or putting in motion the red color of the face, you see on it only a feeble and bluish color. But if one of the company is dressed in blue, such dress will appear uncommonly brilliant. Now the rays of the sun, those of a wax taper or of a common candle, illuminate all bodies almost equally, from whence it is concluded that the rays of the sun contain all colors at once, though he himself appears yellowish. In truth, when you admit into a dark room the rays of all the simple colors, red, yellow, green, blue, and violet, in nearly equal quantities, and blend them, they represent a whitish color. The same experiment is made with various powders, colored in like manner. On being mixed together, a whitish color is the result. Hence it is concluded that white is nothing less than a simple color, but that it is rather a compound of all the simple colors. Accordingly, we see that white is adapted to the reception of all colors. As to black, it is not properly a color. Every body is black when its particles are such that they can receive no motion of vibration, or when it cannot produce rays. The want of rays, therefore, produces the sensation of that color, and the more particles there are found in a body, not susceptible of any motion of vibration on its surface, the more blackish and obscure it appears. 15th of July, 1760. And letter number 28, read by Sandra.
Letter number 29 of Letters on Different Subjects in Natural Philosophy, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler. Translated by Henry Hunter. Letter 29. Transparency of bodies relative to the transmission of rays. I have already remarked that there are bodies, such as glass, water, and especially air, which transmit the rays of light, and on account of this property are denominated pellucid or diaphanous. The ether, however, is the medium in which the rays of light are formed, to which this property most intimately appertains, and other transparent bodies are endowed with it, only by means of the ether which they contain, and with which they are so blended, that the agitations excited by the light may be communicated farther, without being interrupted in their progress. But this transmission is never performed so freely as in the pure ether, though it always loses something, and this in proportion as the transparent body is more or less gross. The grossness may even become so considerable that the light shall be wholly lost in it, and then the body is no longer transparent. Thus, though glass be a transparent body, a great lump of glass several feet thick is not so. In like manner, however pure the water of a river may be, you cannot see the bottom where it is very deep, though you can very easily where it is shallow. Transparency, then, is a property of bodies relative only to their thickness, and when this property is ascribed to glass, to water, and etc., it must always be understood with this restriction, that these bodies are not too gross, and that to every species there is a certain measure of thickness beyond which the body ceases to be transparent. There is not one opaque body, on the contrary, which may not itself become transparent, if reduced to a plate extremely fine. Thus, though gold is not transparent, gold leaf is so, and on examining the minuter particles of all bodies with the microscope, they are found to be transparent. It may, then, be with truth affirmed that all bodies are transparent when reduced to a certain degree of fineness, and that no one is so when too gross. In common language, we denominate transparent the bodies which preserve this quality to a certain degree of thickness, though they lose it when they go beyond that bound. But with respect to ether, it is of its own nature perfectly transparent, and its extent diminishes not this quality in the smallest degree. The prodigious distance of the fixed stars prevents not their rays from being transmitted to us. But though our air appears to be of a perfect transparency, if it extended as far as the moon, that transparency would be entirely lost and would prevent every ray of the sun and of the other heavenly bodies from penetrating to us. We should then be involved in Egyptian darkness. The reason of it is evident, and we remark the same thing in sound, whose resemblance to light is confirmed in every respect. Air is the most proper medium for the propagation of sound, but the agitations excited in the air are capable of shaking also the particles of all bodies, and these again, putting in motion the interior particles, finally transmit the vibration through the substance of all bodies, unless they be too thick. There are bodies, then, which, relatively to sound, are the same thing which transparent bodies are, relatively to light, and all bodies have this property with relation to sound, provided they are not too thick. When you are in your apartment, you can hear almost everything that passes in the antechamber, though the doors are closely shut, because the agitation of the air in the antechamber communicates itself to the partitions, and penetrates through them into the inner apartment, with some loss, however. Were the partition removed, you would undoubtedly hear more distinctly. Now, the thicker the walls are, the more of its force does the sound lose in piercing through them, and the walls may be made so thick that nothing could be heard from without, unless it were some terrible noise, such as a discharge of cannon. This leads me forward to a new remark, that very powerful sounds may be heard through walls, which are impenetrable to sounds more feeble, and, consequently, in order to form a judgment whether a wall is capable of transmitting sounds, it is necessary to take into the account not only the thickness of the wall, but likewise the strength of the sound. If the sound is very feeble, a very thin wall is sufficient to stop it, though a louder could find an easy transmission. The same thing holds as to bodies which are permeable only to a very strong light. Objects, not very brilliant, are invisible through a glass blackened with smoke, but the rays of the sun force themselves through it, and it transmits perfectly well the image of that luminary. Astronomers employ this method to observe him, for without such precaution he would dazzle the eye. And when you happen to be in a dark room, with an aperture in the shutter exposed to the sun, in vain will you attempt to exclude the light. By opposing your hand to the aperture, the rays of the sun will force themselves through. It is perceivable at the same time that the light of the sun loses much of its luster in passing through a body, which, relatively to other objects, is not itself transparent. But a very strong light may lose much of its luster before it is entirely extinguished, while a feebler light is lost at once. A piece of very thick glass, then, will not be transparent with respect to objects less brilliant, though the sun may be visible through it. These remarks on transparent bodies lead me to the theory of refraction, of which you have frequently heard, and which I shall endeavor to place in its proper light. 18th of July, 1760. End of Letter 29. Read by Elijah Fisher. Letter number 30 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 30, of the transmission of rays of light through transparent mediums and their refraction. As long as light moves in the same medium, whether it be ether, air, or any other transparent body, the propagation proceeds in straight lines, denominated rays, as they diverge from the luminous point in all directions, like the radii of a circle or a globe issuing from the center. In the system of emanation, the particles darted from luminous bodies move in straight lines. The same thing holds in that which I have had the honor of proposing, in which the agitations are communicated in straight lines, as the sound of a bell is transmitted in a straight line, by which also we judge from what quarter the sound comes. The rays in both systems, then, are represented by straight lines, as long as they pass through the same transparent medium, but they may undergo some bending in passing from one to another, and this bending is called the refraction of the rays of light, the knowledge of which is necessary to account for many phenomena. I proceed therefore to lay down the principles, in conformity to which the refraction takes place. It is an invariable law that when a ray, such as EC, figure 8, falls perpendicularly on the surface AB of another medium, it continues its progress in the same straight line extended as CF. It will in this case undergo no bending or refraction. If then EC is a trace of the sun falling perpendicularly on the surface AB of water or of glass, it will enter it in the same direction and continues its progress in the line CF, which is likewise perpendicular to the surface AB, so that EF shall be in one and the same straight line. This is only the case in which there is no refraction. But as often as the ray does not fall perpendicularly on the surface of another transparent body, it does not pursue its progress in the same straight line. It recedes less or more from it and undergoes a refraction. Let PC figure 9 be a ray falling obliquely on the surface AB of another transparent medium. On entering into this medium, it will not continue its progress in the direction of the line CQ, which is the line PC produced, but will recede from it in the direction of the line CR or CS. It will undergo then, at the point C, a bending, which we call refraction, which depends partly on the difference of the two mediums and partly on the obliquity of the direction of the ray PC. In order to comprehend the laws of this bending, it is necessary to explain certain terms employed in treating this subject. First, the surface AB, which separates the two mediums, that from which the ray comes and that into which it enters, is called the refracting surface. Secondly, the ray PC, which falls upon it, is called the incident ray. And thirdly, the ray CR or CS, which pursues in the other medium, a course different from CQ, is called the broken or refracted ray. And having drawn through the surface AB the perpendicular line ECF, we call. Fourthly, the angle PCE formed by the incident ray PC with the perpendicular EC, the angle of incidence. And fifthly, the angle RCF or SCF formed by the refracted CR or CS with the perpendicular CF is called the angle of refraction. Therefore, because of the bending which the ray of light undergoes, the angle of refraction is not equal to the angle of incidence, PCE. For producing the line PC to Q, the angles PCE and FCQ being vertical are equal to each other. Euclid's Element, Book 1, Problem 15, as you will easily recollect. The angle QCF, then, is equal to the angle of incidence, PCE. Therefore, the angle of refraction, RCF or SCF, is greater or less. There are, then, only two cases which can exist. The one in which the refracted ray, being CR, the angle of refraction, RCF, is less than the angle of incidence, PCE, and the other in which the refracted ray, being CS, the angle of refraction, is greater than the angle of incidence, PCE. In the former case, we say that the ray CR approaches the perpendicular CF, and in the other, that is refracted ray CS, recedes or deviates from the perpendicular. It is necessary then to inquire in which cases the one or the other of these changes will take place. And we shall find that this phenomenon depends on the difference of the density of the two mediums, or because the rays are transmitted with more or less difficulty through each of them. To prove this, it must be recollected that ether is of all mediums the most rare, and that through which rays are transmitted without the slightest resistance. After the other common transparent mediums are thus arranged, air, water, glass. Thus, glass is a medium more dense than water, water than air, and air than ether. This being laid down, we have only to attend to these two general rules. First, when rays pass from a medium less dense into one which is more so, the refracted ray approaches the more to the perpendicular. This is the case in which the incident ray being PC, the refracted ray is CR. Secondly, when the rays pass from a medium more dense to one less so, the refracted ray recedes from the perpendicular. This is the case in which the incident ray, being PC, the refracted ray is CS. Now, this bending is greater or less according as the two mediums differ in respect of density. Thus, rays in passing from air into glass undergo a greater refraction than when they pass from air into water. In both cases, however, the refracted rays approach the perpendicular. In like manner, rays passing from glass into air undergo a greater refraction than when they pass from water into air. But in these cases, the refracted ray recedes from the perpendicular. Finally, it must likewise be remarked that the difference between the angle of incidence and the angle of refraction is so much greater. As the angle of incidence is greater, or as the incident ray recedes farther from the perpendicular, the greater will be the bending or refraction of the ray. A relation between all these angles exists, and is determinable by geometry. But it is not now necessary to enter into the detail. What has been already said is sufficient from understanding what I have further to propose on the subject. 22nd July, 1760. End of Letter 30. Read by Elijah Fisher. Letter number 31 of letters on different subjects in natural philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard, Euler, translated by Henry Hunter. Letter 31. Refraction of Rays of Different Colors. You have seen that when a ray of light passes obliquely from one transparent medium to another, it undergoes a bending, which is called refraction, and that the refraction depends on the obliquity of the influence and the density of the mediums. I must now call upon you to remark that diversity of colors occasions likewise a small variety in the refraction. This arises undoubtedly from the circumstance that the rays which excite in us these sensations of different colors perform unequal numbers of vibrations in the same times, and that they differ among themselves in the same manner as sharper or flatter sounds do. Thus it is observable that rays of red undergo the least bending or refraction. After them come the orange, the yellow, the green, the blue, and the violet follow in order, so that violet-colored rays undergo the greatest refraction, it being always understood that the obliquity of the incidence and the density of the mediums are the same. Hence it is concluded that rays of different colors have not the same refrangibility, that the red are the least, and the violet the most refrangible. If then PC, figure 10, is a ray passing, for example, from air into glass, the angle of incidence being PCE, the refracted ray will approach the perpendicular CF, and if the ray be red, the refracted ray will be in the direction C, red. If it be orange, the refracted ray will be C, orange, and so of the rest, as may be seen in the figure. All these rays deviate from the line CQ, which is PC produced towards the perpendicular CF, but the red ray deviates the least from CQ, or undergoes the least refraction, and the violet recedes the farthest from CQ, and undergoes the greatest refraction. Now, if PC is a ray of the sun, it produces at once all the colored rays indicated in the figure, and if a piece of white paper is placed to receive them, you will in effect see all these colors. Hence it is affirmed that every ray of the sun contains at once all the simple colors. The same thing happens if PC is a ray of white, or if it proceeds from a white body. We see all the colors produced from it by refraction, whence it is concluded that white is an assemblage of all the simple colors, as we formerly showed. In truth, we have only to collect all these colored rays into a single point, and the color of white will be the result. It is thus we discover what are the simple colors. Refraction determines them incontestably. In following the order which it presents, they are these: 1, red; 2, orange; 3, yellow; 4, green; 5, blue; 6, violet. But it must not be imagined that there are but 6, for as difference of colors arises from the number of vibrations which rays perform in one and the same time, or rather the undulations which produce them, it is clear that the intermediate numbers equally give simple colors. But we want names by which to designate these colors, for between yellow and green we evidently perceive intermediate colors, for which we have no separate names. In conformity to the same laws are produced the colors visible in the rainbow. The rays of the sun, in passing through the drops of water which float through the air, are by them reflected and refracted, and the refraction decompounds them into the simple colors. You must undoubtedly have remarked that these colors follow each other in the same order in the rainbow: the red, orange, yellow, green, blue, and violet. But we discover in it also all the intermediate colors as shades of one color to another, and had we more names to distinguish these degrees, we might find more of them from the one extremity to the other. A more copious language may perhaps enable another nation actually to reckon a greater number of different colors, and another, it may be, cannot reckon so many, if, for example, it wants a term to express what we call orange. Some to these add purple, which we perceive at the extremity of the red, but which others comprehend under the same name with red. These colors may be compared to the notes of an octave, as I have done here, because the relations of colors, as well as those of sound, may be expressed by numbers. There is an even appearance that by straining the violet a little more, you may come round to a new purple, just as in rising from sound to sound, on going beyond B, you can come round to C, which is the octave above C. And as in music, we give to these two notes the same name, because of their resemblance. The same thing takes place in colors, which, after having risen through the intervals of an octave, resume the same names, or if you will, two colors, like two sounds, in which the number of vibrations in the one is precisely the double of the other, pass for the same and bear the same name. On this principle it was that Father Castel, in France, contrived a species of music of colors. He constructed a harpsichord, of which every key displayed a substance of a certain color, and he pretended that this harpsichord, if skilfully touched, would present a most agreeable spectacle to the eye. He gave it the name of the ocular harpsichord, and you must undoubtedly have heard it talked of. For my part, painting rather seems to be that to the eye which music is to the ear, and I greatly doubt whether the representation of several shreds of cloth of different colors could be very agreeable. 27th July, 1760. End of Letter 31. Read by Elijah Fisher.
Letter number 32 of Letters on Different Subjects in Natural Philosophy. This LibriVox recording is in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 32 of the Azure Color of the Heavens. You have just seen that the cause of the visibility of objects is a motion of vibration extremely rapid, by which the minuter particles of their surfaces are agitated, and that the frequency of these vibrations determines the color. It is the same thing whether these particles be agitated by an intrinsic force, as in luminous bodies, or whether they receive their agitation from illumination or from foreign rays, by which they are illuminated, as in opaque bodies. The frequency or rapidity of the vibrations depends on the grossness of these particles, and on their elasticity, as that of the vibrations of a musical string depends on its thickness and degree of tension. Thus, as long as the particles of a body preserve the same elasticity, they represent the same color, as the leaves of a plant preserve a green color as long as they are fresh. But when they begin to dry, the difference of elasticity which then takes place produces likewise a different color. This subject I have already discussed. I now proceed to explain why the heavens appear to us of a blue color in the daytime. On observing this phenomenon with the vulgar eye, it would appear that we are surrounded by a prodigious vault of azure, as painters represent the sky on a ceiling. I have no occasion to undeceive you respecting this prejudice. A small degree of reflection is sufficient to make you comprehend that the heavens are not an azure vault to which the stars are affixed, like so many luminous studs. You are perfectly convinced that the stars are immense bodies at inconceivable distances from us, and which move freely through a space almost void, or which is filled only by that subtle matter called ether. And I will show you that this phenomenon is to be ascribed to our atmosphere, which is not perfectly transparent. Were it possible to rise higher and higher above the surface of the earth, the air would become gradually more and more rare, till it ceased to assist respiration, and would at length entirely cease. We should then have reached the region of pure ether. Accordingly, in proportion as we ascend on mountains, the mercury in the barometer continues to fall, because the atmosphere becomes lighter and lighter, and then likewise it is remarked that the azure color of the heavens becomes fainter. And were it possible to mount into pure ether, it would entirely disappear. On looking upward, we should see nothing at all, and the heavens would appear black as night, for where no ray of light can reach us, everything wears the appearance of black. There is good reason then for asking why the heavens appear to be blue. This phenomenon could not exist were air a perfectly transparent medium as ether is. In that case, we should receive from above no other rays but those of the stars, but the luster of daylight is so great that the feeble light of the stars is absorbed by it. You could not perceive the flame of a taper in the daytime at any considerable distance, but that same flame in the night would appear very brilliant at much greater distances. This clearly proves that we must look for the cause of the azure color of the heavens in the want of transparency in the air. The air is loaded with a great quantity of small particles which are not perfectly transparent, but which, being illumined by the rays of the sun, receive from them a motion of vibration, which produces new rays proper to these particles, or else they are opaque and become visible to us from being illumined. Now the color of these particles is blue, and this explains the phenomenon. The air contains a great quantity of small blue particles, or it may be said that its minuter particles are bluish, but of a color extremely delicate, and which becomes sensible to us only in an enormous mass of air. Thus, in a room, we perceive nothing of this blue, but when the bluish rays of the whole atmosphere penetrate our eyes at once, however delicate the color of each singly, their totality may produce a very deep color. This is confirmed by another phenomenon, with which you must be well acquainted. If you look at a forest from a moderate distance, it appears quite green, but in proportion as your distance increases, it acquires a bluish cast, and this gradually becomes deeper and deeper. The forests on the mountains of Harz, which may be seen from Magdeburg, appear thence to be blue, but viewed from Halberstadt they are green. The great extent of air between Magdeburg and these mountains is the reason of it. However delicate or rare the bluish particles of the air may be, there is such a prodigious quantity of them in that interval, the rays of which enter into the eye at once, that they represent a tolerable deep blue. Footnote. This explanation of the blueness of the sky is strained and unsatisfactory. The air is like water, perfectly colorless, otherwise any portion of it might be distinguished by the sight. Besides, the blueness of the sky, even in clear weather, is not uniformly the same, but acquires different degrees of intensity, and different shades from a variety of circumstances, the climate, the season, and the elevation of the place. The true explanation of the phenomenon must be sought from other principles. The most refrangible rays are, at minute distances, attracted or repelled by colorless substances with the greatest force. A sunbeam, therefore, in its passage through the atmosphere, will first lose its violet rays most profusely, next the indigo, then the blue, and if the track be of sufficient length, perhaps a few of the green. The rays thus separated are either absorbed by the air, or they are reflected, and cause the blue appearance. Hence, on the summits of lofty mountains, the color of the heavens seems faint and dark, and inclined somewhat to violet. On the contrary, in dense, humid air, the color is a light milky blue. Hence also the bright azure which paints the sky of the southern regions, according to the dryness of the air and the shortness of the light's tract. For the same reason, not only the quantity, but even the quality of the light which we receive from the sun depends on his altitude. At rising and setting, those rays which reach the surface and even the lower range of clouds are chiefly the reddish. At a greater elevation of the sun, the prevailing color of his beams is somewhat orange, and when still higher it is a dilute yellow. The same principles will account for the color of the ocean, which is dark blue. It is only in seas not exceeding 100 fathoms in depth that the reflection from the white bottom dilutes the proper color and forms a glaucous hue. This appearance is an invariable sign of the shallowness of the water, which is often a token of the proximity of the land. Dr. Halley relates an observation that he made in a diving bell, which confirms these reasonings. After descending to a great depth in the sea, he stretched out his hand, on which the sun shone through the water and painted a beautiful crimson. The same observation may be extended even to substances that are reckoned opaque. Hold an ivory knife in the focus of a burning glass, perpendicular to the pencil of light, and a bright yellowish spot will be perceived on the back. Incline the knife gradually, and the color of the spot will pass through all the intermediate shades and terminate in a fine red. It is scarce necessary to remark that this experiment must be performed expeditiously, lest the ivory be scorched. End of footnote. We remark a similar phenomenon in a fog, when the air is loaded with a great quantity of opaque particles of a whitish color. On looking only to a small distance, you scarcely perceive the fog, but when the distance is considerable, the whitish color becomes very perceptible, to such a degree that it is impossible to see through it. The water of the sea appears green at a certain depth, but when you take up a small quantity, as much, for instance, as a glass will contain, it is sufficiently diaphanous and has no sensible color. But in a great extent, when you look toward the bottom, so many greenish rays collected produce a deep color. 27th of July, 1760. End of letter 32, read by Sandra.
Letter 33 of Letters on Different Subjects in Natural Philosophy, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 33. Of rays issuing from a different luminous point, and of the visual angle. As long as the rays produced by the rapid vibration of the miniature particles of a body move in the same transparent medium, they preserve the same direction, or diffuse themselves in all directions, in straight lines. These rays may be represented by the radii of a circle, or rather of a sphere, which, issuing from a center, proceed in straight lines to the circumference, and it is on account of this resemblance that we employ the same term radius, or ray, to express them. Though, properly speaking, the light does not consist of lines, but of very rapid vibrations going continually forward in the direction of straight lines, and for this reason, light may be considered as straight lines, issuing from a luminous point in all directions. Let C, Plate 1, Figure 11, be a luminous point, from which rays issue in all directions. Let two spheres be described round C as a center, of the one of which let the great circle be A, B, D, E, and the other A, B, D, E. The light diffused over the surface of the smaller sphere, A, B, D, E, will likewise occupy that of the greater sphere, A, B, D, E. The light then must be more faint and weak at the surface of this last than on that of the smaller sphere, A, B, D, E. Hence, it may be concluded that the effect of light must be smaller in proportion to the distance from the luminous point. If we suppose that the radius of the greater sphere is double that of the smaller, the surface of the greater sphere will be 4 times as great. Since, therefore, the same quantity of light is diffused over the surface of the greater sphere and over that of the smaller, it must follow that light at double the distance is 4 times more faint, at thrice the distance 9 times, at a quadruple distance 16 times, and so on. On applying this rule to the light of the sun, it will appear that if the earth were removed to double the distance from the sun, the light derived from him would be rendered 4 times more faint, and if the sun were 100 times farther from us, his brightness would be 100 times 100, that is 10,000 times less. Posing then a fixed star to be as great and as luminous as the sun, but that it was 400,000 times farther from us, its light will be 400,000 times 400,000, that is 160 billion times more faint than that of the sun. Hence we see that the light of a fixed star is nothing compared to that of the sun, and this is the reason that we do not see the stars in the daytime. A feebler light always disappears in preference of one much more bright. The same thing holds good with respect to candles and all other luminous bodies, which administer less light in proportion to their distance from us. And you must have frequently remarked that, however strong a light may be, it is insufficient to assist us in reading a printed book, if you remove from it to any considerable distance. There is still another circumstance, closely connected with what I have just observed, namely that the same object appears smaller to us in proportion to its distance. A giant, at a great distance, does not appear taller than a dwarf near us. To form a clear judgment of this, it is necessary to attend to the angles at which these objects are seen by us. Let us suppose, then, Plate 1, Figure 12, AB to be an object, say a man, and that the eye looks at it from the point C. Draw from that point these straight lines, AC and BC, which represent the extreme rays proceeding from the object to the eye. We call the angle formed at C the visual angle of that object for the point C. If we look at the same object from a smaller distance at D, the visual angle D will be undoubtedly greater. Hence it is clear that the more distant the same object is, the smaller its visual angle, and the nearer it approaches, its visual angle becomes greater. Astronomers measure very accurately the angles under which we see the heavenly bodies, and they have found that the visual angle of the sun is somewhat more than half a degree. If the sun were twice farther from us, this angle would be reduced to the half, and then it will not seem surprising that it should furnish us 4 times less light. And if the sun were 400 times farther off, his visual angle would become so many times less, and then that luminary would appear no greater than a star. We must therefore carefully distinguish the apparent greatness of any object from its real greatness. The first is always an angle greater or less, according as the object is nearer or more distant. Thus, the apparent greatness of the sun is an angle of about half a degree, whereas his real magnitude far surpasses that of the earth. For the sun being a globe, his diameter is estimated to be 172,000 German miles, while the diameter of the earth is only 1,720 miles. 29th of July, 1760. End of letter 33. Read by Elijah Fisher. Letter number 34 of Letters on Different Subjects in Natural Philosophy, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 34, of the supplement which judgment lends to vision. What I have now submitted to you on the phenomenon of vision belongs to optics, which is a branch of mixed mathematics, and which, likewise, holds a considerable rank in physics. Beside colors, the nature of which I have endeavored to explain, it is the benefits of optics to treat of the manner in which vision acts, and of the different angles under which objects are seen. You must have already remarked that the same object may be viewed, sometimes under a greater visual angle, sometimes under a smaller, as it is less or more distant from us. I say farther that a small object may be viewed under the same angle as a great one, when the former is very near and the latter very distant. A small dish may be placed before the eye in such a manner as to cover the whole body of the sun, and, in effect, a plate of half a foot diameter, at the distance of 54 feet, exactly covers the sun, and is seen under the same angle. And yet what a prodigious difference between the size of a plate and that of the sun! The full moon appears to us under nearly the same visual angle as the sun, and, of consequence, nearly as great, though in reality much smaller. But it is to be considered that the sun is almost 400 times more remote from us than the moon. The visual angle is a point of so much the more important in optics that the image of the objects which paint themselves on the bottom of the eye depend upon it. The greater or less the visual angle is, the greater or less the objects, are great or little. And as we see objects out of ourselves, only so far as their images are painted on the bottom of the eye, they constitute the immediate object of vision or sensation. One of these images, therefore, leads us to the knowledge only of three things. First, its figure and its colors conduct to the conclusion that there is, out of us, a similar object of such a figure and such a color. Secondly, its magnitude discovers the visual angle under which the object appears to us. And finally, its place on the bottom of the eye makes us sensible of the direction of the external object relatively to us, or that in which the rays emitted from it reach our eyes. In these three particulars consists the phenomenon of vision, and we only perceive, first, the figure and colors, secondly, the visual angle, or the apparent magnitude, and thirdly, the direction, or the place in which we conclude that the object exists. Vision, then, discovers to us nothing respecting either the real magnitude of objects or their distances. Though we frequently imagine that we can determine by the eye the magnitude and distance of an object, this is not an act of vision, but of the understanding. The other senses and habits of long standing enable us to calculate at what distance an object is from us. But this faculty extends only to objects at no great distance. Whenever their distance becomes considerable, our judgment cannot exercise itself with certainty, and if sometimes we venture to hazard a decision, it is generally very remote from the truth. Thus, no one can pretend to say that he sees the magnitude or the distance of the moon, and when the vulgar imagine they can judge of the first, by considering it as equal to that of the terrestrial bodies which are seen under the same angle, it is not by vision they are deceived, but by their judgment, which they want to apply to an object far beyond their reach. It is certain, therefore, that the eyes alone can determine nothing respecting the distance and magnitude of objects. To this subject may be referred the very remarkable case of a man born blind, who obtained sight by means of an operation at an advanced period of life. This person was at first dazzled. He could distinguish nothing as to the magnitude and distance of objects. Everything appeared so near that he wanted to handle them. A considerable time and long practice were requisite to bring him to the real use of sight. He was under the necessity of serving a long apprenticeship, such as we perform during the term of childhood, and of which we afterwards perceive no recollection. That it is which instructed us that an object appears to us so much the more clear and distinct as it is nearer, and reciprocally that an object which appears clear and distinct is nearer, and when it appears obscure and indistinct, that it is at a distance. It is thus that painters, by weakening the tints of the objects which they wish to appear remote, and strengthening those which they would represent as near, are enabled to determine our judgment comfortably to the effect which they mean to produce. As they succeed so perfectly that we consider some of the objects represented in painting as more distant than others, an illusion which could not take place if vision discovered to us the real distance and magnitude of objects. 1st of August, 1760. End of Letter 34. Read by Elijah Fisher. Letter 35 of Letters on Different Subjects in Natural Philosophy, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 35. Explanation of certain phenomena relative to optics. You have just seen that vision alone discovers to us nothing respecting either the real magnitude or the distance of objects, and that all we imagine we see, whether as to the distance or magnitude of any object, is the effect of judgment. We must carefully distinguish that which the senses represent to us, from what judgment adds, in which we frequently deceive ourselves. Many philosophers who have declaimed against the accuracy of the senses, and who meant thence to infer the uncertainty of all human knowledge, have confounded the proper representations of our senses with judgment. This is their mode of reasoning. We see the sun no bigger than a trencher, though it be infinitely greater. Therefore the sense of seeing deceives us. Therefore all our senses deceive us. At least, we cannot depend on them. Therefore, all the knowledge we acquire by means of the senses is uncertain and probably false. We, therefore, know nothing. Such is the reasoning of these skeptics, who boast so vaingloriously of their ingenuity, though there be nothing so easy as to say that everything is uncertain, and the greatest dunce may make a shining figure in this sublime philosophy. But it is absolutely false that the sight represents to us the sun no bigger than a pewter plate. It determines nothing, whatever respecting its magnitude. It is our judgment alone that deceives us. When the objects, however, are not very distant, we can pronounce with tolerable exactness of their dimensions and distances, and the other senses, joined to the degree of clearness with which we see these same objects, render our judgments sufficiently certain. Now, as soon as we have the idea of the distance of an object, we form to ourselves, likewise, that its real magnitude, knowing that it depends on that distance. Hence, the more distant we reckon an object to be, the greater we conclude its magnitude, and, reciprocally, the nearer we conclude it is, the smaller we suppose it. We, of course, frequently take one body for another of much greater magnitude, when a suspension of judgment prevents our taking distance into the account. The reason is that a very large body may be seen, at a great distance, under the same angle as a small object placed near us. There is another phenomenon, well known to everyone, and which has given occasion to many disputes among the learned, and which it is now perfectly easy to explain. The full moon appears to every eye at the time of her rising to be much greater than when she has got to a considerable height above the horizon, though the visual angle of the apparent magnitude be the same. The sun, too, at the same time of rising and setting, appears to everyone greater than at noon. What, then, is the foundation of this judgment, so universal and so false? It is, undoubtedly, because we judge the sun and the moon, in the horizon, to be at a greater distance from us than when they have got to a considerable height. But how come we to form such a judgment? The common answer is that when the sun and the moon are in the horizon, we perceive a great many objects between them and us, which seem to increase their distance. Whereas, when the sun and moon have risen to a great height, we perceive nothing between them and us, and therefore conclude that they are nearer. I know not whether this explanation will be satisfactory. It may be objected that an empty apartment appears greater than one completely finished, though the size be exactly the same. Several intervening objects, therefore, do not always lead us to imagine that one more remote is at a greater distance than is really the case. I flatter myself that the following solution will be deemed more natural and better sounded. Let the circle A, Plate 1, Figure 13, represent the Earth, and the dotted circle the atmosphere, or air, with which the Earth is surrounded. Suppose yourself stationed at the point A, If the moon is in the horizon, the rays will reach you in the direction of the line BA. But in her extreme height, the rays will descend in line CA. In the first case, the rays pass through the greater space, BA, and in the second case, through the smaller space, CA. Now, you will please to recollect that the rays of light which pass through a transparent medium have their force diminished in proportion to the length of the passage. The atmosphere, or air, then, being a transparent medium, the ray BA must, in its passage, lose much more of its force than the ray CA. Hence it follows, in general, that all the celestial bodies appear much less brilliant in the horizon than when fully risen and elevated. We are able to look directly even at the sun when he is in the horizon, and when once he has gained a certain height, the eye is constrained to shrink from his lustre. I conclude from this that the moon too appears less brilliant in the horizon than when elevated. Now, you will recollect what I said a little above, in speaking of effect in painting, that the same object appears to us more distant when its light is weakened. The moon, then, being in the horizon, must appear more distant than at any point of elevation. The consequence is obvious. As we judge the distance of the moon greater in the horizon, we must likewise judge her magnitude greater. And in general, all the stars, when near the horizon, appear to us greater because their apparent distance is greater. 3rd of August, 1760. End of letter 35. Read by Elijah Fisher. Letter number 36 of Letters on Different Subjects in Natural Philosophy, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 36 of Shade. I have endeavored to explain almost all that is usually treated of in optics. All that remains is to speak of shade. You already know too well what is meant by shade, to render it necessary for me to dwell long on the subject. Shade always supposes two things: a luminous body and an opaque body, which does not transmit the rays of light. The opaque body, then, prevents the rays of a luminous body from getting behind it, and the space which the rays cannot reach from this interception is called the shade of the opaque body, or what comes to the same thing. Shade includes all that space in which the luminous body is not to be seen, because the opaque body obstructs its rays. Let A, Plate 1, Figure 14, be a luminous point, and B, C, D, E an opaque body. Draw the extreme rays A, B, M, A, D, N, touching the opaque body. It is evident that no ray of light proceeding from A can penetrate into the space M, B, E, D, N, and in whatever point within that space the eye may be placed at O. For example, it will not see the luminous body. This space is the shade of the opaque body, and we see that it is continually increasing and may extend to infinity. But if the body from which the rays proceed be itself of great magnitude, the determination of the shade is somewhat different. There are 3 cases which demand consideration. The first is when the luminous body is less than the opaque, the second when they are equal, and the third when the luminous body is in the greater. The first case is that which we have now been considering, in which the light is smaller than the opaque body. The second is represented, Plate 1, Figure 15, in which the luminous body A is of the same magnitude with the opaque body B, C, E, D. If you draw the extreme rays A, B, M, A, E, N, the space M, B, E, N will be shaded, and through the whole of that space it will be impossible to see the luminous body. You see likewise that the lines B, M, and E, N are parallel, and that the shade extends to infinity, always preserving the same breadth. The third case is exhibited, Plate 1, Figure 16, in which the luminous body, AA, is greater than the opaque body, B, C, E, D. The extreme rays touching the opaque body in B and E, if produced, will meet the point O, and the space of the shade BOE becomes finite and terminates in O. The shade, in this case, is termed conical. It is only into this space that the light has no admission, and in which it is impossible to see the luminous body. To this third case belongs the shade of the celestial bodies, which are much smaller than the luminous body, which enlightens them, namely, the sun. We have here, then, another display of the Creator's wisdom. For if the sun were smaller than the planets, their shades would not be terminated, but extend to infinity, which would deprive immense spaces of the benefit of the sun's light. But the magnitude of that luminary, surpassing by so many times that of the planets, their shades are contracted to very narrow bounds, from which alone the light of the sun is excluded. It is thus that the earth and the moon project their conical shades, and the moon may occasionally plunge into the shade of the earth, either partially or totally. When this takes place, we say the moon is eclipsed, either wholly or in part. In the former case, we call it a total eclipse of the moon, in the other, a partial eclipse. The moon likewise projects her shade, but it is smaller than that of the earth. It may happen, however, that the shade of the moon should extend as far as to the earth, and then those who are involved in that shade undergo an eclipse of the sun. An eclipse of the sun then takes place, when the moon, interposing, prevents our seeing the sun, wholly or in part. We see not the sun by night, though there be no eclipse, but we are then in the shade of the earth, which causes our greatest obscurity. Hitherto we have considered only the cases in which the rays of light are transmitted in straight lines, which is the processed object of optics. But it has already been remarked that the rays of light are sometimes reflected and sometimes broken or retracted. You will recollect that when the rays fall on a well-polished surface, such as a mirror, they are reflected from that surface, and when they pass from one transparent medium to another, they undergo retraction, and are, in some sense, broken. Hence arise two other sciences. That which considers vision in reference to reflected rays is called Catoptrics, and that which has for its object vision in reference to broken or retracted rays is termed Dioptrics. Optics treat of vision relatively to direct rays of light. I shall present you with a summary of these two sciences, Catoptrics and Dioptrics, as they disclose phenomena which are every day presenting themselves, and of which it is of importance to investigate the cause and the properties. Everything relating to the subject of vision is, beyond contradiction, an object highly worthy of exciting curiosity and of an engaging attention. 5th of August, 1760. End of Letter 36. Read by Elijah Fisher. Letter 37 of Letters on Different Subjects in Natural Philosophy, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 37 of Catoptrics and the Reflection of Rays from Plane Mirrors. Catoptrics treat of vision relatively to reflected rays. When rays of light fall on a well-polished surface, they are reflected in such a manner that the angles on all sides are equal among themselves. To set this in a clear light, let AB, Plate 1, Figure 17, be the surface of a common mirror, and P a luminous point, whose rays P, Q, PM, P small m, fall upon the mirror. Of all these rays, let PQ be that which falls perpendicularly on the mirror, and which has this particular and remarkable property, that it is reflected upon itself in the direction of QP, just as on a billiard table, when the ball is struck perpendicularly against the ledge, it is repelled in the self-same direction. But every other ray, as PM, is reflected in the line MN in such a manner as to make the angle AMN equal to the angle BMP, in which it is to be remarked that the ray PM is named the incident ray, and MN the reflected way. In like manner, to the incident ray P small m will correspond the reflected way, MN. And consequently, because of the reflection, the ray PM is continued in the direction of the line MN, and the ray P small m in the direction of MN, so that we have the angle AMN equal to BMP, and the angle AMN equal to the angle BMP. This property is thus announced. The angle of reflection is always equal to the angle of incidence. I have already taken notice of this striking property, but my design, at present, is to show what the phenomena in vision are which result from it. First, it is evident that an eye, placed at N, will receive from the luminous point P the reflected ray MN. Thus the ray which excites in the eye the sensation of the body from whence it proceeded comes in the direction MN, just as if the object P were in some point of that line. Hence it follows that the eye must see the object P in the direction NM. In order the more clearly to elucidate this fact, we must have resource to geometry, and you will recollect with pleasure the propositions on which the following reasoning is founded. Let the perpendicular ray PQ be produced on the other side to the mirror to R, so that QR shall be equal to PQ, and I will show you that all the reflected rays MN and MN, being produced behind the mirror, must meet in that point. For, taking the two triangles PQM and RQM, they have, first, the side MQ common to both, then the side QR was made equal to the side PQ, and finally the angle PQM, being a right angle, its adjacent angle RQM must, likewise, be a right angle. Therefore, these two triangles, having each an equal angle, contained by two equal sides, shall be every way equal, and consequently the angle PMQ equal to the angle RMQ. But the angle AMN and the angle RMQ, being vertical, are equal to each other. Therefore, also, the angle AMN shall be equal to the angle PMQ. That is, the angle of reflection shall be equal to the angle of incidence. In the same manner, it is demonstrated that the reflected ray MN, being produced, would likewise pass through the point R, and consequently produce in the eye the same effect, as if the object P were actually placed behind the mirror at R. this point being in the perpendicular PQR at the same distance as P from the surface of the mirror, but on different sides. This will enable you to comprehend clearly why mirrors represent objects as if they were behind them, and why we judge that these objects are placed as far behind the surface of the mirror as they really are before it. It is thus the mirror transports objects into another place, without changing their appearance. To distinguish in the mirror that apparent object from the real, we name the apparent object the image, and we say that the images represented by reflected rays are behind the mirror. This denomination serves to distinguish real objects from the images of them represented in mirrors, and the images which we see in mirrors are perfectly equal and similar to the objects, with this exception, that what is in the object is on the left, appears in the image on the right, and reciprocally. Thus a person, wearing his sword on the left side, appears with it in the mirror on his right. From what has been said, it is always easy to settle the image of any object whatever the mirror. For AB, Plate 2, Figure 1, being a mirror, and EF an object, say an arrow, draw from the points E and F the perpendiculars EG and FH to the surface of the mirror, and produce these to E and F, so that EG shall be equal to EG, and FH to FH. EF will be the image sought, which will be equal to the object EF, because the quadrilateral figure GEF, H, is, in all respects, equal to the quadrilateral figure GEFH. It must be still further remarked that were you even to cut off the mirror a part, as CB and AC was the mirror, the image, EF, would not be changed. And consequently, when the mirror is not sufficiently large to admit the falling of the perpendiculars EG and FH upon it, we must suppose the plane of the mirror to be extended, as we produce lines in geometry, when we want to let fall perpendiculars upon them. When I have said respects only common mirrors, whose surface is perfectly plane, convex and concave mirrors produce different reflex. 7th of August, 1760. End of Letter 37. Read by Elijah Fisher. Letter number 38 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler. Translated by Henry Hunter. Letter 38. Reflection of Rays from Convex and Concave Mirrors. Burning Mirrors. Everything relating to the reflection of rays is reduced, as you have seen, to two things, the one of which is the place of the image which the reflected rays represent, and the other the relation of the image to the object. In ordinary, or plane mirrors, the image of the object is behind the mirror, at a distance equal to that of the object before the mirror, and it is equal and similar to the object. To both of these circumstances we must attend, when the mirror is not plane, but when its surface is convex or concave, for in either case the image is, for the most part, strangely disfigured. You must frequently have remarked that on presenting any object before a spoon very highly polished, you see its image greatly disfigured, whether reflected from its interior surface, which is concave, or from its exterior, which is convex. A globe of silver, finely polished, represents objects with sufficient accuracy, but in miniature. If the interior surface of the globe is well polished, objects appear upon it magnified, provided always that they are not too distant. For the same objects may, likewise, appear smaller and inverted, if they are removed far from the mirror. There is no occasion to take a whole globe, any part of its surface whatever produces the same effect. These mirrors are denominated spherical, and these are two sorts of them. The one is convex, and the other concave, according as they are taken on the exterior, or interior surface of the sphere. They are compounded of various metals, susceptible of a fine polish, whereas plain mirrors are made of a plate of glass, and converted on one side with a preparation of mercury, designed to stop the passage of the rays and to reflect them. I begin with convex mirrors. Let ACB, Plate 2, Figure 2, be a mirror, the segment of a sphere, whose center is G. If you place before this mirror an object E at a great distance, its image will appear behind the mirror, at the point D, the middle point of the radius of the sphere CG, and the magnitude of this image will be to that of the object, in the relation of the lines CD and CE. It will therefore be, in this case, much smaller than the object, as the line CD is, in effect, much smaller than the line CE. If the object E approaches to the mirror, so likewise will its image. This is all demonstrable on geometrical principles, by supposing that any incident ray whatever, say EM, is reflected in the direction of MN, so that the angle BMN may be equal to the angle CME. Thus, when the eye is at N, receiving the reflected ray MN, it will see the object E according to that direction, and it will observe it in the mirror at the point D, or in other words, D will be the image of the object placed at E, but smaller. It is, likewise, easy to see that the smaller the sphere is, of which the mirror is a segment, the more, likewise, is the image diminished. I proceed to concave mirrors, the use of which is very common on many occasions. Let ACB, Plate 2, Figure 3, be a mirror, forming part of a sphere, whose center is G, and a GC a radius. Let us suppose an object E very distant from the mirror. Its image will appear before the mirror at D, the middle point of the radius CG. For any ray of light whatever, EM, from the object E, falling on the surface of the mirror at the point M, will be reflected thence, in such a manner as to pass through the point D, and when the eye is placed at N, it will see the object at D, but this image will be to the object in the ratio of CD to CE, and consequently, in this case, smaller than it. And when you bring the object nearer to the mirrors, the image retires, the object being placed even at the center G. The image is there likewise. If you bring the object still forward to D, the image will retire infinitely beyond E. But if the object be placed still farther forward, between C and D, the image will fall behind the mirror, and appear greater than the object. When you look at yourself in such a mirror, at some point between D and C, your face will appear frightfully large. This is explained by the nature of reflection, in virtue of which the angle of incidence, EMA, is always equal to the angle of reflection, CMN. To this species must be referred burning mirrors, and every concave mirror may be employed to burn. This remarkable property merits a more particular explanation. Let ABC, Plate 2, Figure 4, be a concave mirror, whose center is G, and instead of the object, let the sun be at E. His reflected rays will represent the image of the sun at D, the middle point between C and G. Now the magnitude of this image will be determined by the extreme rays SC. SC, this image of the sun will be, accordingly, very small. And as all the rays of the sun, which fall on the mirror ACB, are reflected in this image, they will be collected there, and will have so much more force, as the image D is smaller than the surface of the mirror. But the rays of the sun are endowed with the property of heating the bodies on which they fall, as well as that of illuminating them. Hence it follows that there must be at D a great degree of heat, and when the mirror is sufficiently large, this heat may become stronger than the most ardent fire. In fact, by means of such a mirror, you may burn, in an instant, any combustible body, and even melt metals of every kind. It is the image of the sun alone which produces these surprising effects. This image is usually denominated the focus of the mirror. It falls always in the middle point of the radius CG, between the mirror and its center G. You must carefully distinguish burning mirrors from burning glasses, of which I shall give some account in my next letter. 9th of August, 1760. End of letter 38. Read by Elijah Fisher. Letter number 39 of Letters on Different Subjects in Natural Philosophy, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler. Translated by Henry Hunter. Letter 39 of Dioptrics. Having explained the principal phenomena of Catoptrics, which result from the reflection of the rays of light, I proceed to treat of Dioptrics, whose object is to unfold the phenomena of the refraction of rays, which takes place when they pass through different transparent mediums. A ray of light does not pursue the same straight line, unless it continues its progress through the same medium. As soon as it enters another transparent medium, it changes its direction, more or less, according as it falls upon it, more or less obliquely. There is only one case in which it pursues a rectilinear course, namely when it enters the other medium perpendicularly. The instruments principally to be considered in Dioptrics are the glasses employed in the construction of telescopes and microscopes. These glasses are a circular form, but with two faces. Everything relating to them is reducible to the figure of these two faces, which may be plane or convex or concave. Their convexity or concavity is always equal to that of a sphere, of which the radius must be known, it being considered as the measure of the curve of those surfaces. This being laid down, we shall have several kinds of dioptric glasses. The first species, number 1, plate 2, figure 5, is that whose two faces are plane. By cutting a circular piece out of a plate of glass, or equal thickness, we shall have one of these species, which makes no change on objects, either as to magnitude or distance. Glass number 2 has one of its surfaces plane, and the other convex, and such are termed plano-convex. The third species, number 3, has one face plane, and the other concave, and these are called plano-concave. The fourth, number 4, has two convex surfaces, and is called double convex. Number 5 has two concave surfaces, and is called double concave. The species Nos 6 and 7 have one surface convex and the other concave, and we give them the name of meniscus. All these lenses are reducible to two classes, the one containing those in which convexity prevails, as numbers 2, 4, 6, and the other, concavity, is predominant, namely numbers 3, 5, 7. The former class is simply denominated convex, and the latter concave. These two classes are distinguished by the following property. Let AB, plate 2, figure 6, be a convex glass exposed to a very distant object, EF, whose rays GA, GC, GB fall on the glass, and passing through it, undergo a retraction, which will take place in such a manner that the rays proceeding from the point G shall meet on the other side of the glass, in the point g. The same thing will happen to the rays which proceed from every point of the object. By this alteration, all the reflected rays, A, small l, B, small m, C, small n, will pursue the same direction, as if the object were at small e, small g, small f, and inverted, and it will appear as many times smaller as the distance c, small g, shall be contained in the distance c, capital G. We say then that such a glass represents the object EF, behind it at small ef, and this representation is called the image, which is consequently inverted, and is, with the object itself, in the ratio of the distances of the glass from the image and of the glass from the object. It is clear, then, that if the sun were the object, the image represented at small ef would be that of the sun. Though very small, it will be so brilliant as to dazzle the eye, for all the rays which pass through the glass meet in this image, and there exercise their double power of giving light and heat. The heat there is nearly as many times greater as the surface of the glass exceeds in magnitude the image of the sun, named its focus, from which, if the glass be very great, you may produce the greatest effects of heat. Combustible substances placed in the focus of such a glass are instantly consumed. Metals are melted, and even vitrified by it, and other effects are produced, far beyond the reach of the most active and intense fire. The reason is the same as in the case of burning mirrors. In both, the rays of the sun, diffused over the whole surface of the mirror, or glass, are collected in the small space of the sun's image. The only difference is that in mirrors the rays are collected by reflection, and in glasses by refraction. Such is the effect of convex glasses, which are thicker in the middle than at the extremities, and which I have represented in numbers 2, 4, and 6. Those represented in numbers 3, 5, and 7 are thicker at the extremities than at the middle, and, being all comprehended under the term concave, produce a contrary effect. Let ACB, Plate 2, Figure 7, be a glass of this form. If you expose to it, at a great distance, the object EGF, the rays GA, GC, GB, proceeding from the point G, will undergo a refraction on leaving the glass in the direction of A, small l, C, small m, and B, small n, as if they had issued from the point small g, and an eye placed behind the glass at small m, for example, will see the object just as if it were placed at small EGF, and in a situation similar to that in which it is at the point G, but as many times smaller as the distance CG exceeds the distance G, small g. Convex glasses, then, represent the image of a very distant object behind them. Concave glasses represent it before them. The former represent it inverted, and the latter in its real situation. In both, the image is many times smaller as the distance of the object from the glass exceeds that of the glass from the image. On this property of glasses is founded the construction of telescopes, spectacles, and microscopes. 11th August, 1760. End of Letter 39. Read by Elijah Fisher. Letter number 40 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 40. Consternation of burning glasses and their focus. Convex glasses furnish some farther remarks which I beg leave to lay before you. I speak here of those glasses, in general, which are thicker in the middle than at the extremities, whether both surfaces be convex, or one plane and the other convex, or, finally, one concave and the other convex, provided, however, that the convexity exceed the concavity, or that the thickness be greater at the middle than at the extremities. It is farther supposed that the glasses have a spherical figure. They have, first, this property, that, being exposed to the sun, they present behind them a focus, which is the image of that luminary, and which is endowed, like it, with the property of illuminating and burning. The reason is that all the rays issuing from the sun and falling on this surface are collected by the refraction of the glass into a single point. The same thing happens whatever be the object exposed to such a glass. It always presents the image of it, which you see, instead of the object itself. The following figure will render what I have said more intelligible. Let ABCD, Plate 2, Figure 8, be a convex glass, before which is placed an object, EGF, of which it will be sufficient to consider the 3 points EGF. The rays which, from the point E, fall upon the glass are contained in the space AEB, and are all collected in the space A_e_b, by refraction, so as to meet in the point e. In the same manner, the rays from the point G, which fall on the glass, and which fill the space AGB, are comprehended, by means of retraction, in the space A_g_b, and meet in the point g. Finally, the rays from the point F, which fall on the glass in the angle AFB, are refracted, so as to meet in the point f. Thus we shall have the image e_g_f in an inverted position behind the glass, and an eye placed at O behind this image will be affected in the same manner, as if the object were at e_g_f, inverted, and as many times smaller as the distance d g is smaller than the distance cg. In order to determine the place of the image e_g_f, we must attend as well to the form of the glass as to the distance of the object. As to the first, it may be remarked that the more convex the glass is, in other words, the more that the thickness of the middle CD exceeds that of the extremities, the nearer the image will be to its surface. With regard to the distance, if you bring the object EF nearer to the glass, its image e_f retires from it, and reciprocally. The image cannot be nearer to the glass than when the object is at a very great distance from it. It is then at the same distance as that of the sun would be, which is denominated the focus of the lens. When the object, then, is very distant, the image falls in the very focus, and the nearer you bring the object to the glass, the farther the image retires from it, and that in conformity to a law in Dioptrics, by means of which you can always determine the place of the image, for every distance of the object, provided you know the focus of the glass, that is, the distance at which it collects the rays of the sun, in a space sufficiently small to set on fire a body exposed to it. The point where the rays meet is, as has been said, the place of the image. Now this point is easily found by experience. The different denominations of glasses are derived from it, as when we say such a glass has its focus at the distance of an inch, another at the distance of a foot, another at the distance of 10 feet, and so on. Or, more concisely, a glass of an inch, a foot, or 10 feet focus. Long telescopes require glasses of a very distant focus, and it is extremely difficult to make them exact. I once paid 150 crowns for one lens, which I sent to the Academy of Petersburg. It had its focus at the distance of 600 feet. I am convinced it was of no great value, but they would have it on account of its rarity. To be satisfied that the representation of the image small e, small g, small f in the preceding figure is real, you have only to hold at that place a piece of white paper, the particles of which are susceptible of the different kinds of vibrations on which colors depend. Then, when all the rays from the point E of the object on meeting at the point small e will put the particles of the paper into a movement of vibration similar to that which the point E has, and consequently you will see the point of small e of the same color as the point E. In like manner, the points small g and small f will have the same colors as the points G and F of the object, and you will likewise see on the paper all the points of the object expressed in their natural colors, which will represent the most exact and the most beautiful picture of the object. This will succeed perfectly well in a dark room, by applying a convex lens to a hole made in the shutter. You will then see on a sheet of white paper placed opposite to the aperture in the shutter all the external objects so exactly painted that you may trace them with a pencil. Painters make use of such a machine for designing landscapes and other views. 13th August, 1760. End of Letter 40. Read by Elijah Fisher. Letter number 41 of Letters on Different Subjects in Natural Philosophy, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 41, of Vision and the Structure of the Eye. I am now enabled to explain the phenomena of vision, which is undoubtedly one of the greatest operations of nature that the human mind can contemplate. Though we are very far short of a perfect knowledge of the subject, the little we do know of it is more than sufficient to convince us of the power and wisdom of the Creator. We discover in the structure of the eye perfections which the most exalted genius could never have imagined. I shall not detain you, at present, with an anatomical description of the eye. It is sufficient to remark that the exterior membrane, AB, Plate 2, Figure 9, is transparent, and is called the cornea of the eye. Behind this, on the inside, is another membrane, BM, circular and colored, which we call the iris, in the middle of which is an aperture called the pupil, which appears to us to be black. We find behind this aperture the crystalline humor, BBCA, which is a body somewhat like, in form, to a small burning glass. It is perfectly transparent and of a membranous substance. Behind this crystalline humor, the cavity of the eye is filled with a transparent jelly called the vitreous humor. The anterior space between the horny tunicle, AAB, and the crystalline AB contains a liquor fluid as water, which for that reason is called the aqueous humor. Here, then, are four transparent substances through which the rays of light that enter into the eye must pass. 1. The horny tunicle, or cornea. 2. The aqueous humor, between A and B. 3. The crystalline BBCA. 4. The vitreous humor. These four substances differ as to density, and the rays passing from one to another undergo a particular refraction, and they are so arranged that the rays coming from a point of any object are still collected within the eye in a point, and there present an image. The bottom of the eye at EGF, or the retina, is furnished with a whitish tissue adapted to the perception of images, and it is thus, you will please to recollect, that the images of objects may be represented on a white ground. Conformably to the same principle, all the objects whose rays enter into the eye are found painted on the retina. Take the eye of an ox, and having removed the exterior parts which cover the retina, you will see all the objects painted there so exactly that no artist could exceed it, or even arrive at such a degree of perfection. And, in order to see any object whatever, the object must always be painted on the retina. And when, unfortunately, any of the parts of the eye are injured, or lose their transparency, the person becomes blind. But it is not sufficient in order to our seeing objects that their images should be painted on the retina. Some are blind, though this takes place. Hence we see that images painted on the retina are not, after all, the immediate object of vision, and that the perception of the soul is communicated some other way. The retina is a reticulated contexture of nerves, the most subtle, communicating with a great nerve, which, coming from the brain, enters the eye at O, and is denominated the optic nerve. These small nerves of the retina are agitated by the rays of light which form the image at the bottom of the ray, and this agitation is transmitted by the optic nerve to the brain. It is there, undoubtedly, that mental perception is formed. But the most dexterous anatomist is unable to pursue these nerves to their source. The union of the soul with the body must forever remain a mystery. 15th of August, 1760. End of Letter 41. Read by Elijah Fisher. Letter 42 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 42. Continuation. Wonders discoverable in the structure of the eye. It will not be disagreeable to you, I hope, to contemplate with me somewhat more attentively the wonders discoverable in the structure of the eye. And first, the pupil presents an object highly worth of admiration. It is that aperture which we find in the middle of the iris, or star, by which the rays pass into the inside of the eye, and which appears black. The larger it is, the greater quantity of rays can enter into the eye, to form on the retina the image which appears painted there. Thus, the more the pupil is opened, the more brilliant this image will be. On carefully examining the human eye, we observe that the aperture of the pupil is sometimes greater and sometimes smaller. It is generally remarked that the pupil is contracted when exposed to a very strong light, and, on the contrary, very much dilated where the light is faint. This variation is absolutely necessary to the perception of vision. When we are in very strong light, the rays being more powerful, fewer of them are wanted to agitate the nerves of the retina. The pupil, accordingly, is then more contracted. Were it more dilated, and consequently admitted more rays, their force would agitate the nerves too violently, and occasion pain. It is for this reason we are unable to look upon the sun without being dazzled, and without sensible pain in the bottom of the eye. Were it possible for us to contract the pupil still more, so as to admit only a very small quantity of rays, we should not be very greatly encommoned by it. But the contraction of the pupil is not in our own power. Eagles possess this advantage, and are able to look directly at the sun, It is accordingly remarked that their pupil is then so much contracted as to appear reduced to a point. A clear light, requiring a very small dilation of the pupil, in proportion as the light decreases, the pupil dilates, and in the dark is so enlarged as almost to occupy the whole of the iris. If it remained in the same state of contraction as in the light, the rays which enter into it would be too weak to agitate the nerves as much as is necessary to perception. The rays must, therefore, be then emitted in greater abundance in order to produce a sensible effect. Were it in our power to open the pupil still more, we should be able to see in a greater degree of darkness. To this purpose we are told of a person who, having received a blow on his eye, the pupil was so dilated by it that he could read and distinguish the minutest objects in the dark. Cats and several other animals which roam in the dark have the faculty of enlarging the pupil much more than the human species, and owls have theirs at all times too much dilated to bear even a moderate degree of light. Now, when the pupil of the human eye dilates or contracts, it is not by an act of the will, man not having the power of dilating or contracting the pupil at pleasure. As soon as he enters into a luminous situation, it spontaneously contracts and dilates on his return to darkness. But this change is not produced in an instant. It requires a little time for this organ to accommodate itself to circumstances. You must no doubt have remarked that as often as you make a very sudden transition from a clear light to a dark place, as in the theatre of Schuch, you could not, at first, distinguish the company. The pupil was still too narrow to permit a few feeble rays which it admitted to make a sensible impression, but it gradually dilated to receive a sufficiency of rays. The contrary happens when you pass suddenly from darkness to a clear light. The pupil being then very much expanded, the retina is struck in a lively manner. You are quite dazzled, and under the necessity of shutting your eyes. It is, then, a very remarkable circumstance that the pupil should dilate and contract, according as vision requires, and that this change should take place almost spontaneously, and independently of any act of the will. Philosophers who examine the structure and the functions of the human body are greatly divided in opinion as to this subject, and there is little appearance that we shall ever have a satisfying solution of this wonderful phenomenon. The variability of the pupil is, however, an object essentially necessary to vision, and without which it would be very imperfect. But various other particulars are discoverable, equally entitled to admiration. 17th of August, 1760. End of Letter 42. Read by Elijah Fisher. Letter 43 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 43. Further continuation, astonishing difference between the eye of an animal and the artificial eye, or camera obscura. The principle on which the structure of the eye is founded is, in general, the same as that according to which I explained the representation of objects on white paper by means of a convex lens. Both of them must be resolved into this, that all the rays, proceeding from one point of the object, are again collected in a single point, by refraction. And it seems of little importance whether this refraction is performed by a single lens, or by the several transparent substances of which the eye is composed. It might even be inferred from thence that a structure more simple than that of the eye, by employing one single transparent substance, would have been productive of the same advantages. which would amount to a very powerful objection against the wisdom of the Creator, who has assuredly pursued the simplest road in the formation of all his works. Persons have not been wanting, who, from not having attentively examined the advantages resulting from the apparent complication, presumed to censure this beautiful production of the Supreme Being with a levity worthy of censure. They have pretended it was in their power to produce a plan more simple for the structure of the eye, because they were ignorant of all the functions which that organ had to discharge. I shall examine this plan of theirs, and I hope to convince you that it would be highly defective and altogether unworthy of being put in competition with that which actually exists. Such an eye, therefore, would be reduced to a simple convex lens, ABCD, Plate 2, Figure 10, which collects in a point all the rays coming from one and the same corresponding point in the object. But this is only near to the truth. The spherical form given to the surfaces of the lens is liable to this inconvenience, that it does not completely collect in one and the same point the rays which pass through its center and those which pass through the extremities. There is always a small difference, though almost imperceptible, in the experiments, by means of which we receive the image on a piece of white paper. But if this happened in the eye itself, it would render vision very confused. The persons to whom I have been alluding allege that it may be possible to find another figure for the surfaces of the lens, which shall have the property of collecting anew all the rays issuing from the point O in a point R, whether they pass through the center or through the extremities. I admit that this may be possible, but supposing the lens to possess this property with respect to the point O at the fixed distance CO, it would not possess it at points at a greater or less distance from the lens, or even admitting to this possible, which it is not, the lens would, most certainly, lose that property with regard to objects placed on one side, at T, for instance. Accordingly, we see that when objects are represented on white paper, though such as are directly before the lens, say at O, may be sufficiently well expressed, those which are obliquely situated, as at T, are always much disfigured, and very confusedly expressed, and this is a defect which the most ingenious artist is incapable of rectifying. But there is another, and one not less considerable. In speaking of rays of different colors, I remarked that in passing from one transparent medium to another, they undergo a different refraction, that rays of a red color undergo the least refraction, and violet-colored rays the greatest. Hence, if the point O were red, and if its rays in passing through the lens AB were collected at the point R, this would be the place of the red image. But if the point O were violet, the rays would be collected nearer to the lens, at V. Again, as white is an assemblage of all the simple colors, a white object placed at O would form several images at once, situated at different distances from the point O, the result of which would be, on the retina, a colored spot that would greatly disturb the representation. It is accordingly observable that when in a dark room the external objects are represented on white paper, they appear bordered with the colors of the rainbow, and it is impossible to remedy this defect by employing only one transparent body. But it has been remarked that this may be done by means of different transparent substances, but neither theory nor practice have hitherto been carried to the degree of perfection necessary to the execution of a structure which should remedy all these defects. The human eye, however, labors under none of the imperfections which I have mentioned, nor many others to which the hypothetical eye we have been analyzing would be liable. What a sublime idea must we form of him who has furnished not only the whole human species, but every animal, nay, even the vilest insects, with an organ of such curious construction.
19th August, 1760.
End of Letter 43. Read by Elijah Fisher. Letter number 44 of Letters on Different Subjects in Natural Philosophy, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler. Translated by Henry Hunter. Letter 44. Perfections discoverable in the structure of the eye. The eye, then, infinitely surpasses every piece of mechanism which human skill is capable of producing. The different transparent substances of which it is composed have not only a degree of density capable of causing different refractions, but their figure it likewise determined in such a manner that all the rays producing from one point of the object are exactly collected in one and the same point, whether that object be more or less distant, whether it is situated directly or obliquely with respect to the eye, and though its rays undergo different refractions, were the least change to be made in the nature and figure of these substances, the eye would lose all the advantages which we have been admiring. The strength of our sight is exactly proportioned to the extent of our necessities, and far from complaining that objects too remote escape this organ, we ought, on the contrary, to consider it as one of the most precious gifts of the Supreme Being. It must be farther remarked that in order to see objects distinctly, it is not sufficient that the rays which come from one point should be collected in another. It is likewise necessary that the point of reunion should fall precisely on the retina. If it fell either short of or beyond it, vision would become confused. Now if, for a certain distance or objects, this point of union fall upon the retina, those of more distant objects would fall in the eye, short of the retina, and those of near objects would fall beyond the eye. In either case, there would be a confusion in the image painted on the retina. The eyes of every man, therefore, are constructed for a certain distance. Some persons see distinctly only such objects as are very near to their eyes. We call them myopes, that is, short-sighted. Others, on the contrary, named presbytes, see distinctly objects only which are very distant. And those who see distinctly objects at a moderate distance are said to have good eyes. Both the other two, however, have the power of contracting or dilating the globe of the eye to a certain degree, and thereby of bringing nearer or of removing the retina, which enables them likewise to see clearly objects a little more or less distant. This, undoubtedly, greatly contributes to render the eye more perfect, and it cannot surely be ascribed to chance merely. Those who have good eyes derive most advantage from their structure, as they are thus in a condition to see distinctly objects very distant and very near, but this never exceeds a certain bound. There is, perhaps, no one who can see at the distance of an inch, and consequently still less at a smaller distance. If you hold a writing close to your eye, you will see the characters, but very confusedly. This is all I presume to offer on a subject of such high importance. 21st August, 1760. End of Letter 44. Read by Elijah Fisher. Letter number 45 of Letters on Different Subjects in Natural Philosophy, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 45. Of gravity, considered as a general property of body. Having now treated of light, I proceed to the consideration of a property common to all bodies, that of gravity. We finish that all bodies, solid and fluid, fall downward when they are not supported. I hold a stone in my hand. If I let it go, it falls to the ground and would fall still farther, were there an aperture in the earth. While I write, my paper would fall to the ground, were it not supported by the table. The same law applies to every body with which we are acquainted. There is not one that would not fall to the ground if it were not supported or stopped by the way. The cause of this phenomenon, or of this propensity of all bodies, is denominated gravity, which is said that bodies are heavy or possess gravity. We mean that they have a propensity to fall downward, and actually would fall if we remove what before supported them. The ancients were little acquainted with this property. They believed that there were bodies which had naturally a tendency to rise, such as smoke and vapors, and such bodies they termed light, to distinguish them from those which have a tendency to fall. But it has been discovered by experiment that it is the air which raises these substances aloft. For in a space void of air it is well known by means of the air pump that smoke and vapors descend as well as stone, and that these substances are, of their own nature, heavy like others. When, therefore, they rise into the air, the same law acts upon them, which acts upon a log of wood plunged into the water. Notwithstanding its gravity, it springs up as soon as you leave it to itself, and swims because it is not so heavy as water. And in virtue of a general rule, all bodies rise in a fluid of more gravity than themselves. If you throw a piece of iron, of copper, of silver, and even of lead, into a vessel full of quicksilver, they swim on the surface, and if you force them down, they ascend when left to themselves. Gold alone sinks, because it is heavier than quicksilver. And, since there are bodies which rise in water and in other fluids, notwithstanding their gravity, for this reason merely, that they are not so heavy as water or those other fluids, it is not at all surprising that certain bodies less weighty than air, such as smoke and vapors, should rise in it. I have already remarked that air itself possesses gravity, and that by means of this gravity it supports the mercury in the barometer. When, therefore, it is affirmed that all bodies are heavy, it is to be understood that all bodies, without a single exception, would fall downward in a vacuum. I might venture to add that they would fall with an equal degree of rapidity, for a feather and a piece of gold descend with equal velocity in an exhausted receiver. It might be objected to this general property of body that a shell discharged from a mortar does not at once fall to the ground like a stone which I let drop from my hand, but mounts into the air. It cannot, however, be inferred that the shell has no gravity, for it is evident that the strength of the powder hurls the bomb aloft. But for this, it would, without doubt, immediately fall to the ground. And we see, in fact, that it does not continue always to ascend, but as soon as the force which carries it upward is exhausted, down it comes with a rapidity that crushes everything it meets, a sufficient proof of its gravity. When, therefore, it is affirmed that all bodies are heavy, no one means to deny that they may be stopped, or that they may be thrown aloft. But this is effected by an external power, and it remains indubitably certain that all bodies whatever, as soon as left to themselves, at rest, or without motion, will assuredly fall when no longer supported. There is a cellar under my apartment, but the floor supports me, and preserves me from falling into it. Were the floor suddenly to crumble away, and the ark of the cellar to tumble in at the same time, I must infallibly be precipitated into it, because my body is heavy, like all other bodies with which we are acquainted. I say, with which we are acquainted, for there may perhaps be bodies destitute of weight, such as possibly light itself, the elementary fire, the electric fluid, or that of the magnet. Except these bodies, the gravity of which is not yet confirmed by experiment, gravity may be considered as a general property of all the bodies which we know, in virtue of which they all have a tendency to fall downward, and actually do so when nothing opposes their descent. 23rd of August, 1760. End of Letter 45. Read by Elijah Fisher. Letter number 46 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 46, Continuation of Specific Gravity. You have just seen that gravity is a general property of all the bodies with which we are acquainted, and that it consists in the effect of an invincible force, which presses them downward. Philosophers have warmly disputed whether there actually exists a power which acts in an invisible manner upon bodies, or whether it be an internal quality inherent in the very nature of the bodies, and, like a natural instinct, constraining them to descend. The question amounts to this: if the cause of gravity is to be found in the very nature of every body, or if it exists without it, so that were this extrinsic power to fail in its operation, the body would cease to be heavy. Before we attempt a solution of this, it will be necessary to examine more carefully all the circumstances connected with gravity. I remark first that when you support a body to prevent its falling, if it rests on a table, its pressure is equal to the force with which it would tend to fall, and if a thread is affixed to it by which it may be suspended, the thread is stretched by that force, in other words, by the gravity of that body, so that if the thread were not of a certain strength, it would break. We see, then, that all bodies exercise a degree of force on the obstacles which support them and prevent their falling, and that this action is precisely the same as that which would make the body descend if it were at liberty. When a stone is laid upon a table, the table is pressed by it. You have but to put your hand between the stone and the table to be sensible of this force, which may be increased to such a degree as even to crush the hand. This force is called the gravity of the body, and it is clear that the weight of the gravity, or of every body, signifies the same thing, both denoting the force with which that body is pressed downward, whether this force exists in the body itself or out of it. We have an idea, too, clear of the weight of bodies, to make it necessary to dwell longer on the subject. I only remark that when two bodies are joined together, their weight too is added, so that the weight of the compound is equal to the sum of the weight of the parts. From this we see that the weight of bodies may be very different. We have also the certain means of exactly measuring and comparing them by the help of a balance, which has the property of resting in equilibrium, when the bodies, put in its two scales, are of equal gravity. In order to make this comparison, we agree on some fixed measurement of a certain determinate weight, such as a pound, and by means of a good balance, all bodies may be weighed, and their gravity ascertained, according to the number of pounds which they contain. A body too great to be put into the scale of a balance may be divided, and the parts being weighed separately, you have only to add the particulars. The weight of a whole house, however large, may be thus ascertained. You must, no doubt, have frequently remarked that a small piece of gold weighs as much as a piece of wood greatly superior in size, a proof that the gravity of bodies is not always regulated by their magnitude, and a very small body may be of great weight, while a very large one may be light. Every body, then, is susceptible of two measurements, entirely different from each other. The one determines its magnitude or extent, called likewise its size. This measurement belongs to the province of geometry, which teaches the method of measuring the magnitude or extent of bodies. The other mode of measurement, by which their weight is determined, is totally different, and serves to distinguish the nature of the different substances of which bodies are formed. You can easily conceive several masses of different substances, all of the same magnitude or extent, each, for example, of a cubic figure, whose length, breadth, and height shall be a foot. Such a mass, if it be of gold, would weigh 1,330 pounds, if of silver 770 pounds, if of iron 500 pounds, and if of water only 70 pounds. Were it of air, it would weigh no more than the 12th part of a pound. From this you see that the different substances of which bodies are composed vary considerably in respect of gravity. To express this indifference, we employ certain terms which might appear equivocal, if they were not perfectly understood. Thus, when it is said that gold is heavier than silver, it is not to be understood that a pound of gold is heavier than a pound of silver. For a pound of whatever substance is always a pound, and is always precisely the same weight. But the meaning is that having two masses of the same size, the one gold and the other silver, the weight of the mass of gold will exceed that of the silver. And when it is said that gold is 19 times heavier than water, we mean that having two equal masses, the one of gold, the other of water, that which is of gold will have 19 times the weight of that which is of water. When we thus express ourselves, we say nothing of the absolute weight of bodies. We only speak by way of comparison, and with a reference always to masses on an equal size. Neither is it of importance whatever the size be great or small, provided they be equal. 25th August, 1760. End of Letter 46. Read by Elijah Fisher. Letter 47 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler, translated by Henry Hunter. Letter 47, Terms Relative to Gravity and Their True Import. Gravity, or weight, seems so essential to the nature of bodies that it is almost impossible to form the idea of a body diversified of this quality. And its influence is so universal in all our operations upon body that we must, in every instance, pay attention to its gravity or weight. As to our own persons, whether we stand, sit, or lie, we continually feel the effect of the gravity of our own body. We could never fall, if the body were not, as well as all its parts, endowed with this force. Language itself is regulated according to this property of bodies. The place toward which a body tends in its descent we term low, and the opposite direction from the body we term high. It must be remarked that when a body, in falling, is at perfect liberty, it always descends in a straight line, pursuing which its direction is said to be downward. This line is likewise called vertical, by which term we always mean a straight line, drawn from high to low, and if we conceive this line produced upward till it reaches heaven, we call that point in the heavens our zenith, an Arabian word denoting that point in the heavens which is directly over our head. You comprehend, then, that a vertical line is that straight line in which a body falls when no longer supported. When you affix a thread to any body, holding it fast at the other hand, that thread will be stretched out into a straight line, and that line will be vertical. Masons employ a small cord, with a leaden ball at one end, which they call a plummet, to direct the perpendicularity of the walls which they raise, for these, to be solid, must be vertical. All the floors of a house ought to be so level that the vertical line shall be perpendicular to them. The floor in that case is said to be the horizontal. And you will please to remember that a horizontal plane is always that to which the vertical line is perpendicular. When you are in a perfect plane, bounded by no mountain, its extremities are termed the horizon, a Greek word which signifies the boundary of flight. And this plane, then, represents a horizontal plane, just as the surface of a lake. We make use of still another term to express what is horizontal. We say that such a surface or line is level. We likewise say that 2 points are on the level, when a straight line passing through these 2 points is horizontal, so that the vertical or plumb line shall be perpendicular to it. But 2 points are not on the level, when the straight line drawn through these points is not horizontal, for then one of them is more elevated than the other. This is the case with rivers. Their surface has a declivity, for were it horizontal the river would be stagnant, and run down no longer, whereas all the rivers are continually flowing toward places less elevated. These are instruments by means of which we can ascertain whether 2 points are on the same level, or which is the higher, and by how much. This instrument is called a level, and the application of it is called the art of leveling. Were you to draw a straight line from any point in your apartment at Berlin to a given point in your apartment at Magdeburg, you might, by means of such an instrument, ascertain whether this line were horizontal, or whether one of these points were more or less elevated than the other. I believe the point at Berlin would be more elevated than that at Magdeburg, and I found this opinion on the course of the rivers Spree, Havel, and Elbe. As the Spree runs into the Havel, it must, of course, be higher, and for the same reason, the Elbe must be lower than the Havel. Berlin, therefore, stands higher than Magdeburg, provided you compare 2 points at an equal degree of elevation from the ground. For were a straight line to be drawn from the street pavement at Berlin to the pinnacle over the dome at Magdeburg, that line would perhaps be horizontal. Hence you see how useful the art of taking levels is when the conducting of water is concerned. For as water can only run from a more to a less elevated situation, before digging a canal you must be well assured that one of the extremities is more elevated than the other, and this is discovered by taking the level. In building a city, the streets should be so disposed as that, by means of a declivity on one side, the water may run off. It is otherwise in the construction of houses, the floors of which should be perfectly horizontal and without the smallest declivity, because there is no water to be discharged, except in the floors of stables, which are constructed with a gentle declivity. Astronomers take great pains to have the floors of their observations perfectly level to correspond with the real horizon in the heavens. The vertical line, produced upward, marks the zenith. 27th August, 1760. End of letter 47. Read by Elijah Fisher.
Letter 48 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by JJ. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler. Translated by Henry Hunter. Reply to certain objections to the Earth's spherical figure derived from gravity. You know well that the figure of the Earth is nearly that of a globe. It has, indeed, been demonstrated that its form is not perfectly spherical, but somewhat flattened toward the poles. The difference, however, is so trifling that it does not at all affect the object I have in view. Neither does the difference of mountain and valley excite any solid objection to its globular figure, for its diameter being 1,720 German miles, whereas the highest mountains, being scarcely half a mile in height, sink into nothing, compared to this prodigious mass. The ancients had a very imperfect notion of the real figure of the earth. It was, in general, considered as a huge massy substance, ABCD, Plate 2, Figure 11, flattened above as AB and covered partly with earth, partly with water. According to their idea, the surface AB alone was habitable, and it was impossible to go beyond the points A and B, which they considered as the extremities of the world. When, in the progress of discovery, it was found that the earth was nearly spherical and universally habitable, so that there were upon the globe spots diametrically opposite to us, the inhabitants of which are therefore called our antipodes, because their feet are turned directly toward ours. This opinion met with such violent contradiction that certain fathers of the church represented it as a dreadful heresy, and thundered out anathemas against all who believed in the existence of the antipodes. A man, however, would now pass for an idiot, who would call it in question, especially since the opinion has been confirmed by the experience of navigators, who have actually, more than once, sailed round the globe. But another difficulty here presents itself, the solution of which must assist us in discovering the real direction of gravity. If the circle AB, Plate 2, Figure 12, say they, represents the Earth, and we are at A, our antipodes will be diametrically opposite at B. As we, then, have the head upward and the feet downward, our antipodes must have the feet upward and the head downward, supporting these words to indicate the same direction, as when we pronounce the same words at the place where we are. For navigators who have made the circuit of the globe, observe that their head and feet had throughout maintained the same position relatively to the surface of the terrestrial globe. Some persons, whom this phenomenon embarrassed, formerly thought of explaining it by the comparison of a globe, over the surface of which you see flies and other insects crawl, on the under as well as the upper part. But they did not consider that the insects on the dependent surface adhere to it by their claws, and, without this assistance, would presently fall off. The antipode, then, must have his shoes furnished with hooks to hold him fast to the surface of the earth. But though he has none, he falls not any more than we do. Besides, as we imagine ourselves to be on the uppermost surface of the earth, the antipode has the same idea of his situation, and considers us as undermost. But the whole phenomena are easily accounted for on the hypothesis which experience has demonstrated, that the direction of gravity is sensibly perpendicular to the surface of the earth, at every point of that surface, that it varies at these different points, and that at those which are antipodes to each other, it must be exactly opposite. The terms upward and downward, therefore, do not express an invariable direction, but the direction of gravity wherever it is. Our antipodes have their heads downward only with relation to us, but not with relation to themselves. They, as well as we, are in the position which the power of gravity constrains them to preserve, and that position is similar relatively to the surface of the earth. You had undoubtedly no need of this explanation, but there was a time, and it is not long elapsed, when it would have been necessary, even to persons who were then honored with the appellation of the learned. 28th August 1760. End of Letter 48.
Letter 49 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Read by Verla Vieira. Letters on Different Subjects in Natural Philosophy. Volume 1, by Leonhard Euler. Translated by Henry Hunter. True direction and action of gravity relatively to the earth. Though the surface of the earth is unequal, because of the mountains and valleys which overspread it, it is, however, perfectly level wherever there is sea. The surface of water being always horizontal, and the vertical line, in the direction of which bodies fall, being perpendicular to it. If, then, the whole globe were covered with water, at whatever spot of the surface a person was, the vertical line would be perpendicular to the surface of the water. Thus, the figure A, B, C, D, E, F, G, H, I, Plate 3, Figure 1, representing the Earth, its surface being everywhere horizontal. At capital A, the line lowercase a, capital A, will be vertical. At capital B, the line lowercase b, capital B. At capital C, the line lowercase c, capital C. At capital D, the line lowercase d, capital D. At capital F, the line lowercase f, capital F, and so of the rest. Now, at every place, the vertical line determines what is to be denominated upward or downward. To persons at capital A, then, the point capital A is downward, and the point lowercase a upward. And to persons at capital F, the point capital F will be downward, and the point lowercase f upward, and so for every other spot on the surface of the earth. All these vertical lines, lowercase a, capital A, lowercase b, capital B, lowercase c, capital C, lowercase d, capital D, etc., are likewise named the directions of gravity, or weight, because bodies universally descend in the direction of these lines. Thus, a body left to itself at lowercase g would fall in the direction of the line lowercase g, capital G. Hence it is evident that bodies universally must fall toward the earth, and that perpendicularly to the surface of the earth, or rather of the water, if it were water. At whatever place of the earth, therefore, you may happen to be, as bodies fall there toward its surface, we call downward that which is directed toward the earth, or is nearest to it, and upward what is placed in the opposite direction, or is farthest from the earth. And universally, men having their feet pressed to the earth their feet will be downward and their heads upward. If the earth were a perfect globe, all the vertical lines lowercase a, capital A, lowercase b, capital B, lowercase c, capital C, being produced inwardly, would meet at the center of the globe, which is likewise that of the earth. And for this reason, we say that bodies universally tend toward the center of the earth. Thus, wherever you are placed, when asked what is downward, the answer must be what approaches nearest to the center of the earth. In fact, were you to dig a hole in the earth at whatever place, and to continue your labor incessantly, digging always downward and downward perpendicularly, you would at length reach the center of the earth. You will remember how Voltaire used to laugh at the idea of a hole reaching to the center of the earth, mentioned by Maupertuis. It is true such a project could never be executed, as it would be necessary to dig to the depth of 860 German miles. Footnote: 3,950 miles English. End footnote. But there is no harm in supposing it, in order to discover what would be the result. Let us suppose, then, such a hole, Plate 3, Figure 2, to be dug at A, and continued beyond the center of the earth O, the whole length of the diameter, as far as to our antipodes B, and that we were to descend along this aperture. Before arriving at the center O, and having reached, for example, the point E, the center of the earth O will there appear downward, and the point A upward, and unless something supported us, we should fall toward O. But having passed beyond the center, to F, for example, our gravity would then have a tendency toward O. This point, and much more the point A, would appear downward, and the point B upward. Thus the terms upward and downward would suddenly change their signification, though we should have passed from A to B in the direction of a straight line. As long as we are on the passage from A to O, we are descending. But in going from O to B, we are actually rising, for we are removing from the center of the earth, our own gravity being always directed toward that point, so that, if we were to fall, whether from E or from F, we should always fall toward the center of the earth. Our antipode at B, if he wanted to pass from B to A, would be in precisely the same situation. From B to center O, he would have to descend, but from O to A, it would be all an ascent. These considerations lead us thus to define gravity, or weight. It is a power by which all bodies are forced toward the center of the earth. The same body which, being at A, is forced in the direction AO if transported to B, will be forced, by the power of gravity, in the direction BO, which is directly opposite to the other. By the direction of gravity, then, we everywhere regulate the signification of the terms upward and downward, rise and ascend, as gravity or weight has a very essential influence on all our operations and enterprises, and as even our own bodies are animated by it to such a degree as universally to feel its effects. 29th August, 1760. End of Letter 49. Letter 50 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Read by Verla Vieira. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler. Translated by Henry Hunter. Different action of gravity with respect to certain countries and distances from the center of the earth. You are now sensible that all bodies are forced directly towards the center of the earth and perpendicularly to its surface by their gravity. The perpendicular lines at the surface of our globe are accordingly considered as the directions of the power of gravity. With strict propriety is the term power applied to gravity, as everything capable of putting a body in motion is expressed by that name. Thus we ascribe power to horses, because they are able to draw along a chariot, or to the current of a river, or to the wind, because by their means mills may be put in motion. There can be no doubt, therefore, that gravity is a power, as it forces bodies downward, and we are abundantly sensible of the effect of this power by the pressure which we feel when we carry a load. Now, in every power, two things are to be considered. First, the direction in which it acts or forces along bodies, and secondly, its quantity, which is estimated by the effect it produces. As to the direction of gravity, it is sufficiently known, for we are sure that it forces all bodies toward the center of the earth, or, which amounts to the same thing, that it acts perpendicularly to the surface of our globe. It remains, therefore, that we examine its quantity. This power is always determined by the weight of every body. And as bodies differ greatly with respect to weight, those which are heaviest are likewise forced downward with the greatest violence. Footnote. In order to form an exact idea of the weight of a body, it must be recollected that gravity impresses, or has a tendency to impress, on every particle of bodies, in an instant, a certain velocity with which they would fall if they were not supported, and that, abstracting the influence of the air, this velocity would be the same for each of the particles of bodies, whatever be their substance. This being laid down, we must understand by the weight of a body the effort necessary to prevent it from falling, and it is evident that, in order to this, it is necessary to destroy the velocity which gravity has impressed on every particle. This effort must, therefore, be equal to the sum of the velocities of all these particles. Hence it may be easily concluded that bodies the most compact, that is, those whose particles are the closest, and which, consequently, contain a greater number of them in the same bulk, will weigh more than others, because the weight being the sum of the velocities impressed on each particle, that sum must be so much greater as there are more material particles contained in the mass of the body. From what I have just said, we feel the necessity of carefully distinguishing between the effect of gravity and that of weight. The former is the power of transmitting, or a tendency to transmit into every particle of matter a certain velocity, which is absolutely independent on the number of material particles. And the second is the effort which must be exercised to prevent a given mass from obeying the law of gravity. Weight, accordingly, depends on the mass, but gravity has no dependence at all upon it. I thought myself obliged to enter thus minutely into the subject, as the notions commonly entertained of it are not very exact. F.E. End of footnote. It has been asked whether the same body, transported to a different place of the globe, preserves always the same weight. I speak of bodies which lose nothing by evaporation. It has been demonstrated, by undoubted experiments, that the same body weighs somewhat less toward the equator than toward the poles of the earth. It will readily occur to you that it is impossible to ascertain this difference by the exactest balance, because the standard weights employed for determining the weight of matter in bodies undergo the same variation. Thus, a mass, which with us might weigh 100 pounds, being transported to the equator, would still, nominally, be 100-pound weight, but the effort will be somewhat less than here. This variation has been discovered by the effect itself of the power of gravity, which is the velocity of the descent, for it is found that the same body under the equator does not descend with so great velocity as in high latitudes. It is certain, therefore, that the same body, being transported to different places of the earth, undergoes a little change as to weight. Let us now return to the aperture made in the earth through its center. It is clear that a body at the very center must entirely lose its gravity, as it could no longer move in any direction whatever, all those of gravity tending continually toward the center of the earth. Since, then, a body has no longer gravity at the center of the earth, it will follow that, in descending to the center, its gravity will be gradually diminished, and we accordingly conclude that a body, penetrating into the bowels of the earth, loses its gravity, in proportion as it approaches the center. You must be sensible, then, that neither the intensity nor the direction of gravity is a consequence from the nature of every body, as not only its intensity is variable, but likewise its direction, which, on passing to the antipodes, becomes quite contrary. Having traveled, in idea, to the center of the earth, let us return to its surface and ascend to the summit of the loftiest mountains. We shall observe there no sensible change in the gravity of bodies, though there is a very good reason to believe that the weight of a body diminishes in proportion as it removes from the earth. You have but to imagine a body gradually removing from our globe till it reached the sun, or one of the fixed stars. It would be ridiculous to think that such a body must fall back to the earth, as it is almost a nothing compared to these stars. Hence, then, it may be concluded that a body in removing from the earth must undergo a diminution of gravity, which will become smaller and smaller, till, at last, it wholly disappear. There are reasons, however, which demonstrate that a body removed to the distance of the moon will still have some weight, though 3,600 times less than it had on the earth. Let us conceive such a body to weigh 3,600 pounds on the earth. No one, surely, is capable of supporting it here. But convey it to the distance of the moon, and I shall engage to support it with one of my fingers, for then it will weigh only 1 pound, and farther removed would weigh still less. We are certain, therefore, that gravity is a power which forces all bodies toward the center of the earth, that this power acts with the greatest force at the surface of the earth, and is diminished in proportion as it removes from thence, whether by penetrating toward the center or rising above the surface of the globe. I have still much to say on this subject. 30th August, 1760. End of Letter 50. Letter 51 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Read by Verla Vieira. Letters on Different Subjects in Natural Philosophy, Volume 1, by Leonhard Euler. Translated by Henry Hunter. Gravity of the Moon. I have said that a terrestrial body, placed at the distance of the moon, would be reduced to the 3,600th part of its weight, or, in other words, would be forced toward the center of the earth with a power 3,600 times less than it has at the surface of the globe. This power, however, would be sufficient to make it descend to the earth if it were no longer supported. It is true, we are incapable of proving this by any experiment, as no means exist of raising ourselves to such a height. There is, however, a body at that height, the moon. She must, therefore, be subject to this effect of gravity, and yet we see she does not fall to the earth. To this I answer that if the moon were at rest, she would certainly fall, but the rapid motion which carries her along prevents her falling. There are experiments which prove the solidity of this answer. A stone dropped from the hand, without having any motion impressed upon it, falls immediately in the direction of a straight vertical line. But if you throw this stone, impressing on it a motion which forces it out of that direction, it does not fall immediately downward, but moves in a curved line before it reaches the earth, and this will appear more sensibly in proportion to the velocity impressed upon it. A cannon ball, discharged in a horizontal direction, does not come to the earth till it has got to a considerable distance, and were it fired from the top of a high mountain, it might, perhaps, fly several miles before it reached the ground. If the direction of the cannon is farther elevated, and the quantity and strength of the powder increased, the ball will be carried much farther. This might be carried so far that the ball should not light till it had reached the antipodes, nay, farther still, till it should not fall at all, but return to the place where it was shot off, and thus perform a new tour round the globe. It would thus be a little moon, making its revolutions round the earth like the real moon. You will now please to reflect on the height of the moon and the prodigious velocity with which she moves, and you will no longer be surprised that she should not fall to the earth, though forced by gravity toward its center. There is another reflection which will place this in a clearer light. We have only to consider the path described by a stone thrown, or a cannon ball shot off, in an oblique direction. It is always a curve, such as represented in the annexed figure. Plate 3, Figure 3. Let A be the summit of the mountain from which the cannon ball is fired off, which, after having moved in the direction A, E, F, B, falls to the ground at B, and the path which it describes is a curved line. I remark then that if the ball were not heavy, that is, if it were not forced toward the earth by the power of gravity, it would not fall, though left to itself, as gravity is the only cause of its descent. Much less, being fired off at A, as represented in the figure, would it ever fall to the ground. Hence we see it is gravity that brings it down to the ground after having described the curve AEFB. Gravity, therefore, directs its path in the curve AEFB, and if it were destitute of gravity, the ball would not describe a curve, but proceed forward in the direction of the straight line AC, the direction in which it was fired off. This being laid down, let us attend to the moon, which assuredly does not move in a straight line. Her path must, of necessity, be a curve, as she always preserves nearly the same distance from us, and that curve almost a circle, such as you would describe round the earth, with a radius equal to the moon's distance. It is very reasonable to demand why the moon does not move in a straight line. But the answer is obvious, for as gravity occasions the curved direction of the path pursued by a stone thrown, or a cannonball fired off, there is good ground for maintaining that gravity acts likewise upon the moon, forcing her toward the earth, and that this gravity occasions also the curved direction of her orbit. The moon, then, has a certain weight. She is, of consequence, forced toward the earth, but this weight is 3,600 times less than it would be at the surface of the earth. This is not merely a probable conjecture, but a truth demonstrated. For this gravity being supposed, we are enabled to determine, on the most established mathematical principles, the path which the moon must pursue. And this is found perfectly to agree with that in which she actually does move, and this is a complete demonstration of the truth of the assertion. 1st September, 1760. End of Letter 51.
Letter 52 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Anthony. Letters on Different Subjects in Natural Philosophy. Volume 1 by Leonhard, Euler. Translated by Henry Hunter. Discovery of Universal Gravitation by Newton. Gravity, then, or weight, is a property of all terrestrial bodies, and it extends, likewise, to the moon. It is in virtue of gravity that the moon presses toward the earth, and gravity regulates her motion, just as it directs that of a stone thrown or of a cannonball fired of. To Newton we are indebted for this important discovery. This great English philosopher and geometrician, happening one day to be lying under an apple tree, an apple fell upon his head, and suggested to him a multitude of reflections. He readily conceived that gravity was the cause of the apple's falling by overcoming the force which attached it to the branch. Any person whatever might have made the same reflection, but the English philosopher pursued it much further. Would this force have always acted upon the apple had the tree been a great deal higher? He could entertain no doubt of it. But had the height been equal to that of the moon? Here he found himself at a loss to determine whether the apple would fall or not. In case it should fall, which appeared to him, however, highly probable, since it is impossible to conceive a bound to the height of the tree at which it would cease to fall, it must still have a certain degree of gravity forcing it toward the earth. Therefore, if the moon were at the same place, she must be pressed toward the earth by a power similar to that which would act upon the apple.
Nevertheless, as the moon did not fall on his head, he conjectured that motion might be the cause of this, just as a bomb frequently flies over us without falling vertically. This comparison of motion of the moon to that of a bomb determined him attentively to examine this question, and, aided by the most sublime geometry, he discovered that the moon, in her motion, was subject to the same laws which regulated that of a bomb, and that if it were possible to hurl a bomb to the height of the moon, and with the same velocity, the bomb would have the same motion as the moon, with this difference only, that the gravity of the bomb at such a distance from the earth would be much less than at its surface. You will see from this detail that the first reasonings of the philosopher on this subject were very simple, and scarcely differed from those of the clown. But he soon pushed them far beyond the level of the clown. It is then a very remarkable property of the earth that not only all bodies near it, but those also which are remote, even as far as to the distance of the moon, have a tendency toward the center of the earth, in virtue of a power which is called gravity, and which diminishes in proportion as bodies remove from the earth. The English philosopher did not stop here, as he knew that the other planets are perfectly similar to the earth. He concluded that bodies adjacent to each planet possess gravity, and that the direction of this gravity is toward the center of such planet. This gravity might be greater or less there than on earth. In other words, that a body of certain weight with us, transported to the surface of any planet, might there weigh more or less. Finally, this power of gravity of each planet extends, likewise, to great distances around them. And as we see that Jupiter has 4 satellites, and Saturn 5, which move round them, just as the moon does round the earth, it could not be doubted that the motion of the satellites of Jupiter was regulated by their gravity toward the center of that planet, and that of the satellites of Saturn by their gravitation toward the center of Saturn. Thus, in the same manner as the moon moves round the earth, and their respective satellites move round Jupiter and Saturn, all the planets themselves move round the sun. Hence, Newton drew this illustrious and important conclusion, that the sun is endowed with a similar property of attracting all bodies towards its center by a power which may be called solar gravity. This power extends to a prodigious distance around him, and far beyond all the planets, for it is this power which modifies all their motions. The same great philosopher discovered the means of determining the motion of bodies from the knowledge of the power by which they are attracted to a center. And as he had discovered the powers which act upon the planets, he was enabled to give an accurate description of their motion. In truth, before he arose, the world was in a state of profound ignorance respecting the motion of the heavenly bodies, and to him alone we are indebted for all the light which we now enjoy in the science of astronomy. It is astonishing to think how much of their progress all the sciences owe to an original idea so very simple. Had not Newton accidentally been lying in an orchard, and had not that apple, by chance, fallen on his head, we might, perhaps, still have been in the same state of ignorance respecting the motions of the heavenly bodies, and a multitude of other phenomena depending upon them. Footnote: Newton was asked one day how he had discovered the system of the universe. By continually thinking upon it, replied he. This anecdote has a greater air of probability than the story of the apple. End footnote. This subject, undoubtedly, is altogether worthy of your attention, and shall therefore be resumed in a future letter. 3rd of September, 1760. End of letter 52.
Letter 53 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Prajakta. Letters on Different Subjects in Natural Philosophy, Volume 1 by Leonhard Euler. Translated by Henry Hunter. Letter 53. Continuation of the mutual attraction of the heavenly bodies. The Newtonian system, you will easily believe, made at first a great noise, and with good reason, as no one had hitherto hit upon a discovery so very fortunate, and which diffused at once such clear light over every branch of science. It has been expressed by several names, of which it is proper you should be informed, because it is frequently the subject of conversation. It has been denominated the system of universal gravitation, for Newton maintained that not only the earth but all the heavenly bodies in general are endowed with this property of attracting those which surround them with a power familiar to that of weight or gravity. Hence is derived the term gravitation. This power is, however, totally invincible, for we see nothing acting upon bodies and pressing them toward the earth, and still less toward the heavenly bodies. The lodestone by which iron and steel are attracted, without our being able to discern the cause, presents a phenomenon somewhat familiar, though it be now certain that this is produced by a substance extremely subtile, which penetrates through the pores of the lodestone and of the iron. It may, however, be affirmed that the lodestone attracts iron, and that iron is attracted by it, provided this manner of speaking does not exclude the true cause. It may likewise be affirmed then that the earth attracts all bodies that are near it, say those which are at very great distances, and we may consider the weight or gravity of bodies as the effect of the attraction of the earth, which acts even upon the moon. Footnote: so far is the existence of a magnetic fluid from being undeniable that it is highly improbable, if not absurd. The various phenomena of magnetism may clearly be derived from two laws or general facts, than which a greater simplicity can hardly be expected. If we recur to the agency of a fluid, we must gratuitously bestow on it a number of properties, and after all, we shall find it extremely difficult, I might say impossible, to preserve consistency in our complicated hypothesis, nor shall we ever be able from our assumptive principles to account for the facts observed. Such at least has been the fate of Speculations hitherto offered on the subject of magnetism. EE. End footnote. Again, the Sun and all the planets are endowed with a similar power of attraction which extends to all bodies. In conformity to this manner of speaking, we say that the Sun attracts the planets and that Jupiter and Saturn attract their respective satellites. Hence, Newton's system has likewise been denominated the system of attraction. As there can be no doubt that bodies very near the moon must likewise be pressed to it by a power of similar to gravity, it may likewise be affirmed that the moon too attracts adjoining bodies. It was natural to suppose that this attraction of the moon should extend as far as the earth, though it must be undoubtedly very feeble, as we have seen that of the earth upon the moon to be. Now, the same philosopher has placed this also beyond the reach of doubt by demonstrating that the flux and reflux of the waters of the sea, of which I shall take occasion to speak afterwards, are caused by the attraction of the moon. It can no longer be doubted, therefore, that Jupiter and Saturn are reciprocally attracted by their respective satellites, and that the Sun itself is subject to the attraction of the planets, though this attractive power be exceedingly small. This is the origin of the system of universal attraction, in which it is maintained, and with good reason, that not only does the Sun attract the planets, but is reciprocally attracted by each of them, nay, that all the planets exert their attractive power upon each other. The earth then is attracted not only by the Sun but also by all the other planets, though their power be almost imperceptible compared to that of the Sun. You will easily comprehend that the motion of a planet, which is attracted not only by the Sun but by the other planets, in however small a degree, must be somewhat different from what it would have been were it attracted by the Sun only, and that consequently the attractions of the other planets must cause some small derangement of that motion. Now, their derangements are likewise confirmed by experience, and this has carried the system of universal attraction to the highest possible degree of certainty, so that no one now presumes to dispute its truth. I must likewise remark that comets too are subject to this law, that they are principally attracted by the Sun, whose action regulates their motion, but that they likewise feel the attractive power of all the planets, especially when they are not very distant from them. It is a general rule, as we shall see afterwards, that the attraction of all the heavenly bodies diminishes in proportion to the distance and increases in proportion to the nearness. Now, comets likewise are endowed with a power by which other bodies are attracted toward them, and so much the more sensibly as they approach nearer. When therefore a comet passes somewhat more closely to a planet, it may derange the motion of that planet by its attractive power, and its own will likewise be disturbed by that of the planet. Their consequences are verified by real observation. Examples might be adduced to prove that the motion of a comet has been deranged by the attraction of the planets near which it happened to pass, and that the motion of the earth and of the other planets has already undergone some derangement from the attraction of comets. The fixed stars, being bodies similar to the Sun, are likewise endowed, no doubt, with an attractive power, but their enormous distance prevents our feeling any sensible effect from it. Footnote: the comet of 1682, which should have reappeared in 1757, underwent from the attractive powers of Jupiter and Saturn, near which it passed, a considerable derangement which retarded its appearance nearly 2 years. Mr. Claret calculated theoretically the perturbations which its motion must have suffered, and predicted the return of that comet with a degree of exactness which constitutes a convincing proof in favor of the system of gravitation. There was, however, an error of 2 months, but Mr. de Laplace has since demonstrated that it would have been much less had we then been able to calculate the perturbations of Jupiter and Saturn with as much exactness as it now can be done. F.E. Footnote complete. 5th September 1760. End of letter 53. Letter 54 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Prajakta. Letters on Different Subjects in Natural Philosophy, Volume 1 by Leonhard Euler. Translated by Henry Hunter. Letter 54. Different sentiments of philosophers respecting universal gravitation, the attractionists. It is established then by reasons which cannot be controverted that the universal gravitation pervades all the heavenly bodies by which they are attracted toward each other, and that this power is greater in proportion to their proximity. This fact is incontestable, but it has been made a question whether we ought to give it the name of impulsion or attraction. The name undoubtedly is a matter of indifference, as the effect is the same. The astronomer, accordingly, attentive only to the effect of this power, gives himself little trouble to determine whether the heavenly bodies are impelled toward each other or whether they mutually attract one another, and the person who examines the phenomena only is unconcerned whether the earth attracts bodies or whether they are impelled toward it by some invisible cause. But in attempting to dive into the mysteries of nature, it is of importance to know if the heavenly bodies act upon each other by impulsion or by attraction, if a certain subtle invisible matter impels them toward each other, or if they are endowed with a secret or occult quality by which they are mutually attracted. On this question, philosophers are divided. Some are of opinion that this phenomenon is analogous to an impulsion. Others maintain with Newton and the English in general that it consists in attraction. It must be observed that the terms attract and draw are not perfectly synonymous, that accordingly it is not to be supposed there is an intermediate body between the sun and the earth. The English and those who have adopted the same opinion explain it in this manner. They maintain that the quality of mutual attraction is proper to all bodies, that it is as natural to them as magnitude, and that it is a satisfying solution of the question that the Creator willed this mutual attraction of bodies. Had there been but two bodies in the universe, however remote from each other, they would have had from the first a tendency toward each other, by means of which they would have in time approached and united. Hence it follows that the greater a body is, the more considerable is the attraction which it exerts upon others, for as this quality is essential to matter, the more of it any body contains, the greater is its attractive force. As the Sun, therefore, considerably surpasses all the planets in magnitude, its attractive force must be much greater than theirs. They likewise remark that the mass of Jupiter being much greater than that of the Earth, the attractive force which he exercises over his satellites is much more powerful than that with which the Earth acts upon the Moon. According to this system, the gravity of bodies on the Earth is the result of all the attraction exercised upon them by the particles of our globe, and if it contained more matter than it actually does, its attraction would become more powerful and the gravity of bodies would be increased. But if, on the contrary, the mass of the earth should happen by some accident to be diminished, its attractive force too would be diminished, as well as the gravity of bodies at its surface. It has been objected to these philosophers that, on their hypothesis, any two bodies, whatever at rest, for instance, on a table, must attract each other and consequently approach. They admit the consequence, but they insist that in this case the attraction would be too small to produce any sensible effect, for if the whole mass of the earth by its attractive force produces in every body only that effect which we perceive in the weight of a body, a mass many millions of times smaller than the earth will produce an effect as many times smaller. It must readily be admitted that if the weight of a body became many millions of times less, the effect of gravity upon it must be reduced to almost nothing. Attraction, therefore, cannot be perceptible except in bodies of very great magnitude. The partisans of the system of gravitation, therefore, are not vulnerable on this side, and they produced, in support of their opinion, an experiment made in Peru by the French academicians, in which they perceived the slight attraction of a prodigious mountain on adjacent bodies. In adopting, therefore, the system of attraction, we need to be under no apprehension of its leading us to false consequences, and it has hitherto been always confirmed by the new facts which have been discovered. Footnote: the academicians sent to Peru in 1735 to measure a degree of the meridian observed a deviation of 8 degrees in the plumb line of their quadrant, occasioned by the attraction of Pichincha, a mountain near the place where they were making their observations. Dr. Markelin has more recently made observations for ascertaining the effect of the attraction of the mountains of Scotland. F.E. Footnote complete. 7th September 1760. End of letter 54. Letter 55 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Prajakta. Letters on Different Subjects in Natural Philosophy, Volume 1 by Leonhard Euler. Translated by Henry Hunter. Letter 55. Power by which the heavenly bodies are mutually attracted. You are well acquainted with the property of the lodestone, that of attracting iron. You have seen small bits of iron and steel, such as needles, when placed near the lodestone, move to it with a force proportional to their proximity. As you see nothing that impels them toward the lodestone, we say that the lodestone attracts them, and this phenomenon we call attraction. It cannot be doubted, however, that there is a very subtle, though invisible matter which produces this effect by actually impelling the iron toward the lodestone. But as modes of expression are regulated by appearances, it has become customary to say that the lodestone attracts iron. Though this phenomenon be peculiar to the lodestone and iron, it is perfectly adapted to convey an idea of the signification of the word attraction, which philosophers so frequently employ. They allege, then, that all bodies, in general, are endowed with a property similar to that of the lodestone, and that they all mutually attract, but that this effect becomes not perceptible unless they are very, very great, and cannot be perceived when they are small. However great, for example, a stone may be, It exercises no sensible attraction on other bodies adjacent to it because its power is too small. But if its mass were to increase and to become many thousands of times greater, its effect would at length become perceptible. It has already been remarked that from actual observation it was found that a lofty mountain in Peru had produced attraction, though indeed in a very small degree. A mountain still greater would produce, therefore, a more sensible attraction, and a body much greater, such as the whole globe, would attract others with a force proportionally greater, and this force would be precisely the gravity with which we see that they are actually impelled toward the earth. According to this system, then, the gravity which obliges all bodies to descend is nothing else but the result of the attraction of the whole mass of the earth. If this mass were greater or less, the gravity or weight of bodies would be proportionally greater or less. Hence, it follows that all the other great bodies in the universe, as the sun, the planets, and the moon, are endowed with a similar attractive power, but greater or less in proportion as they themselves are so. As the sun is many thousands of times greater than the earth, his attractive power exceeds that of the earth so many thousand times. The mass of the moon is calculated to be 40 times less than that of the earth. It will follow that her attractive force is so many times less, and the same rule applies to all the heavenly bodies. 9th September 1760. End of letter 55. Letter 56 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Prajakta. Letters on Different Subjects in Natural Philosophy, Volume 1 by Leonhard Euler. Translated by Henry Hunter. Letter 56. The same subject continued. In virtue of the system of attraction or universal gravitation, each of the heavenly bodies attracts all the rest and is reciprocally attracted by them. In order to form a judgment of the force with which their bodies attract the others, we have only to consider two bodies whose attraction is mutual. And here we must attain to three things. First, to the body attracting, secondly, to the body attracted, and finally, to their distance. For on these three circumstances, the attractive power depends. Let A, plate 3 figure 4 be the attracting body and B the body attracted, both of them spherical, the heavenly bodies being nearly of this figure. Take for their distance that of their centers A and B, that is, the straight line AB. Now, with respect to the mass of the attracting body A, it must be remarked that the greater it is, the greater also will be its power to attract the body B. Consequently, if A were twice as great as B, this last would feel an attraction twice as powerful exercised over it by the other. If it were three times as great, the effect would be triple, and so on, always supposing the distance of their centers to be the same. If then the earth contained more or less matter than it actually does, it would attract all adjacent bodies with greater or less force, or their weight would be increased or diminished. And as the earth itself is attracted by the sun, the same thing might be affirmed as to it, should the mass of that luminary happen to change. As to the attracted body B, supposing the attracting body A and the distance AB to continue the same, it is to be remarked that the greater or smaller its mass is, the greater or less also is the power with which it is attracted toward A. Thus, if the body B were twice as great, it would be attracted toward A with double the force, if three times greater, with triple the force, and so on. In order more clearly to elucidate this remark, we have only to substitute the earth in the place of the attracting body A, then the force with which the body B is attracted is nothing else but the weight of that body. Now, it is demonstrated that the greater or smaller the body B is, the greater or less also is its gravity. Hence, it follows that while the attracting body A and the distance AB continue the same, the attraction which B feels precisely follows the magnitude of that body. To express this circumstance, mathematicians employ the term proportional. Thus, they say the body B is attracted by the body A with a force proportional to its mass, the meaning of which is that if the mass of body B were twice, thrice, or four times greater, the attractive power would be precisely so many times increased. Thus, with respect to the attracting body A, they say that the power which it exercises over the body B is proportional to its mass so long as that of B and the distance AB continue the same. I must further observe that when we speak of the quantity of the attracting body A or of the attracted body B, we mean the quantity of matter which each contains and not their magnitude merely. You will recollect that bodies differ considerably in this respect and that there are some which in a very small compass contain a great deal of matter, gold for example, while others, such as air, contain very little in great space. When therefore we here speak of bodies, we are always to be understood as referring to the quantity of matter which they contain. This is what we mean by their mass. All that now remains is to examine the third circumstance, namely the distance AP of the two bodies, supposing them to continue always the same. It must be observed that as the distance AB increases, the attraction diminishes, and that as they approach nearer, it increases, but in conformity to a law which it is not so easy to express. When the distance becomes twice as great, the force with which the body B is attracted toward the body A will be twice too, or four times less, and for triple the distance, the attraction becomes 3 times 3, that is 9 times less. If the distance becomes 4 times greater, the power of attraction becomes 4 times 4, that is 16 times less, or so on. Finally, for a distance 100 times greater, the power of attraction will be 100 times 100, or 10,000 times less. From this it follows that at very great distances it must become altogether imperceptible, and reciprocally, when the distance AP is very small, the attraction may be very considerable, though the bodies may be of no great magnitude. 11th September 1760. End of Letter 56. Letter 57 of Letters on Different Subjects in Natural Philosophy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Prajakta. Letters on Different Subjects in Natural Philosophy, Volume 1 by Leonhard Euler. Translated by Henry Hunter. Letter 57. The same subject continued. I have now demonstrated that when a body B is attracted by a body A, the power of attraction is proportional to the mass of the attracting body A and to that of the attracted body B, but it depends to such a degree on the distance of these bodies that if it should become twice, thrice, four, or five times greater, the power of attraction would become 4, 9, 16, or 25 times less. In order to ascertain the rule of these quantities, we must multiply into itself the number which marks how many times the distance is increased, and the product will show how many times less the power of attraction has become. To put this rule in its clearest light, it must be observed that when we multiply a number into itself, the product resulting from it is called its square. Thus, to find these squares, we must multiply the numbers by themselves as below. 1 multiplied by 1 is 1, 2 multiplied by 2 is 4, 3 multiplied by 3 is 9, 4 multiplied by 4 is 16, 5 multiplied by 5 is 25, 6 multiplied by 6 is 36, 7 multiplied by 7 is 49, 8 multiplied by 8 is 64, 9 multiplied by 9 81, 10 multiplied by 10 100, 11 multiplied by 11 121, 12 multiplied by 12 144. It is clear from this last example that the square of number 12 is 144, and if you wish to know the square of any number whatever, say 258, you must multiply that number by itself as in the following separation. 258 into 258, 66,564, from which we see that the square of 258 is 66,564, and the squares of all numbers whatever may be calculated in like manner. As the distance of bodies then must be multiplied by itself, it is evident that the power of attraction diminishes as much as the square of the distance increases, or that the square of the difference becomes as many times greater as the power of attraction is diminished. In treating subjects of this nature, mathematicians employ expressions whose signification it is proper you should know because they sometimes occur in the course of conversation. If the attractive power increased in proportion to the square of the distance, we would call it proportionally to the square of the distance, but as the direct contrary takes place and as the attractive power diminishes as the square of the distance increases, we employ the term reciprocally to express this contrariety, saying that the power is reciprocally proportional to the square of the distance. It is geometrical mode of expression, the meaning of which you perfectly comprehend, and it refers to what I have just been attempting to explain. In order to judge aright of the power which one body exercises over another, you have only to remark that this power is, first of all, proportional to the mass of the attracting body, then to that of the body attracted, and finally reciprocally to the square of their distance. Hence, it is evident that though the Earth and the other planets are likewise attracted toward the fixed stars, this power must be imperceptible on account of their prodigious distance. Supposing, therefore, the mass of a fixed star to be equal to that of the Sun at equal distances, the Earth would be attracted toward it with a force as great as toward the Sun. But as the distance of the fixed star is 400,000 times greater than that of the Sun, the square of this number being 160,000,000,000,000,000, that is 160,000 millions, the power with which it acts upon our globe is 160,000 millions of times less than that of the Sun, and consequently too feeble to produce any perceptible effect. For this reason, the attractive power of the fixed stars does not at all affect the Earth's motion, nor that of the planets and the moon, but it is that of the Sun which chiefly regulates their motions, because his mass exceeds many thousands of times the mass of each planet. When, however, two planets approach so that their distance becomes less than that of the Sun, their attractive power increases and may become sufficiently perceptible to derange their motion. Such derangement has in fact been observed and constitutes an irresistible proof of the system of universal gravitation. Accordingly, when a comet approaches very near to a planet, the motion of this last may be considerably affected by it. 13 September 1760. End of letter 57.